Hello and welcome, I'm your Code Monkey, and here is my awesome 7-hour free tutorial video all about learning Unity dots and making an awesome RTS. The final game has lots of units, lots of buildings and zombies. It has resources, fog of war, ragdolls, destruction, zombie hordes, and tons more. In order to build all of this, we're going to learn all about Unity dots. This is Unity's super performant tool stack. It can make your code run literally 200x faster. That is really insane. With this massive speed up, you can make more complex, more ambitious, more interesting games. Or it simply helps your games hit 60 FPS much more easily, or helps keep battery consumption low on mobile. So this kind of extreme performance has a ton of really awesome benefits. We're going to learn all about dots, starting from the absolute basics, starting from literally what exactly is dots, what is an entity, a component, and a system. Then we're going to learn what is the job system, what is the burst compiler, and what exactly is the syntax to build all of this. We're going to learn about dots physics, how to handle authoring and runtime data, learn how to do all kinds of queries, and tons more. So we're going to start completely from scratch and learn each of these dots concepts one by one, slowly, bit by bit, over the course of about 80 lectures. Now, I worked super hard to make this course have a really nice, smooth learning curve. Based on the comments from students, I did achieve that. But with that said, dots is still very much an advanced topic. This is not for beginners. If you are a beginner, then just stick with game objects and don't worry about dots for now. Just keep learning the basics and get a nice foundation before learning about dots. For beginners, you can check out my free Catch and Chaos course on making a game from start to finish, all with normal game objects, and then a second one on making it multiplayer. Alternatively, you can check out my free C# course. If you understand everything in that course for both the beginner and the intermediate sections, if so, then you're ready to learn about dots. Or if you've gone through my turn-based strategy course, if you managed to go through that one, through that entire thing, then yep, you do have the skills needed to start learning about dots. So if you are a beginner, then don't worry about dots. But if you're not, if you're past the beginner stage, if you're in the intermediate or advanced level, if so, then yep, I highly recommend you learn about this really awesome toolset. Like I said, the benefits are immense. You can run code over 200 times faster compared to normal game objects. This allows you to make more complex, more ambitious, more interesting games. So this is definitely a very, very powerful toolset that you should know how to use. Now in this video over here, this free 7-hour video, this contains the first 7 hours of the course. The full course is about 17 hours long, so if you want to get the whole thing, then check the link in the description. That one contains the full course alongside bonuses like obviously having no ads. Then the videos are split into separate lectures. It also grants you access to my private Discord and my private weekly live streams. But over here in this free video, this still has a ton of knowledge. I made sure to include as much dots knowledge as possible over here in the first few hours, specifically to make this free video really valuable. So even if you can't afford the full course, you can still learn how to use dots completely for free with this video. I think dots is an absolutely awesome piece of tech. I really love what Unity built with it, and I really want everyone to be able to learn this awesome tech. It's going to be really interesting to see the games that come up in the next few years as people learn more and more how to work with this. So I'm really hoping that this free video helps a ton of people learn how to use this awesome tech. If you want to get the full 17-hour course without any ads to interrupt you and with all the bonuses, if so, then check the link in the description. But if you can't afford it, then that's fine. I hope you'll learn a ton from this awesome free video. And one final request, if you find this free video helpful, if so, then hit the like button and subscribe to the channel. It's a small thing, but it really does help. Alright, so with the intro out of the way, let's begin making an awesome RTS and learning all about dots. So let's start the course in the next lecture. Hello and welcome, I'm your Code Monkey. Welcome to my Unity dots course. Here we're going to learn all about dots, which is Unity's super performant tool stack. It requires us to learn a different way. It requires us to learn about data-oriented programming as opposed to object-oriented. So that requires a different way of thinking. And by learning this, we're actually going to get some massive performance benefits. Those will allow us to make games with tons of complexity so you can bring whatever vision you have to life. And despite being a big change, changing from OOP to DoD, that change is actually not as intimidating as it sounds. We're going to start from the absolute basics of dots and slowly, step by step, increase in complexity. So by doing that, the learning curve will actually be quite smooth. And by the end, you will have gained an insanely powerful tool that you can use in making whatever games you want to make. Now, like I mentioned in the course page, this is not a beginner level course. So I'm assuming you're already at the intermediate level. I assume you know what is a game object, what is a transform. I assume you know your way around Unity. I assume you know what are generics, events, and singletons, and just basic C# knowledge. So I assume you are intermediate, but when it comes to the topic of dots, I will teach everything starting from the absolute scratch. Since one of the primary goals of dots is to enable massive performance with tons of objects moving around, because that, naturally, one excellent genre for learning about this tool stack is making an RTS game, which is what we're going to do. This involves lots of units and lots of logic being applied to lots of objects at once. Doing an RTS game using game objects, that requires quite a lot of trickery to make it performant. Whereas over here, by using dots, as long as we do it properly, we're pretty much going to get awesome performance by default. In the final game, we're going to have tons of units fighting tons of zombies. We're going to have multiple buildings, unit spawning, resource gathering, massive zombie hordes. We're going to learn how to create flow field pathfinding, how to do fog of war, how to create a minimap. set up zombie building spawners, handle shooting, melee attacks, different unit types, and so on. We're going to learn how to do dots animation, learn about the various sorts of dots, like how the baking system works and what exactly has structural changes, as well as how to combine dots and game objects in various ways. So all of this will be built step by step. There is no code written off screen. All of the lectures also have the downloadable project files, so if you get lost at any point, you can just download the exact same project files that I'm using and continue from there. And as usual, I'm always available in the comment section to answer any questions you have. So now let's see the final game that we're going to build in this entire course. Let's see that in the next lecture. Hello and welcome, I'm your Code Monkey. Here, let's look at the final game we're going to build throughout this entire course. Alright, so we start off with a super simple main menu. This means we're going to handle all about scene loading and dots. So let's go ahead and just play. And yep, this is our game. So we have a bunch of units, we have some resources, we have a nice UI, we've got buttons, we've got a minimap, we've got special skills, so we've got all kinds of things. This is an RTS game, so naturally we can click to select and move a whole bunch of units. So I can click to draw a selection area and move them around. And there you go, there are some zombies, so as the entities get close enough to a zombie, they start attacking, they start shooting. Then the zombies also have some really nice satisfying ragdoll, so as soon as they die, they fall down. They also have the health bar over there on top of the unit itself. So they walk around, they deal all kinds of damage. Then over here we can also see the fog of war in action. So we can see there's a persistent dark fog of war, so that one has been unexplored. Whereas if we do explore it and we go back, yep, now that area becomes explored. Then the game has a nice horde system, so every once in a while we get a horde, so we can move around. And of course we can also spawn some buildings. So let's place down a tower. This one takes some resources. So we can place down a bunch of towers. They also have rules, so they cannot be placed way too close to one another. So they need to be a little bit further apart. So place down a bunch of towers. Let's prepare for the horde that is coming. Let's clear off all those zombies. And yep, here we have the first zombie horde coming. This one is pretty simple. And another nice mechanic is our special skill. So here we have the airstrike, which is triggered once we kill enough zombies. So I can click, and there you go. And after a while, a bunch of helicopters come in. They drop a bunch of bombs, and there you go. Everything drops down. So yep, it's a really nice special skill. Then on the buildings that we can build, naturally we can build a barracks. So that is one from where we spawn our units. Then we can spawn a whole bunch of harvesters. So this one over here, this one in light gray, this one is actually an iron harvester. Except of course we need to be able to afford the cost, so we need some gold. Up there we can see our resources. And there's another horde, so let's actually defend from it. So up here we have a gold node, so I can place a gold harvester, place it next to the gold node. And there you go, the building starts doing construction. So it spawns from the bottom and starts going up. So it has a nice construction state. So it goes, and once it gets fully built, yep, the building also has a view radius, so it can see the area around it. And there's some nice visual drones to gather around and gather some resources. So we can start gathering that. We can start placing down a whole bunch more buildings. So let's place down some more gold harvesters, place them all. Then over there, let's defend from this horde. The towers themselves, they also defend, but they also can be destroyed. Then over here on the barracks, naturally we can spawn some units. So we can spawn either soldiers or scouts. The scouts deal less damage, but they wall quite a bit faster. So we can spawn either of those and select a bunch of them and prepare for the next horde that is coming in. So let's spawn a whole bunch of them. We can right-click in order to give it a different rally point. So the units are spawning and they're going to come over here. Let's spawn another nice airstrike. And boom, there you go, everything blows up. So yep, we keep fighting a bunch of zombies as the hordes keep coming in. Also, naturally, the game does have pathfinding, so we cannot walk through these walls, so the units have to go around it. So this using some nice full field pathfinding. Then the buildings also have some nice satisfying destruction. So they've got the health as they are destroyed. Yep, there you go, they blow up into nice pieces. Then the ultimate goal of the game is to simply destroy all the zombies. So we need to explore the entire map, destroy all the zombies, and then we win. So there's only a few more zombies, so just take them out. And as soon as the counter reaches 0, yep, there you go, you win, and we have control of the entire map. Alright, awesome! So yep, this is the game that we're going to build in this entire course. We're going to build this, all of these mechanics, all of this, everything step by step, starting completely from scratch. So we're going to learn how to make all of these awesome RTS mechanics, and we're going to learn all the awesome dot stuff that makes all of this game work. So now let's see a quick overview of all the steps we're going to take in this entire course. So let's see that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to see a quick overview of the entire course. So all the lectures and all the things we're going to learn and build step by step until the final polished game. Okay, so we're going to start off with a lecture mostly focused on the theory behind dots. So what exactly is it? What are all the components to it, like ECS, job system, and burst? And just basically get a nice overview of the whole tool stack before we start using it. Then we're going to start the section for creating and setting up our project. First, create the project and install all the packages. Then we're going to set up our Unity layout. After that, set up our Visual Studio. Then import the first batch of visual assets that we're going to use. After that, set up the post-processing and lighting. And with that done, we will have our complete setup. And in order for you to follow everything exactly the same as I have in this course, this is the part where I will tell you to download the project files to use. So this way, use the exact same project as me with everything using the exact same versions. That way there is no confusion. Then we start actually building our game. So first learning about .subscene baking. What is it and how do we convert game objects into entities? Next, we're going to create our first super simple component. Components store some data. So we're going to do that and set up our unit structure. Again, all while using normal game objects and the baking system. With that done, we're then going to create our very first system. It's going to be the unit mover system, which like name implies will move our unit. Meaning that at this point, we will have seen the basics of entities, components, and systems. Then we take that movement system and we're going to refactor it to use dots physics instead of moving the object transform. This is super easy to do thanks to the dots baking system. We're going to work with normal physics components and everything just works. Then, since this is an RTS game, we're going to need the mouse wheel position, so we're going to calculate that. This is also a super important lecture because it will teach us that not every system needs to be dots. We can and we will have normal monobehavior scripts and dot scripts, both of them working together. Then with the mouse position, we're going to use that logic to tell the unit to move to the mouse. And then here is another super important lecture. We're going to refactor our movement code to turn it into a super fast job using the job system. We're going to see the actual numbers behind normal main threaded code and super fast burst enabled multi-threaded code. The difference is literally 100x. Next, we're going to handle unit selection. First, just setting up the component to select just one unit, and then we're going to be selecting multiple units. This means we're going to set up our UI and do some math to be able to draw a selection area and select multiple units. This is another great example of interacting with the dot swirl from a normal monobehavior script. Next, we're going to handle selecting a single unit by clicking on it. This is another fun lecture because it requires us to learn about dots physics and how to do a dots raycast. Then we're going to generate some move positions for a unit to go to. That way they don't all go to the exact same spot. This is basically where we can draw our own unit formations. Next, we're going to have a very important lecture, learning how to do events in dots. This is actually really tricky because normally events require objects and delegates, so finding a data-oriented approach for events is a really interesting challenge. Then we're finally going to create some zombies to play with, create the enemies, and define what is the concept of a faction. After that, we're going to build our find target system. So this system, coupled with the concept of factions, will work for both zombies and friendly units. It will work for both for finding units of the opposing faction, and this also requires us to work with dots physics to find nearby potential targets. Then we're going to implement the concept of health, create a component to store some data and systems to handle death, then create a visual bullet that we're going to fire, set up the component and system to make it move towards the target and damage. Next is another really important lecture where we're going to learn all about entity spawning. This has some interesting implications with regards to the concept of structural changes. After that, we're going to polish some things in our shoot logic, then set up a simple component and system for spawning zombies. Then we're going to make them randomly walk around. This requires us to learn how to use the random class that is burst compatible, which works in quite a different way than you might be used to. Next, setting up a visual health bar. This also requires an interesting setup to make sure that the bar is rendered using the dots renderer and is scaled correctly. Then we're going to polish up the shooting with some nice lights. So this one is a great example of how we can use dots companion game objects. After that, we're going to implement melee attacks. So our zombies will be able to approach our soldiers and damage them. Then we're going to implement a move override logic. This will let us have full control of our units, even while they are trying to attack an enemy. Next is a simple lecture, learning about required for update. This is how we can define a required component before a system updates, so this helps us solve issues with singletons not existing. Afterwards, we're going to do some refactoring to make our find target system always find the closest target. This is a simple change. This lecture is actually a great example of how refactoring is a perfectly normal part of the process. First we make the find target system, and then we add some more logic onto it. Then, continuing with targets, we're going to implement the logic to lose a target. Make it so that if the target is too far, it just gets reset. Then create a simple component to override a target. This allows the player to target a specific unit, regardless of any others being closer. And for another target logic, we're going to set the target when hit. So when a zombie gets attacked, it will target the unit that attacked it. After that is another nice refactoring lecture. This one is all about performance, all about refactoring normal systems and making them into super fast bursted jobs. Like I said, this is how you should do it. First get it working with a simple system for each, then refactor it all into a super fast job. This lecture is very, very important. This kind of refactoring is a core part of dots. Next, we're going to see an important section. This one is all about how to create a custom animation system. Right now, dots does not have any animation support, so we need to build the system ourselves from scratch. This is going to be a fun challenge. First, we're just going to see an overview of how we're going to implement it, and then we're going to start building off the basics, preparing everything so we can build upon it. Next, we're going to learn about dots blob assets. This is the main way that you can store large amounts of data in an easy-to-read structure. We're going to use blob assets to basically store all of our animation data. Then we're going to build upon it to store multiple animation data. This requires being a little bit tricky with how we set up the blob asset. After that, we're going to learn how to change animations on the fly. For example, go from idle to walk animation. Then with that done, we're going to implement some events so we can play our animations when they should. We're going to implement the idle and walk animations. And after that, we're going to work on the attack animations. This is also going to be a tricky one because some animations should be interrupted and some should not. After that, we're going to do the same thing we've done several times. It's time to refactor a normal system into a super fast burst job. Then with the custom animation system fully working, we're going to fix one sneaky issue that always happens. It has to do with subscenes and how there are some errors that only show up if the subscene is closed. So by solving this issue, it actually requires us to learn how to make a custom baking system. After that, for a simple lecture, we're going to implement a scout unit. This is a unit that is meant to be faster and deal less damage, so they're really meant for exploration. This is going to be an important lecture to learn how our game can support multiple unit types. Next, we're going to create the zombie building spawner. Zombies are going to spawn from this building with certain rules, and they're going to keep spawning until that building is destroyed. Then we're going to make a friendly building, the defensive tower. This one will target nearby zombies and automatically attack them. This lecture is really a great example of the power of dots. We're going to build this tower really quickly thanks to reusing a ton of previously made components and systems. Next, we're going to create a proper scriptable object to keep track of all of our building types. After that, we're going to work on a really interesting building, the barracks. This is where we're going to spawn our units, meaning we need to keep track of some kind of unit spawn queue, which means we're going to learn about dots dynamic buffers. This is how we can store multiple pieces of data in just one dots component. Then we're going to build a UI for our barracks, add some nice buttons to queue up some units. At that point, we're going to have multiple buildings working, so it's time to work on a building placement manager so we can place down multiple buildings. First, we're going to handle the logic for the placement, and then we're going to build the UI to match. We're going to add some buttons so we can select what building we want and then click to place it. Then we're going to create another building. This one is going to be the special HQ building. If the zombies destroy this building, then it's game over. Next, we're finally going to create a simple camera manager. This one will be made using Cinemachine 3.0. It's going to be a nice camera controller where we can move, rotate, and zoom the camera. Then another refactoring lecture. This one is going to be on fixing some memory leaks. After that is another handful of very important lectures that make up the grid system and the pathfinding section. First, we're going to see a quick overview of the grid system, how we're going to make it work with dots, which again, that's important. Then we're going to start implementing that design, again, making sure it's all data oriented. After that, we're going to build a nice visual debug. This will be very helpful as we build the pathfinding. Speaking of that, we're then going to see an overview of the pathfinding that we're going to implement. In this course, it's going to be the flow field pathfinding, which has some nice benefits when compared to A-star pathfinding, especially when it comes to having tons of units. So this is the algorithm that we're going to go with. After that, we're going to start implementing the pathfinding system, write the entire algorithm, and make it all work. Next, we're going to make use of our debug visual to make sure it's all working, make sure that all the arrows point in the right direction to reach the target, and then of course, pathfinding needs some walls, so we're going to add those. We're going to do it in such a way that we can easily place them in the editor, and they are automatically identified as walls by the algorithm. Next, once the path is calculated, we're going to make our units follow it. So first, just a quick overview of all the components we're going to build to help us do that, and then we start implementing the flow field follower. Like the name implies, this one makes a unit follow a certain flow field. It just looks at the vector on the grid position under it and follows it until the destination. After that, we're going to apply that logic to multiple units, being able to give orders to tell each unit where to go to. Then another very important lecture. This one is all about how exactly do we handle pathfinding for multiple units to multiple targets if the path cannot be saved. This is going to be a tricky one. We're going to end up solving this issue by storing multiple flow fields. After that, we're going to optimize our pathfinding in some simple ways. We're going to do some Raycast to basically ensure that we only use pathfinding when we absolutely need to. Next, we're going to go through all of our code and make sure that all movement is using pathfinding. Then make sure the underlying flow field gets updated based on obstacles spawning and being destroyed. And then another awesome refactoring lecture. We're going to take all of our pathfinding code and refactor it into super fast bursted jobs. After that, we're going to implement some nice fun RTS mechanics, starting off with a minimap. Units and buildings have icons that show up on the minimap, which we can easily see. Next is another fun mechanic, implementing a fog of war. This is a pretty interesting one. Our units have a visibility radius, and enemies are only visible inside of it. Then, as units move, it also has two pieces of fog of war. There's the immediate one and the persistent one. So as units explore the map, some parts of it become permanently revealed. Once again, the zombies are only visible in the active fog of war. After that, for some more RTS mechanics, we're going to implement the concept of resources and make some buildings harvest them. They need to be placed near resource nodes to start gathering resources. Next, we're going to put those resources to good use by implementing some costs to our buildings and our units. After that, we're going to make sure that our buildings have a construction stage. They will take some time to construct instead of just spawning fully constructed right away. Then we're going to implement a pretty nice horde mechanic. This is pretty simple. Every certain amount of time, we're just going to have a massive amount of zombies spawn somewhere in the world and simply attack the HQ. Next, for a really fun lecture, we're going to implement some ragdolls. This is another tricky one because DOTS does not support skin mesh renders, so we're going to need to be clever to handle this. As the enemies die, they spawn a ragdoll and fall to the ground in a very satisfying manner. Then we're going to make a simple main menu. Doing so requires us to learn how to properly handle multiple scenes in DOTS. This is another interesting question since DOTS doesn't really have the concept of scenes. All systems exist at all times. After that, we're going to take all of our game elements and make a nice playable map. It will have walls, resource nodes, zombie buildings, hordes, and a bunch more. And then another fun lecture, another nice performance refactoring session. We're going to use the profiler to figure out how to optimize a bunch of our systems. And finally, we have the polished lecture. This one includes a ton of tiny things like adding a horde UI indicator, adding a counter for zombies and zombie buildings, adding some screen shake, some building particles, some destruction pieces, a nice airstrike mechanic, and a bunch more. After all that, yep, our game will be fully complete and really awesome. So as you can see, we're going to go step by step from a completely empty project until the final polished game. We're going to start from the absolute basics of DOTS, learning how to convert a game object into an entity with the baking system, then how to make a simple component and a system to run it, learning how to use burst and the job system for massive performance, how to use DOTS physics, and a bunch more. So little by little, we're going to learn more and more about DOTS in a nice smooth learning curve, while also building our really nice RTS mechanics. So yep, this is everything that we're going to learn in this course. In total, 17 hours split across 75 lectures. Again, remember to take your time. It really does not matter how long it takes you to go through this course. All that matters is that you're learning. So take it slow and just make sure you're understanding everything. Alright, so with all that said, let's get started. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to start with the absolute basics, learning exactly what is DOTS and what does it do. Okay, so before we begin building the game and writing some code, let's first cover the absolute basics of DOTS, just so we're all on the same page. Now, DOTS, or Unity DOTS, that stands for the Data-Oriented Technology Stack. This is a set of technologies that Unity built, which are based on some very specific rules, like being data-oriented, and by following those rules, it can provide you an insane amount of performance. This was a very ambitious toolset. They started working on it back in 2017, and only very recently became production ready. The benefits it can provide are definitely immense, but they do require a different way of thinking. So my goal over here in this course is to teach you that different way of thinking so you can properly use this insanely powerful tool. Like the name implies, this is a technology stack, meaning it's not just one thing. It is actually composed of 3 separate technologies. The 3 main ones are the entity component system, the job system, and the burst compiler. And out of those, the entity component system by itself is composed of 3 things. You have entities, you have components, and you have systems. Now, entities are basically just an identifier. Entities by themselves have no data, no logic, nothing at all. They're really just a number and nothing else. Then on those entities, you can attach components. And components, this is what actually stores the data, like for example, some kind of movement speed. And finally, you have systems. And systems, this is what runs logic on entities that have certain components. Like for example, if you have some kind of unit mover system, which looks for entities that have both a local transform and a move speed component, the system will cycle through all entities that match those components, that have the same components that match the entity query, and then it uses the data from those components, like the speed inside move speed and the position inside transform. It uses those to do some kind of transformation on that data. So for example, in this case, maybe it grabs some kind of float movement speed from this component and uses it to modify the position on the local transform component. So this is the core of ECS. You've got entities which are just identifiers, components which actually holds data, and then systems which run logic on that data. Another very important part of ECS is actually memory management. Although you don't need to do this yourself, it's all handled in the background, but it explains why it's so fast. So the reason why ECS is so insanely fast is because in the background, Unity is making sure that all the memory is all tightly packed. All of the components, like this is one component type, this is another one, this is another one, instead of being split all over across memory, instead of that, it is all nicely, tightly packed. All that data is right next to each other, which makes it insanely fast for the CPU to access. Compared to, for example, game objects, since it follows an object-oriented design, you have tons of pointers to different positions in memory, so everything is very scattered, which makes for very slow CPU access. You have, for example, a game object over here, which accesses a position memory for some kind of move speed, and it's over here, so the CPU has to jump here, then has to run some kind of functions that is on a different component, so it jumps over here. Then it accesses some kind of other game object reference, so it jumps over here, and here, and so on. So this process of jumping all over the place in memory, this one is quite time consuming, it is quite inefficient. Whereas over here with ECS, all of the components have their memory packed tightly together. So when a system goes to do some logic on some components, the system's literally just jumping from component to component. So just one to the other one, that is so much faster than jumping randomly around in memory. Also note the specific separation between the components that just hold data and the systems which just run logic on that data. ECS is all about a data-oriented design as opposed to object-oriented programming that you're probably familiar with. In object-oriented programming, you define some kind of object and that object has both data and logic. This is what leads to lots of pointers pointing to different positions in memory. Whereas in ECS, with a data-oriented design, with this you have a separation between those two, which again leads to faster, more tightly packed memory. So entities are just identifiers, components just hold data, and systems just run logic on some data. That's it. This also means that your code can actually be more modular. For example, if you have this kind of system, let's say this is a unit mover system, this system will move any entity that has a local transform and a move speed component. Importantly, it does not matter what that entity represents. It doesn't matter if this represents a single unit, or a tank, or a building, or a bullet. If the entity has these two components, if so, then the system is going to run the same logic on it. The system does not care what exactly the entity represents, it just runs the exact same logic on all entities that have all of the components that match the query. We're going to see this in the course, how, for example, we're going to create a find target system. That system will work for both the player finding targets of the zombies, and work for the zombies finding targets of the player. So that makes the entity component system. The second main part of DOTS is the job system. This one is all about writing insanely fast multi-threaded code, meaning run code on multiple threads, multiple cores all at once. As you might know, CPUs nowadays have lots of cores. However, a lot of game code usually only runs on one core, just one thread. So all the other cores, they're just wasting time doing absolutely nothing. Based on that, as you can imagine, you can gain an insane amount of performance, essentially for free, by just using those other cores. Now, the reason why a lot of game code uses only one core is because writing multi-threaded code is usually extremely difficult. You can easily get a ton of errors that are extremely difficult to debug. The job system helps solve that by adding a ton of safety nets and a bunch of limitations, which in itself makes it much easier to write multi-threaded code. You simply define some jobs and queue them up, then Unity handles all of the complex logic of dependencies and figuring out which thread should work on what job. So job system helps you take advantage of the CPU and all its cores as much as possible. You can take the exact same code and literally run it in double or sometimes 100 times faster, because instead of running it all sequentially on just one thread, you're going to split it across multiple threads. And the third main part of DOTS is the burst compiler. Now this one is almost a piece of magic. It is a special compiler that Unity built which is all about performance. Just by enabling it, you can literally get 100x performance improvements in some scenarios. It is truly an insane piece of tech. However, in order to get those massive speedups, it has a bunch of limitations. The main one has to do with how your code needs to be data-oriented as opposed to object-oriented. It needs that in order to receive those benefits. These limitations are something we're going to learn about in detail in future lectures, specifically the difference between value types and reference types. So you can't just make every code burst compatible by default, but if you keep in mind those limitations, then the results you can get by just adding a simple attribute to your code is really quite insane. When you combine burst with the job system, your code will not only run super fast, but run super fast on all cores all at once. Then when combined with the entity component system, which again is all about data-oriented design, when you use all three, you get some really insane results. This right here, this is an actual example that we're going to build in a future lecture. You can absolutely have some normal code that takes 9 milliseconds to execute, running that just on a single thread, just on your main thread. Then you can use that code and convert it to use a job, and that same code all of a sudden runs at 0.29 milliseconds, and then you take that same job and you just apply the burst compatible attribute, and with that exact same code is running on 0.035 milliseconds. So you go all the way from 9 milliseconds to 0.35. That is a 260x faster performance improvement. You get all that just by using jobs and the burst compiler. Now this sounds crazy, making the exact same code 260 times faster. That does sound insane, but that is absolutely real. That is how powerful dots can be, and it is why you should definitely learn how to use this tech. Now these are the three main components of dots, but dots also is composed of a bunch more packages. For example, you've got Unity Physics. This is an extremely performant physics system that was built specifically for ECS. Then you've got the collections package. This one includes a bunch of data-oriented collection, meaning things like lists and arrays, but that were made to be data-oriented instead of object-oriented, meaning they work with jobs and burst. Then you've got the mathematics library. This is another package that was built specifically for use with burst, so it handles all kind of math operations, all of them extremely performant. Then entities graphics. This is how you can render entities. It's also super performant and works with both URP and AGRP. And netcode for entities. This is their networking library meant for multiplayer games using dots for some super high, fast-paced multiplayer. All of this together is what is known as dots, or the data-oriented technology stack. And one very crucial thing about dots is how each of these main parts, each of these can work by themselves. You don't have to use them all. For example, you can just use the job system and the burst compiler. You can just use those two without using entities at all. Or you can just use entities without using jobs or burst. Basically, these three tools, these are distinct separate tools by themselves. Although, of course, when combined, that's when you get some truly insane results. And another extremely crucial thing about dots is always remember that dots is just a tool, and it's a tool that can be combined alongside game objects. So you can and you should mix and match both game objects and dots. You don't have to go full 100% one or the other. You can use the right tool to solve the right problem. For example, in this course, we are going to be making an RTS game. RTS games are all about tons of units and lots of complex logic. So in this case, for this game, we are indeed going to be making this game, let's say about 80% using dots and about 20% using game objects. We're mostly going to be using game objects for the UI and some general manager scripts. However, you could absolutely do the opposite. If you were making some kind of action-adventure game, you could definitely use game objects for about 80% of your gameplay and use dots just for the 20% that is really performance heavy. One of the main benefits of dots is indeed performance. So you can build your games using mostly game objects. Do it just like you're used to building any games. And then when you use the profiler and find some hotspots in your game, you can use dots just to solve those particular hotspots. And again, when it comes to dots, you can either use entities plus job system plus burst, or you can perhaps solve those hotspots by just using the job system and burst without using entities. So you can get a ton of benefits by just refactoring some piece of code without having to completely re-architecture your entire game. So always keep this in mind, they can work together, dots and game objects. Dots is really powerful because of that. It does not require you to give up all your knowledge of game objects. Dots is just another tool in your toolbox. It is not a replacement for game objects. It is a tool that is extremely good at what it does, and as with any tool, it is up to you as a developer to figure out when and where to use that tool. Now in terms of learning all about dots, here in this course I won't teach you everything needed to build this game. I will introduce concepts like entities, systems, and jobs. I will introduce those as we need them to build the game. This is a very practical step-by-step course, so instead of learning everything all at once, learning just the theory on all the concepts, instead of that we are going to learn them as we use them. But if you want to get an overview of the entire tool stack, there's two excellent sources that I recommend. The first one is Unity's official ebook. This is an excellent free ebook that has 50 pages. It is really detailed, it talks a lot about dots. Specifically, this is a high-level overview on the theory behind dots, how it works, all of the various components, why it's important, how exactly it makes the code faster, and so on. So this is very much a high-level overview as opposed to a technical guide with very specific implementation details. And for a mix of both high-level and technical, you can go watch my tutorial on dots. In there, I focus on teaching how to start using all the technical parts that make up dots. So that video is a great, very condensed way of learning the entirety of dots. Like I said, in this course, I will teach you everything, all of the components of dots, step by step as we need them, so you don't necessarily have to go through these two resources. Personally, if I was you, I would go through both those, just because, personally, I like first learning a high-level overview and then learning the more practical aspects, but either way works. You can either make a quick pause to go through these resources or just continue following the course. Either way works, up to you. Okay, so now that we know exactly what is dots and what does it do, now it's time to start actually using it. So let's begin creating our project and installing packages in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to begin setting up our project and installing all the packages. Okay, so let's begin setting up everything. Now, if you want to follow the course as you go along, normally you are supposed to follow along exactly as I do things. However, for these first few lectures, where we are setting up everything, it is actually simpler if you just watch these lectures and then later on download the project files. That way there are no issues with mismatched versions or anything like that. So just watch all the lectures in this section and then download the project files. That one contains the entire project. Then you just unzip that file, edit on Unity Hub, open it, and you'll have everything exactly the same as I have. Like I said, this avoids any issues with version mismatches, either Unity version or individual package versions. So if you want to follow along, definitely wait a bit and then download that. But over here in this video and in these following lectures, I will show you the whole setup that I did in order to create that project. So first of all, here I am in Unity Hub. I'm going to go ahead and create a brand new project. For the editor version, I'm going to choose Unity 6. Then for the template, dots can actually work with either URP or AGRP. Let's go with URP because it runs on everything. Then for the project name, let's give it some name like dots RTS course. Then select the location, the organization. In this case, we don't need to connect Unity Cloud, and that's really it. Okay, so let's create. Alright, so here is our empty Unity project. Now let's go ahead and first of all get rid of the URP README files since we don't really need those. So let's go ahead and just remove. Okay, now let's go ahead and install all the packages that we're going to need. So let's go up into Window, open up the package manager. Then here, let's go inside the Unity registry and let's see. So the first one is we want to install the entities package. So let's scroll down. Yep, there it is, the entities package. This is the main dots package that contains ECS, the entity component system. And over here, we can also look at the dependencies. So we can see this will already install a bunch of these ones. It will automatically install burst. That's the burst compiler. It will also automatically install collections. This one contains a bunch of native collections like native arrays, native lists, and so on. And it will also install the mathematics library. This is the one that is burst capable, which is super fast. Okay, so let's go ahead and install the entities package. Okay, all of those are installed. Next, since we're going to render our entities, we also need to install over here the entities graphics. If we don't have this package, then we can't actually render entities. We can't see those visuals. So if we want to do that, which we do, then let's go ahead and install this one. Okay, that one's done as well. And since in our game we're going to be using dots physics, let's scroll down and find over here the Unity physics. This is Unity's physics system that is built on top of ECS. So let's also go ahead and install this one. Okay, that's it. And finally, let's just go all the way up here. And let's also install the 2D sprite package. This basically helps us being able to edit a bunch of sprites as we import them so we can then use them in the UI and so on. So let's go ahead and just install this. Okay, that's it. So here, if we look in the project, here in the project, all of these packages are installed. So it's really the default ones plus the ones that we just installed. Again, like I said, part of the reason why I told you to wait and then download the exact project files is so you get exactly the same package versions. That way there's no confusion about any differences. If you download the project, you will have exactly this setup. Okay, so that's it. All our packages are installed. Let's close them. Now let's actually follow the setup that Unity recommends. In terms of IDE, I'm going to be using Visual Studio Community. That's the free version. I'm going to talk about that setup in a future lecture. Now technically you can use whatever IDE you want, but it has to support source generation. If you look over here inside the documentation for the entities package, over here we do see a section for IDE support, and over here it says how this uses the Roslyn source generators. So because of this, it needs to be using an IDE that is compatible with source generator. So in my case, like I said, I'm going to be using Visual Studio, the community version, but if you want, you can also use Rider and that should work as well. Now interestingly, there's no mention over here of Visual Studio Code, so I don't know if that one is specifically not supported. Maybe it is, maybe this one refers to both the Visual Studio proper and Visual Studio Code, but I'm not sure. Like I said, I'm going to be using Visual Studio Community. So the next important setting is what it says here on domain reload setting. For that, here in Unity, let's go into Edit. Then let's scroll down into Project Settings. Then on the left side here, let's go into the Editor tab. And now we can scroll down until we find it. Here it is, the Enter Play Mode settings. And over here, when entering play mode, by default, it is on this one, reload domain and scene. And what the docs recommend is do not reload domain or scene. So that's it. Now, like it says here, this actually has one very important implication. Basically, by disabling domain reloading, any static field or any static events, any static data you have will not be reset between runs. Meaning if you have some kind of static field for an int for some kind of player score, and the player's playing the game and they got a score of 50, then you stop playing and you start playing again. If you do that, when you start playing, it will remain with that 50. Whereas if you have domain reload enabled, it would automatically reset that, and when you replay, it would once again reset to 0. So basically, if you're used to using lots of statics and assuming they reset every time you stop playing, that will no longer happen with domain reload disabled. So always keep that in mind. Okay, so with that, our super basic setup is done. Our project is pretty much ready to use dots. Now let's go on to the next lecture and set up our Unity layout. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to set up our Unity layout. Okay, so here we are in our project. Let's just customize our layout. It's very important that you set up your layout in a proper way, so that you have easy access to all the things you need and you know where exactly everything is. Now, you can set up the editor in any way you want, but it will probably be easier to follow this course if you're using the exact same layout as me. And like I said, since this course is meant for intermediate or advanced users, I am assuming that you know the absolute basics. So I'm assuming you already know what exactly is the inspector window, what is the project window, the hierarchy window, and so on. I'm assuming you know what is a game object, what is a component, transform, and so on. So I'm assuming you already know all of those absolute basics. Now, in terms of layout, I've been using Unity for over 10 years now. I started making my first Unity game in 2012, so let's see the Unity layout that I've developed over the years. First is the inspector over here on the right side. This way we always have a nice view of the selected object and whatever scripts it has. Then for the hierarchy, I like to grab it and place it down here on the left side. We're going to make sure that our scene is always nice and organized, so we don't really need the hierarchy to take up tons of space. Then with the project files over here right next to it. With the console also over here on the next tab. Usually I find that when making the game, I want to look at the project window, but then when playing, I mostly just look at the console. So keeping them in the exact same place but on different tabs, that makes perfect sense to me. Then over here in center, we have the scene view, and with the game tab, either over here on the exact same next tab, or over onto the side. So depending on whether I want to see both of them at once, I swap it out one or the other. Okay, so the basics, this is the rough layout that I normally use. Now for a couple more options. So over here on the project files, on the top right corner over here, you see these little 3 dots. Over here, I like to set it as one column layout. Basically, this showcases all of the project files, all of it in this nice compact list tree view. Now, if you need to browse lots of visuals in your project files, then you can swap back into the other one. But for most of the time, this compact view works great. Also, since we're here, just in case you don't know, there's this nice little button over here with an eye. This basically shows the visibility of the packages. So over here, we can see we have all of these packages installed. And if we click on that, basically that folder shows up as empty. Packages still exist, they're really just hidden. So just a small thing in case you want to browse the packages, untick this. But in most cases, probably leave it ticked, leave everything nice and collapsed. Okay, that's for the project window. Then over here for the console. For this one, let's also go into the 3 dots for some more options. The main one I like changing here is over here the log entry, set it as just one line. Basically, this makes the console nice and compact, which personally I prefer. You can see a bunch more logs without taking up quite a lot of space. Then of course, if you want to read the whole log, you can just click on it and view the whole stack trace. Then if you want, you got some more options, so show the timestamp or not, using monospace font or not. You can choose whatever you want. I'm going to go with these settings. Also extremely important is over here these 3 buttons. This is for the tab messages that appear in the console. So the left one over here, this is info messages. Basically the regular messages, we're going to use this quite a lot. Next we've got the warnings, and then we have errors. Basically if you untoggle any of these, then the messages over here will not show up in the console. This is something that a lot of people find quite tricky. So if you ever come across an issue where for some reason nothing is showing up in the console, definitely make sure you check these buttons. Always make sure they are all ticked so you can see exactly every single message. Then over here on the left side for the clear, I like to clear on play just so everything resets. Then for collapse, this one basically collapses messages that are exactly the same into one entry and then just shows a number. Now personally, I don't like this. I want to see every single message as it comes, even if it is duplicated. I've also seen this lead to a lot of confusion for some people. They think their code is just firing one message when it's actually firing hundreds. So to avoid any confusion, leave this untoggled. Then for pause, yep, we do want this ticked. We want the game to automatically pause if some error occurs. If you untoggle this, you might get an error, but the game might keep playing, which might in turn lead to a bunch more errors. So always leave this toggled. And that's really it over here for the console. Then let's go over here onto the game view on the center. First over here on this tab for the free aspect, let's swap from free aspect into full HD. This is the standard aspect ratio. Technically this will really only matter when we start working on the UI and positioning elements, but either way I like to put it on 16:9, just as always. And then for another very important option over here, let's enable VSync. Basically this will limit the frame rate depending on your monitor's refresh rate. This is really good to make sure that your graphics card doesn't go crazy trying to render a completely empty scene at like 1000 frames per second. This way it won't be limited. In my case, it will limit it to 144 FPS. And also, if your game view is looking pixelated, then make sure you check out this slider. If you move it like this, then this looks really pixelated, so always make sure this one is all the way over to the left. Okay, that's the game view, and next to it we have the scene view. Now for this, pretty much on default should be good. Now over here, these two are extremely important. Definitely make sure you know exactly what these two mean. These basically place the handles that you see, like for example the move handle. If I select something, there you go, that move handle. If it is like this, it is placed on pivot, but if it is on center, then it's placed on the center of the object. Usually this is very confusing, so if you ever see your handles in weird places, make sure this one is on pivot. That is probably what you want to do. Then for this one, either a local or global rotation. Sometimes global can be useful if you want to rotate or move something while ignoring the rotation of that particular object, but in most cases probably leave it on local. Then over here, let's show the grid on the y-axis. There's no need for snapping. And over here, all of these also look good, so let's leave it on shaded draw mode. With 2D disabled, sound doesn't really matter for now. Let's leave all of the various effects enabled by default, just without the always refresh. Let's hide hidden objects. Then for the layers, show all of them. For the camera, everything on defaults. And for the gizmos, again, everything on defaults. Okay, so here is the layout that I'm going to be using throughout this course. Like I said, it will be easier to follow the course if you're using the exact same layout as me, so ideally you should be using this. But again, all the windows are customizable, you can place them anywhere you want. So if there is something you absolutely prefer on a different place, then go ahead. You can drag the windows and place them anywhere you want. And once you have a layout that you're happy with, go ahead on the top right corner and you can go ahead and save the layout. So in this, I'm going to save it as the .rts course. And if you ever get lost, you can go ahead, you can reload default layout or go back into that one and everything reloads. Okay, great. So our layout is all perfectly set up. Now the next important thing is setting up Visual Studio. So let's continue that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to set up our Visual Studio. Alright, so with the Unity layout all set up, let's make sure Visual Studio is also set up correctly. Now over here, I'm using Visual Studio Community 22. This is the free version. You can download it directly from their website. Now you don't have to use the exact same ID that I'm using here. Technically, you can use something else. Like it says here on the manual, you can use whatever ID you want as long as it supports source generation. That's really important since Dots does use quite a lot of source generation. Specifically over here, they mentioned Visual Studio 22 Plus or rather 21 Plus. So you can use whatever you want. In my case, I'm going to be using Visual Studio 22 Community. Now let's see my setup for Visual Studio. Now I've also included a file with my Visual Studio settings along with the project files on this lecture. So just like with the project files, you don't necessarily need to follow everything I'm doing in this lecture step by step. You can just download those settings and import them. Okay, so before we actually get into setting up Visual Studio, first actually over here on Unity, let's go into Window, open up the package manager. And over here, let's just make sure that package is installed. So yep, over here, the Visual Studio editor, make sure this package is installed. And again, in your case, if you're using JetBrains Writer, then I'll go ahead and install this package. Next, inside of Unity, let's go into Edit and Preferences. Then over here on the left side, let's go into External Tools. And here, make sure you select your external script editor. In my case, I'm using Visual Studio 22. Then for these extra options, if you want to play around reading the source code, like for example, the source code for dots and so on, if you want that, then you can go ahead and tick these boxes. But in our case, for this simple game, we don't really need to do that. So let's just leave them like this, and everything is working perfectly. So now if I go up here into Assets and open up the C# project, yep, there you go, it does open up Visual Studio. Okay, great. Now over here for some more settings. Again, like I mentioned, I exported all the settings to a file that you can download. So here in my Visual Studio, I have a nice extension that adds a bit more colors to my code, which makes it easier to read and write. And for that extension, let's go up here into Extension, Manage Extensions. Then again, I'm going to search for something called Viasphora. Yep, there you go, this one. Like it says here, the main thing is that I add some rainbow braces, so a bunch of colors so everything is easier to see. Then highlight some keywords and so on, so it's a really great thing. I believe if you download the settings file, it will also automatically install this one. But if it doesn't, then just go ahead and do this, search for VS4 and install it. Then with that installed, let's go into the settings, so into Tools, and let's go into Options. Over here, let's scroll down until we find VS4, yep, just like this. And here are all the settings. Now I think these are really mostly all the defaults. I don't remember if I changed anything. But again, I'm going to export all the settings. I think the main thing that I changed was really just the rainbow braces. I think I changed some of these colors. Let's just create an empty script just to see these colors in action. So let's just go and let's just right click and create a brand new mono behavior script. Let's just call it testing. And over here, just write a bunch of testing code just to see the colors. Okay, here's some dummy code. And yep, we can see we do have a bunch of colors. So the if is calling like that, the for like that, the ints like that, the comment like that, the function like that. So yep, that's really it. Now, these are really just visuals. It's not a requirement. So you don't absolutely need this extension, but personally I do find it quite useful. I find it helps make the code a little bit more readable. So next for some text formatting rules, let's go again into Tools, into Options, and then up here let's go into the text editor. And again, I believe here everything is pretty much defaults. These are the settings. Again, you can just download them, or if you want to follow along, just pause the video and compare directly with your own. I think the only thing that I changed was in one of these. So these are the C#, the scroll bars, the tabs, the advanced, and the code style. I think the main change that I did was actually over here on new lines. By default, C# usually has new lines on all of these. Personally, I don't like it. Personally, I don't like to place the curly braces, the opening directly on the same line instead of the new line. But again, just a personal preference. If you like it on a new line, then you can definitely go ahead and do that. Okay, so like I said, I've exported all of these settings. You can go ahead and download that file directly under this lecture. Then for importing, go up here into Tools, and then into Import and Export Settings. Then over here, click on Next. Then over here, let's select Import and click on Next. Then if you want, go ahead and make a backup of your current settings. If not, then by importing you will override it. So I definitely recommend you do this, just in case you have your Visual Studio set up in some different way. If you want to then write some code outside of this course, you probably want to get back to your usual settings, so make sure you save these. Then over here on this window, click on Browse. Find the file that you downloaded from this lecture, so the .rtscourse.vs settings, and just go ahead and open that one. Then click on Next and Import. So with that, you should have your Visual Studio set up exactly like mine. And the other thing is VS4, so let's go into Tools, Options. Then down here, scroll down into VS4, then Export Import. Click on Import Settings. And again, same thing, find the file that you downloaded, so the .rtscourse vs4.xml, and just go ahead and import this. Alright, so yep, with that, you should have your Visual Studio set up exactly like mine. Again, this will avoid any confusion with things being slightly different on your end versus in the video. This way, everything should match perfectly. So yep, everything is working. Let's just go back over here inside of Unity and let's get rid of our testing script. We don't need this. Okay, great. So Visual Studio is perfectly set up. Now let's import some visual assets and let's do that in the next lecture. Hello and welcome. I'm your Code Monkey. In this lecture, we're going to import the visual assets that we're going to use in the first part of this course. Okay, so here we have our project set up. Let's import some nice visual assets. Now the assets that we're going to use, those are the ones made by Synthi Studios. They are an excellent team that makes some really gorgeous low poly assets. Personally, I'm a huge fan of their style. I've used in many of my tutorials and in my own game, Dinky Gardens. They have allowed me to use part of their packs in this game and distribute them to you. The license for the assets included in this course is you can use them for non-commercial use only. So if you want to use them in your own commercial projects, you can pick up the entire packs from their store. The assets that I selected are from a bunch of their simple series. It's a very blocky and low poly style, which personally I felt that it looked really great for this game. I think it looks really great for an RTS game. A lot of assets are from this simple military pack. Then for a bunch of the buildings, I picked them up from the simple space pack. And of course, for the zombies, they came from this simple zombies pack. Now, I really like their style, and like I said, if you want to use these assets in your own commercial projects, then go ahead and pick up these packs from the Synthi store. There's links right under this lecture for all the packs. And if you like this style, then you can pick up this simple bundle. This one contains a ton of their assets in this nice style. And also, by the way, the packs that I mentioned, those contain a lot more assets than just the ones we're going to use in this course. Okay, so now let's go ahead and download the asset pack for this lecture. Although again, like I said, in this section, I'm showing you all the setup, everything that I'm doing, but you should really just wait until the end of this section to download the pre-prepared project files. So I download the assets and I get this nice Unity package file. Just double click or drag it onto the project window. And yep, here it is with the asset list. These are the assets that we're going to use in the first part of the course. Later on, we're going to import some more assets. So over here, just make sure you select all of them, select all, and go ahead and import. And yep, here it is. Right away, we have all of our assets in our project, so we can see a bunch of textures. We can see a bunch of meshes and materials and all kinds of things. With this, we can right away set up a basic scene. So first, let's actually clean this up a little bit. So instead of calling it simple scene, let's call it the game scene. Yep. Then let's right click on the hierarchy. Let's create a 3D object. Let's create a plane. Name this our ground. Over here on transform, let's put it on 0, 0, 0. So right on the origin. And for the scale, let's make it quite a bit bigger. Let's put it on 40. So 40 on all of them. Then let's also go ahead and use a ground material. So here inside the materials folder, we have the ground desert. So let's just go ahead and apply this one. Okay, great. Next for the camera, so let's put the game view right side by side. For the camera, we want a top-down view. So let's select the camera object and let's position it on 0, 29, and -25. And for the rotation, let's put just 45 degrees over here on the X. Okay, so we have kind of like an overhead view. Then for the field of view, let's go ahead and put it on 40, just like this. Now let's drag some visuals just for testing. So let's go ahead and just drag these meshes. So there you go, there's a soldier and there's a zombie. Let's make sure to assign the material. So inside the materials folder, there's the characters. So for the soldier, let's assign this material. So let's expand that one and assign that material. Yep, there it is. And for the zombie, let's also assign this material. All right, that should do it. So here we have both of our units and they are visible directly over here on the camera. Okay, great. So we have our starting assets imported. So everything is looking nice. Now let's just handle some more visual things. We want to set up lighting, post-processing, and SSAO. So let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to set up post-processing and lighting to make our scene look really nice. Okay, so here we have some assets and we have our camera set up. Now let's make it look nice. We already have the project set up to use URP, so adding post-processing is actually pretty simple. It's already somewhat enabled by default. Here, this scene that was created automatically already has a global volume, and by default, it already has a volume profile attached. So let's use this as a starting point, but let's also just rename it. So instead of sample scene profile, let's just give it a proper name, so the game scene profile. Okay, so now here, let's set up the effects. Although of course, keep in mind this is really just a visual thing. So if you prefer a different visual, then feel free to use whatever effects you want. Now personally, I don't really enjoy tone mapping. I think it makes it look quite a bit washed out, so personally I don't really like it, so I tend to remove it. Then for bloom, we can go ahead and leave it like this, so with a threshold of 1, intensity of 0.25. Then for motion blur, that is also something I don't like, so let's go ahead and remove. And for vignette, I think this one always looks good. Let's make it just a little bit more intense, so maybe something like 0.4. Okay, great. So that's it for post-processing. Like I said, this is just a visual thing, so if you want a different look, definitely go ahead and use it. Next thing, let's set up the lighting. So let's go for the main light. So on the hierarchy, let's select the directional light. And for this one, in terms of temperature, it looks pretty good. Then over here for the intensity, let's make it a little bit less intense, so 1.5, just like this. Everything else on defaults. Next, let's handle the global lighting. So for that, let's go into Window. Then down here, let's go into Rendering and open up the lighting window. Okay, so here it is. Let's go onto the Environment tab. And on this one, over here for the environment lighting for the source, instead of skybox, let's go with color. And then over here for the ambient color, let's make it sort of a grayish white. So let's put it maybe something like this. So maybe about 220 on all of them. Yep, there you go, just like this. So that's looking pretty good in terms of lighting and visuals. Next, let's add some nice screen space ambient occlusion. So that one is going to be added on the renderer. So let's select the default one. And by default, it actually comes with a mobile renderer and a PC renderer. We're making a PC game, and this is set up for the PC. So let's go ahead and use this render. This is the one that is actually active. And importantly, it's over here on the renderer, not on the render pipeline asset. No, for the screen space ambient occlusion, we want it over here on the renderer. And it's actually already here by default. We already have screen space ambient occlusion. Let's just make it a little bit more intense, since as you can see here, the camera is going to be quite far away. So for the method, I think interleave gradient looks a little bit better. Then for the intensity, let's make it quite a bit more intense, so let's say about 10. Then for the radius, let's also make it bigger, so 0.6. Fall off distance like this, and indirect lighting a bit more like that. So as our camera is quite zoomed out, I think like this looks quite a bit better. We can enable and disable it in order to see the difference. So with it disabled and enabled, and personally I think it looks quite a bit better with it enabled. Okay, that's great. Finally, let's go onto the render pipeline asset. And over here on this one, most things are already correct. Over here, let's make sure we have AGR so that bloom works. If you want, you can go ahead and enable anti-aliasing MSA. Either way, it shouldn't change too much. The important one is down here for the shadows. Again, since the camera is going to be quite far away, we don't want shadows to disappear at just 50 units, that's way too close. So let's put the max distance at something like 150. Okay, so I think this visual looks pretty good. Again, like I said, most of these visual effects are very much personal preference. They don't affect how the code runs in any way. Also, by the way, the post-processing effects, like we saw, those are actually saved onto a file. So if we select the global volume, yep, here is the game scene profile. So if you want, you can just duplicate this file. Then you can have two files with completely different effect settings. You can have one that looks exactly like I have here, and another one that has whatever effects you want. Okay, that's really it. Our post-processing effects and everything is all nice and set up. So with that, let's go on to the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, the goal is very simple. Let's just download the project files and start the project from there. This way you have the exact same setup as me, with the exact same version numbers, everything with the exact same settings, everything is exactly the same. This is going to help avoid quite a lot of confusion, and confusion that I usually see in comments in my courses or tutorials. People installing different versions of packages, different versions of Unity, using the built-in renderer instead of URP and so on. So by downloading the exact same project files, it will avoid any of those issues. So just go ahead and download the exact same project files that I have here. On the page for this lecture, just scroll down and download the file. It is going to be a zip file. You can download it and then unpack it somewhere. Again, this contains the entire project. So after you unpack it, go ahead over here onto Unity Hub, click on the little arrow and add project from disk, then find the folder and just add it. And yep, here it is. Now, if you don't have this specific Unity version, then you'll see a button over here to download it. Again, use the exact same version as me, just to avoid any confusion. After you go through this entire course, after you learn all of this, afterwards for your own projects, you can then use whatever Unity version you want. All the knowledge that you'll learn here will apply to pretty much any Unity version. So download that, add the project, and just open it. Now, by the way, the first time that you open the project, it can take a while. Basically, it's going to download all of the packages onto your local machine. And after you download everything, then you should have this exact same scene here. And by the way, for the Visual Studio settings, I also added those as downloadable directly on this lecture. So if you haven't done that yet, then go ahead and do it. Download these two files and then import them just like I covered in the Visual Studio lecture. Okay, great, so you should have this exact same scene open up on your PC. With that, we can now continue. And just before we finish this lecture, let's just clean up this scene. Let's just remove these visual meshes. These were just temporary. So let's get rid of them, save the project, and that's it. Alright, so our project is completely set up. It's time to finally start working with dots. So let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to start learning the basics of dots. learn about subscenes and the various dots windows. We're going to create an empty game object and learn about the baking workflow that converts game objects into dots entities. Okay, so here we have our empty project with all of the packages installed, everything ready to work with dots. Now, the first thing we do is create what is called a subscene. So over here on the hierarchy, let's right click and let's go up here, create a brand new empty subscene. Let's call it something like entities subscene. And yep, there it is. So basically this is how you can mix game objects and entities. Objects outside of this subscene, like all of these game objects over here, all of these are regular game objects. They will not be converted into entities. They have nothing to do with dots or ECS or anything like that. Whereas objects that we place inside of this subscene, those will automatically be converted into entities. So let's actually see that in action. Let's right click directly on top of the subscene so that whatever we create ends up inside of it. And over here, let's create a brand new game object and let's just make it a simple 3D cube. And if there it is, we have a cube directly inside of the subscene. And over here, we do see it. Over here on the scene view, we do see our game object cube. In the game view, the camera is indeed rendering that cube. And over here on the inspector, we do see the regular components. So we have a mesh filter with mesh assigned to it. We have the mesh renderer, the box collider, and so on. All of these are normal game object components. And of course, if we hit on play, yep, everything still runs. Everything is still the same. There's our cube, again, just like a game object. We created using the exact same method and everything looks exactly the same. However, if we select the cube and over here and look on the inspector, if we go down here, we see this little thing said the entity baking preview. Baking is essentially a dots term. It is the process by which game objects and their game object components are converted into entities and their entity components. So it's kind of like making a cake. You take some raw dough, you bake it, and you end up with a cake. So dots is kind of like that. Here we have the normal game object with normal game object components. Those components are then baked, and during the baking process, we then end up with an entity that has all of these dots components. So down here, we are just seeing all of the types of the components that we're going to see, and by clicking, we can actually see some more data in those components. And we can also see all of this data all at once. So on the inspector, on the top right corner, we have this little circle here. Here we can basically modify the mode of our inspector. So authoring, this is what we're seeing right now. So it shows us all of the authoring game object components, so all of the normal ones that you're used to seeing. But then if we click on it and we swap it into runtime mode, yep, now here we can see all of the entity components and all of their data. For example, you can see how instead of having a regular transform component, instead of that we have a local transform. This is a dots component. Also, by the way, if you don't see it, that is probably because you went over here on the authoring and you removed this box slider. If you do that, and now we go back into runtime, yep, now it does not have the local transform component. Basically, dots is pretty smart. This baking process is pretty intelligent. It will only bake components as they are needed. And basically without any physics, just an empty game object. This one does not need the local transform component, so it does not get it added. Whereas if we leave that on, so let's go up here into authoring, and let's add the box slider back in. If we go back there, yep, now we do see the local transform component. And again, during the baking process, all of the data is automatically converted. So if we go back into authoring, and let's put this on position 5, 3, and 2. And now if we go inside the runtime component, yep, there you go. Now it does have the exact same position. Again, the process of baking, the goal of it is to take the game object components and all of their data and convert them into their equivalent dots components. Also note how the components do not match one by one. So for example, over here on the authoring component, on the normal game object components, we've got transform, mesh filter, mesh render, and box collider. So we have 4 game object components. Whereas if we go inside runtime to see dots components, we can see we have quite a lot more of those. This is actually a very important concept in dots. It's how your authoring data can be different from your runtime data. Later on, when we create our own custom authoring components, we will be able to have, for example, one game object component turned into multiple dots components. This can be really useful to simplify some things on the authoring side, doing that so that it's really easy to build things, but then convert it into some specific components to make it super fast on the runtime side. So this is the baking process. This is a really important part to know about dots. It's how game object components are directly converted into dots components. This system is what makes dots actually surprisingly easy to use. For the most part, you can actually keep using regular game object components, and then everything gets converted into dots components. So on that note, talking about that conversion, let's learn a little bit about what baking is actually doing. Basically, as it takes all of this game object data, as it converts that data into dots data, as it does that, that process is essentially taking all of the game object data and converting it into binary dots data. So if we look on the hierarchy here, if we look inside the subscene, we can see how it has this little checkbox here. And actually, if we click to select the subscene, if we look in the inspector, we can see how this subscene is actually just a special game object with a special subscene component. So even though in the hierarchy it looks like something really special, in reality it's really just a game object. But anyway, so here we have this little checkbox, and this one is basically for opening or closing the subscene. So right now it is open, meaning we can inspect all of the objects inside the subscene. We can go here, we can move it, we can modify any of this data, and then we can close it. Or before we do, let's just hit on save. We have the little asterisk saying we have unsaved changes, so Control S just to save it. And now if we click on this, yep, there you go, the subscene is now closed, and now we can no longer inspect the objects that are inside of this subscene. The object still exists, we can still see it over here on scene view and on game view, so the object still exists inside of the subscene, but it is now no longer open for editing. So what happened here is that object with those game object components, all of that was baked directly into binary data, and that is the exact same thing that is being loaded directly in here. This is exactly why one of the huge benefits of dots is actually world streaming, meaning how you can have, for example, a huge open world and you can have it split into various parts, and then you can dynamically load and unload each of those parts. That's usually how open world games are usually made. And the way that dots has a huge benefit in that aspect is because dots works with binary data, and binary data is insanely fast to load. So the baking process here, converting this game object cube into actual dots binary data, that process essentially means that the game does some really heavy processing right now during edit time, but then it is insanely fast to load and unload during runtime. So like I said, this is really excellent for creating huge open worlds. You can split a giant world into multiple subscenes and then very easily dynamically load and unload those scenes as the player moves throughout that world. So right now with the subscene closed, right now we cannot edit our objects with its authoring data. So here in the hierarchy it does not even show up. However, dots also has some entity-specific windows. So let's go here up top into the window menu. Let's go down here into entities, and we can open up the entities hierarchy window. So here it is. This one is very much like the normal hierarchy, except instead of showing game objects, it shows entities. It also has multiple modes like the inspector, and it has a toggle to see various worlds at the same time. Now sometimes this window gets a little bit bugged, sometimes it doesn't update. If that's the case, you can just reselect the world and everything should update. But anyways, the main point is that if we look in the game object hierarchy, with the subscene being unloaded, being closed, this way we cannot inspect the object. However, inside of the entities hierarchy, over here, even though the subscene is closed, we can indeed inspect the entities that are inside of that subscene. Now we still cannot modify it because, again, it was baked into binary data. But if we hit on play, if we start playing the game, again, here's the bug. Here, let's switch it into runtime mode. And again, here's the bug, it's not updating, so let's select the default world. And yep, there you go, now it does update. And now we can select, for example, this subscene. And again, another strange bug, so on the inspector, let's go back into authoring mode and go into runtime mode. And in the inspector, let's just go into runtime mode. And yep, here we do see the dots components. So the entity is alive, and since the game is running, now we can indeed modify this data, and yep, everything moves correctly. Whereas on the main hierarchy, over here, we still see just the normal game objects. Whereas if we stop playing, and now let's open up this subscene for editing, and yep, we can now see the cube, and we can now start playing. And yep, now we do see the cube still selected in there. And while the subscene is open, we can actually modify it. So if we go in the inspector, we swap it back into authoring mode, and we modify this one. And yep, modifying this over here on the game object inspector, modifying this one does automatically trigger a sort of bake and actually modifies the entity that is currently running. Now, when making the final build of your game, you want everything to be running as fast as possible. So in that case, you want to close the subscenes, or if you're working with tons of them, you probably only want to open one of them. But while building our game, we're mostly going to leave it open just so we can easily edit things. And this entities hierarchy window, this is also very useful at some points. So let's leave it open. Let's just put it right next to the hierarchy, just like this. So we can access both of them easily. Also note one thing, how when we hit on play, over here on the entities hierarchy, we can see all of these entities were created. Some of these are default entities that Unity creates automatically to set up the entire game world. So some of these are going to be related to rendering, others for various systems and so on. Every system also has a corresponding entity. But don't worry about that for now, we're going to learn about systems in a little bit. Now let's see also one very interesting thing. So if we go inside the hierarchy, so the normal game object hierarchy, and let's right click on the subscene, let's create an object inside the subscene. In this case, let's create a completely empty game object. So if there it is, a game object, it's completely empty. The only thing it has is just the default transform component, just because this one we cannot remove. So this is a completely empty game object. So we can see it over here inside of our subscene. But if we go inside the entities hierarchy, and nope, it is not in there. Even if we refresh this, nope, it does not show up. And same thing if we select this game object, and on the inspector, if we swap from authoring mode where it does show, if we go into runtime mode, nope, it does not show. It says this is an invalid entity. This is another very important thing. Basically, the baking process will indeed convert all of the game objects inside the subscene into a dots entity. It will do that, but only if there's anything to actually convert. Now in this case, this game object is completely empty, and when something is completely empty, the baking system is smart enough to not waste any time converting that object. So just be aware, if you make something completely empty, and it is not a child or a parent of any other object, if it has no components, nothing, if so, then something completely empty will not automatically be converted into an entity until you finally add some components, which does trigger the baking process. As long as you have any kind of bakeable component, this game object will indeed be converted into an entity. And by default, like we saw, dots already works with a bunch of the built-in components. So if you set up your game objects with some of these basic components, if so, they will automatically be converted into dots components, like we saw over here with the rendering. The rendering did convert automatically. We can look here in the runtime components. We can see it has a chunk world render bounds. We can see it has the material mesh info and a bunch more rendering components. Same thing for the physics. We can see it has a physics world index, a collider, and so on. Let's see how dots physics already works by default. So let's first of all get rid of both these. Let's right click, create a new game object, and this time let's make it a sphere. Let's lift it up by a little bit, and over there let's go into the authoring component, and let's make it a little bit bigger. Okay, there you go, we have our sphere right there. Down here on the baking preview, we can already see all of the various physics components that will be baked. So we've got the physics collider and so on. Now let's add a rigid body. Again, a normal rigid body component. So a perfectly standard game object component. Let's add the rigid body. And now let's make another object. So inside the subscene, let's create a new 3D object. This time let's make it a plane. Let's lift it up by a little bit. And let's make it slightly tilted just so the sphere falls down a little bit. Okay, that's really it. So we created both a sphere and a plane. And importantly, we created both those using normal game object components, the normal game object process. So far, we didn't do anything that was specific to dots. And just with this, if now we hit on play, and if right away we can see it does work. We can see that the sphere fell down and is now rolling along exactly according to physics. All right, awesome. So just like this, our dots entities already have physics and everything working. So this is really how awesome the baking system is. We just work with normal game object components like we're used to, and then they are automatically converted into entities with dots components, and everything works with dots physics. Also right now, you might have noticed something interesting. So if we hit on play, we can see here in the game view, the sphere did fall down and is now rolling down. But over here on the scene view, if we look, we can see on the scene view, the sphere is actually still up here. And if I try to move this object, you can see the actual dots entity, that one kind of teleports up there. This is a little bit strange, but it's actually very much intentional. Like I said, the baking process happens just once. You edit things, and then game objects get baked into binary data for all the entities. And over here on scene view, basically we are seeing the edit time pre-bake world. And this is actually a setting that we can change. So let's stop playing, let's go into edit, go into preferences. Then over here on the left side, let's go into entities. And here we have the setting for the scene view mode. Here we can change, do we want to see on the scene view, do we want to see the authoring data or the runtime data? Now, for the most part, I find it a little bit confusing to see authoring data. I think runtime data makes more sense in most cases. So I usually set it on this one, let's click. And now if we hit on play, and if now we do see both in scene view and game view, everything looks exactly the same. Alright, so here we learn how dots baking works. This is a really crucial part of dots. It's how we can keep working with game objects for building our game, but then automatically convert them into super fast entities for our runtime. So now that we know how baking works, it's time to create our custom component. So let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to set up our unit and learn how to create a custom dots component along with its authoring component. Okay, so in the previous lecture, we already learned how the baking process works. So here we have a sphere and a plane. We set it up using normal game object components, which are then converted into dots components. So if I hit on play, then yep, all of these regular game object components converted into dots components, and using dots physics, everything falls down. Great. Now that we've tested that, let's get rid of these two objects, and let's set up our normal unit object. And for this, I'm going to build the unit like I normally do, meaning normally I like to have a parent game object with all of the logic components, and then child game objects for other individual things. Like for example, the visual mesh, the visual selected, any kind of thing like that, those will be child objects. But the parent one will be an empty game object with just logic. So let's go ahead, right click, again, directly on the subscenes. We're trying to make a game object that will eventually be converted into an entity. Let's construct a brand new empty game object. Let's name this just a unit. And if this is going to be the parent game object, this is where we're going to place all of the logic components. And now inside it, let's make another empty game object. So inside, let's create another empty one. Call this one the mesh. Let's make sure that it's on 000, scale of 111. Okay, great. Now let's add the usual visuals. So the mesh filter and the mesh render component. And for the mesh, let's select over here the soldier aim mesh. So yep, there it is, the soldier aim mesh. And for the material, let's make sure to assign the one over here inside materials, characters, the soldier material, like this. And yep, there it is, there's our nice mesh visual. So we have our soldier unit. Now, I like the structure of having an empty game object and then children for individual parts. Personally, I find that it really helps me stay organized and becomes quite a bit more versatile as we want to add more things onto the unit. Like one common example is sometimes you have visual meshes that are not exactly the same size that you want, and if you take this approach then you can easily scale, you can modify, put it on some kind of offset, you can apply that on the child object, and leave the parent object on the exact same position with scale of 1, 1, 1. So that's one of the many benefits of this method. Let's go ahead and reset this to everything on 0 and 1, 1, 1. And like I said, later on we're going to create more objects, more child objects. Those are going to be for the select visual, the fog of war shape, the minimap icon, and so on. All of those are going to be child objects. So this is how I like to set up my objects. One parent game object with all the logic, then visuals and other parts in child objects. But just to be clear, this is not a requirement. Like we saw, we can create just a regular sphere and use everything directly on just one game object. So I just want to clarify what is a personal preference versus what is a requirement. So anyways, here we have our game object set up, and it's already correctly being converted into an entity. If we hit on play, and we see on the entities hierarchy, yep, here we have the mesh entity. Again, the parent is not being converted because right now it is actually empty. Like I mentioned in the previous lecture, a game object will only be converted onto an entity if it needs to, meaning needs to have some kind of component that will be baked in order for the entity to actually bake. So now is a great time to see how do we create our own custom dots components. Now this is actually going to be pretty simple. So over here on the project files, first of all, let's create a nice folder to organize all of our scripts. So right click on the assets, let's create a new folder called scripts. And now inside, let's right click on the scripts folder, go under create. And now here we've got tons of menus. So let's go over here inside the entity submenu. In this case, we want to create a component. So let's choose an I component data script. Let's name it move speed like this. Yep, that's it. Let's open it. And here it is. Here we have a component. It is super simple, as you can see. This is all it takes to define a component. You just need to implement iComponentData. This is an interface, but this has no methods you need to implement. It basically just works kind of like a tag to identify this type as being a component. By the way, this interface itself, as you can see, exists inside the unity.entities namespace. So make sure you add the using statement up top. And the other very crucial part is this has to be a struct. This is extremely important, and it's why dots is as fast as it is. Remember what we learned in the what is dots lecture? How the insane performance benefits we get from dots comes from being basically very clever about memory usage. Now, normally in C# code, you work with a lot with classes. For example, monobehaviors, those are classes. And the main difference between class and structs is how classes are reference types, whereas structs are value types. Or another way that Unity likes to refer to those two types is as either managed or unmanaged, meaning their memory is going to be either managed or unmanaged by the C# runtime. So classes are managed components or reference types, whereas structs are unmanaged components or value types. Other examples of value types are the basic types like int, float, bool, and so on. And reference types are classes and pretty much any kind of object. So for example, arrays are also reference types and strings are also reference types. Now the difference is, for example, when we define a class and then we construct an object of that class, when we do that, like I said, classes are reference types, meaning this variable over here, this one is not storing the class object directly. It is not storing the actual class data. Instead, this variable really just has a pointer, and then that pointer points to a certain position in memory. And this memory itself, this memory position, this is what actually contains the class data. Whereas if we define something as a struct, we construct a brand new struct, and by doing that, that struct, that variable is actually holding the actual struct data. Meaning there are no pointers, there are no references to anything. The struct data is stored directly here. The power of dots is really all about how it handles memory, how it packs memory in some super tight chunks, and doing so then allows the code to run super fast between all the components within this chunk. It is super fast because it is accessing contiguous memory locations, meaning one all after the other. Whereas with game objects, those are regular objects. So for those, the CPU basically has to jump from all kinds of positions in memory in order to find whatever kind of data it needs. So it needs to go forwards, backwards, and so on, constantly jumping in memory, and this is actually quite costly. This leads to a lot of things called cache misses, which is where the CPU basically loads a ton of positions in memory when it requests one position, which is how the CPU basically requests a ton of positions in memory and stores it in a super fast cache. But then if you need to access some other position that is not loaded within the cache, then basically it needs to unload that entire cache, load the new cache, and finally grab that memory. So that is how when dealing with ECS, when the CPU loads an entire memory chunk into the cache, since all of the memory positions are contiguous, All of them get access without any cache misses. That is how dots is so insanely fast. So when working with dots, almost everything is going to be based on structs in order to benefit from that memory management. Now in general, changing something from a class onto a struct literally just means swapping out the keyword. Instead of class, we write struct, and yep, that's it, that defines it as a struct. And in doing so, naturally, we change it from reference type onto a value type. However, that change does have some very important implications. The main one being in terms of working as something as a copy versus as a reference. So for example, if we have a class, myClass, and we construct an instance of that class, and then a second one, and we make it equal to the first one, when doing so, both these variables, myClassA and myClassB, both of these are storing the exact same position in memory. Because again, these are classes, meaning they are just storing the positions in memory, they are not actually storing any data itself. And in doing this, basically they are both just storing the exact same position in memory, and the actual data, they are both pointing to the exact same data. Now what that means is if we went to go through myClassB and modify some field inside of it, it would also modify the value inside myClassB, because again, both variables, both are referencing the exact same underlying data. Whereas if we do that with structs, structs are value types and not reference types. So if we do the same thing, so construct a brand new struct and then assign a second one onto that one, if we do this, instead of having two variables that both point to the exact same object, instead of that, we have two copies of the underlying data. So if we were to modify some field inside myStructB, it would not automatically modify anything inside of myStructA, because again, both are separate pieces of data. They are not pointing to the exact same thing. When working with structs and when we assign a struct, what we are doing is we are creating a copy. We are not storing the same reference to the original data in memory. We create a copy of the data. So when we modify something inside myStructB, we are modifying just that copy and we are not touching the original data at all. Now this is really very crucial to understand. You must fully internalize this difference, really understand how structs work as copies and not references. You need to know this so that you don't get confused when at some point you write some code and have no idea why it isn't changing. It is probably because you're working with a copy of the data and not the original data itself. For example, later on in this course, when we write some systems, we are going to see how if you get some component and you just modify it, it won't actually update the value in the component attached to the end, because again, the component will be a struct and structs receive copies. So modifying that copy will not modify the original data. But we'll cover that when we get to systems. For now, I hope you understood the difference between structs and classes, the difference between value types and reference types, or the difference between managed and unmanaged. All of that is extremely important to dots. So now we can continue working with our component. All we need to define a component is, again, make it a struct and make it implement iComponent data. That's it. This is now a dots component. And now inside this, we can place whatever that we want to store inside of this component. For example, for some kind of move speed component, let's just store a float for the move speed value. So we literally do just this, so public float and call it value. That's it. Also, by the way, if you're a regular on my channel, you might have heard me talk a lot about clean code principles, and the main one is how you should never make everything public. Usually I tell you to always make it private and then expose it with some kind of field, like float get value, and over here you would return the value. This gives you a lot more control as to how your fields are accessed, so that's how I usually recommend you do it. However, ECS is a very different thing. That oriented design is very different from object-oriented programming. For example, components in ECS, these are not meant to have any functions at all. These are just meant to store data, just fields, just data. So you are really not supposed to have any kind of functions inside of your component. Technically, you can do it, the compiler won't stop you, but you really should not put any functions inside of your components. The general idea of ECS is you have entities, which are really just IDs. Then you have components, and those should only store data and nothing else. And then you have systems, which are the things that actually do some work, do some logic on that data. So since dot components are really just meant to be simple data containers, if so, then it makes sense for them to just have their data directly exposed, so making it public. This makes sense in dots world, in ECS world. When working with normal game objects, I definitely encourage you to keep those same clean code principles in mind. When working with mono behaviors, always minimize access as much as possible. But over here in the world of dots, in the world of ECS, go ahead and expose your fields by making them directly public. Okay, so here we have defined our component. The component is called moveSpeed, and inside we just have a value field of a float. So let's just go ahead and save this and wait for Unity to compile. However, now if we inspect our entity, if over here we click on the unit and look at the runtime component, and nope, it still does not exist. Unity does not exist because again, it's completely empty, so this entity would not have any component. Naturally, it did not magically get our newly created component added. So the question is, how do we add a component onto an entity? So one way is through code. We can just call a function to add a component onto an entity. We're going to do that later on many times. But once again, we can really just use the baking process. So like we already saw for the default components, how those get used as normal game object components and then they get converted, get baked into dots components. That is all the baking logic, and we can also implement baking logic for our own custom components. That way we can keep building our objects using normal game object components and then have them be baked into dots components. So the way we do that is with a monobehavior component. So on the scripts, let's right click, go ahead and create. Let's create a new monobehavior script. And now for the name, a nice convention is to name it just like the component, so move speed, and then simply append the word authoring onto it. So move speed authoring. So yep, just like this. Here is the normal monobehavior component, the standard thing that I'm sure you're very used to. Now here we can add whatever fields we want to have in our monobehavior component. In this case, since in our move speed component, in this one we expose some kind of value, let's do the exact same thing. So over here on this one, let's also expose a public float value. However, again, let me mention this is not a requirement. Like we saw in the previous lecture, you can have one authoring component that gets baked into multiple different dots components. So your components do not have to have the exact same fields. It all depends on what you're trying to do. In this case, we do want to easily define the move speed value on the authoring component and use the exact same thing in the dots component. So up here on the monobehavior, let's define the same public float value. Okay, let's go ahead and save this. Wait for Unity to compile. Then let's select our unit. And in the inspector, let's put it back into authoring mode, and let's just drag our move speed authoring component. So just the same as any authoring component. However, just like this, we still don't have any baking. We can see down here the empty baking preview, that one is still empty. We have created a dots component and we have created a monobehavior authoring component, but those two are still completely separate things. There is no connection. The way we define that connection, or rather the way that we define the baking logic, is with a baking class. So here inside of our monobehavior, inside let's define a nested class. Let's make a public class. Now we can name it whatever we want. I like to name it just baker. And then the very important part is let's extend the baker class. And it's this one right here, the one inside the unity.entities namespace. So make sure you add that one on top. And this one takes in generics. And the generic type should be what type we want to bake, which in this case, we want to bake this type, the move speed authoring. So let's go ahead and put it like this. So yep, here we have a baker class, which extends this baker class. Now the important thing is over here on the type that you use inside the baker generic, it is the authoring class. It is not the dots component. It is not this one. It is the authoring component. Okay, great. And also, like I said, for the name, you can call it whatever you want. You can use whatever word you want here. It doesn't really matter. It does not have to be called baker, but I think that makes quite a bit of sense. And also technically, it does not have to be a nested class. We can put it down here and everything works the same. But again, I think it makes sense since it is related directly to this component. It makes sense to place it directly in here. So with this, we have defined our baker and we can see we have an error. Basically, we need to implement this bake method. So let's do that. And actually, we can use Visual Studio to help us. We can place the cursor on top of the error, then use the quick actions to implement the abstract class. And if there you go, it writes the code automatically. If you're not using Visual Studio or you don't have these kind of quick actions, you can just manually write this function. So we've got a public override void. We're going to override the bake function. And this one is going to take in a parameter of the exact same type as our authoring component. Okay, so now we need to implement this function. Now this one is going to run during the baking process. And in this function, we do have an access to our authoring object. Meaning this is where we can grab this component, which in itself has all the data that we want to expose, and we can convert this into our regular dots component. And in order to add our dots component, we use the add component function, and this one takes in an entity parameter. So the way we get our baked entity is with another function. So let's call get entity. This one takes in a parameter for our transform usage flags. Now this is a really nice optimization thing. It has to do with whether we want the baked entity to have a transform component or not. Like we saw a while ago, if we were to remove the box highlighted component, then the baked entity would not have a local transform component. That's an optimization thing. So here for the transform usage flags, we have a bunch of options. For example, if our entity never moves and does not have any kind of concept of a world position, like for example, let's say if it's an inventory container, if so, then we can just select none and it will not have any dots transform components. Or if the entity does have a world position but will never move, like for example, static visual objects placed in the world, for that one we can use renderable. In doing so, it will have a matrix component in order to be able to render, but will not have a local transform since again, it will never move. So if you want maximum performance, definitely choose the most restrictive usage flags you have here. But in most cases, you probably want your objects to be able to move. So in this case, let's go ahead and choose dynamic. This means this entity, which in this case is going to be our unit, this one will have all the transform components, which means it can have a world position, it can move, rotate, scale, and so on. So yep, this function will now return our baked entity. And now using that entity, we can then add some components. And specifically in this case, we want to add our move speed components. Over here, just new move speed, and let's add this component. And yeah, that's it, we are adding it. But we also want to assign the value in there. So instead of adding it like this, instead of constructing using the parameterless constructor, instead, let's just open and close the curly braces. And then in here, we can set the value. So this is the value inside of move speed. We can grab the value from the authoring component. So let's go inside the authoring component and grab the same value. Okay, so yep, that's really it. So basically, this function is going to run during the bake process. In doing so, it will create an entity that has the dots transform components. And then it will add a component onto that entity. And the component we're going to add is our custom move speed component. And that component will be initialized with the value field on exactly the same as we have in our authoring value field. So if that's it, let's save. Just wait for it to compile. And now here in the editor, let's make sure the inspector is on authoring mode. And over here, let's set the value speed again on the authoring component, so the mono behavior component. Let's set it to some number, like let's say 56. And yep, now let's go swap the inspector into runtime mode. And sometimes this bug happens, so this entity does exist, but for some reason this bug happens. If it happens, very simple, just deselect and reselect the unit. And yep, there you go, now it does show. And if we scroll down here, yep, we do see it does have our custom dots move speed component. And yep, the value does match exactly the one that we set in the mono behavior component. Alright, awesome. So basically we created a brand new component type called move speed. It implements iComponentData, meaning this is a dots component. Then we also created an authoring component. This is a normal mono behavior component. We attached that normal mono behavior component onto our normal game object. Then we wrote the bake logic in order to convert the authoring component into a dots component. And if the final result is that our baked entity does have our custom dots component with exactly the data that we want. So yep, everything worked perfectly. Now that everything is working, let's just do one more thing. So right now we have two scripts, the move speed and the move speed authoring. This works as you can see, but in order to not end up with literally hundreds of files in our project with a ton of duplication, in order to not have that, we can also just merge both these into just one script. To do that, let's go ahead and grab our dots component. So let me cut this one, go onto the authoring component, and let's paste it right down here. Now let's go ahead and save both these files. In Unity, wait for it to compile, and let's delete the move speed. Okay, up like this, let's make sure everything still works. And yep, the unit does still have the dots component, and on the authoring, yep, does have the authoring component. So this works, but now we have just one file, and this one file contains both the authoring component, the baker logic, and the dots component. So this makes it quite a bit easier to work with. Everything is just in one place, very easy to work with. Also, let me make just one quick note here. In order to make this work, then the name of the file here, the file name itself, this one has to be named just like the mono behavior component. If you were to name this file just move speed, it will not work. In order to use this authoring component as a regular actual mono behavior component, in order to use that and be able to attach it to some kind of unit, then the file name does need to match whatever class is inside of it. So in order to use this method of putting everything in just one file, just make sure the file name itself does match the authoring component. So yep, down here we have our dots component, then we have the authoring component, and inside we have the nested baker class, which bakes our authoring component onto our dots component. This is the standard format that I will be following throughout this course when making components. Dots component, authoring component, baker class, and so on. Also, let's keep our project nice and organized. We're going to end up with tons of scripts. That's one thing about dots, you do end up with quite a lot more files than with object-oriented programming. So in order to make sure this does not become very messy, let's make things nice and organized. So inside the scripts folder, let's right click, let's create a brand new folder and call it authoring. And this is going to be where we place all of our authoring components. Let's just verify again that everything is working. Let's set on play mode. Let's select the unit. Yep, it does have the component with whatever value we want. Then go into runtime. And yep, it does have the move speed component, the dots component. Okay, great. All right, so by now we have already learned how to create entities by placing a game object inside a subscene and letting the baking process do its thing. We also learned how to create a custom dots component and how to create the authoring component that bakes game object data into dots data. So we've already learned both the E and C in ECS, the entities and components. Now what's left is the S for systems, so let's learn about that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to write our first system to make our unit move. This requires us to learn how to do entity queries. We're going to first just move a transform and then later on do it using physics. Okay, so far we have our move speed component. It stores a field for the actual value that we're going to move. we have implemented the baking system and attached the authoring component to the game object, so the final entity is going to be baked with our component and with the correct value. But so far it's not doing anything. If I hit on play, then obviously nothing happens. So going back to how ECS works, entities are just IDs, components store data, and systems are what do logic on that data. So let's make a system to move our unit. So here in project files, again, let's keep things nice and organized. So inside the scripts folder, let's make another subfolder. This is going to be for our systems. And now inside the systems folder, right click, let's go into create, let's go down under entities. And now let's make this one an iSystem. For the name, let's call it unit mover system. And let's open. By the way, personally as a rule, I like to append system to the name of my systems. You don't have to, it's not a requirement. I just find it helpful to easily be able to identify what types are systems. Okay, so here we have our default system. Now, once again, Dots has some very specific requirements. So first of all, we need to implement iSystem. This interface has a bunch of functions. This one also needs to be marked as a struct, not a class. And importantly, this one needs to be marked as partial. Now, if you're not familiar with the partial keyword, basically this is how you can define a type in multiple files. So you can define part of the class or the struct in one file, and then another file define another part. The way Dots works is very much based on source generation, meaning you write some code, but then the system auto-generates a ton more code in the background to make everything work. That's how, despite Dots actually being so complex, it is not that difficult to use. It is because a lot of the tricky code is actually auto-generated. But here the important thing is these requirements: implement iSystem, make it struct, and make it partial. Also, let me make one quick mention. ECS actually has two different system types. We have our iSystem, but then there's also system base. Now, the difference between these two is system base meant for managed systems, and iSystem is meant for unmanaged. Or put another way, iSystem is meant for structs, and system base is a class. Now, in general, you should prefer iSystem as much as possible, basically because it will be burst compatible and much faster. In this course, I actually don't think we're ever going to be using system base, just because whenever we want to do something that uses lots of managed data, we're actually just going to make it using a normal mono behavior. So in general, don't really worry too much about system base, just know that it exists, but for the most part, we're going to be using iSystem. Okay, so here we have our system, and as you can see, we have our three functions by default: on create, on update, and on destroy. So their names are pretty self-explanatory. On create is going to run just once when the system is created. Then on update, this one is going to run on every single update, pretty much like a regular mono behavior update. And finally on destroy, this one is going to run when the system is destroyed. Now in terms of lifecycle for systems, by default, systems will automatically be created and destroyed, so you don't actually need to worry about manually doing this. As soon as we play the game, the automatic bootstrapper will handle all of that. It will automatically create all the systems and handle all that logic. So we don't have to manually initialize it in any way. We don't need to add it to any entity, any object. Just by existing, just by implementing the iSystem, it will automatically be registered with the automatic bootstrap. And these functions are also optional. So for example, to keep things simple, let's actually delete the onCreate and the onDestroy, since we're actually not going to be needing these right now. Right now, all we want is the basic onUpdate. Also, you might notice the burst compile attribute over here. I'm going to talk about burst in a little more detail in a future lecture when we work on the job system. But basically, by adding this attribute over here, by doing this, we are enabling burst compilation directly on this function, meaning it's going to use burst, which can make it super fast. Again, this becomes very important later on, and I'm going to cover it in a few lectures, but for now, just leave it on, just like this. Now, the goal with this system, our goal is to move our unit. So if we go back to the theory behind Dots, the reason why it is so fast is because of memory management, how it packs memory tightly together for all of the components. That way makes it super simple to cycle through thousands of components. And the way we're going to run our system logic is with a query, meaning we define all of the components that we want to run that query, and then the code will automatically cycle through all the entities that match all of those components. Here in the code, the way we define a query is pretty simple. We just use systemapi.query. This one takes in generics, and the generic parameters over here is going to be where we define all of the component types that we want to query for. So in this case, we want to move our units. So to move them, we're going to need the transform, so the dots transform, which is actually called local transform. And this one exists inside the unity.transforms. And just with this, we should be able to move them. So this is our query, and this function over here, this one returns an IEnumerable, meaning the way we cycle through all the entities that match this query is by putting this code inside a for each. So let's do a for each. And for the parameter, it is going to be of the type of the components that we're grabbing. So local transform, call it local transform in our query. And yep, just like this. Now any code that we write inside of here, all of this is going to run for every single entity that matches this query. However, it's not actually like this. this code will not actually run properly. Once again, it's due to how structs work. They are value types, meaning they work as copies. So if we just use this code and we modified something inside this local transform variable, if we did, we would only be modifying the local copy and not the original data in memory, so the unit wouldn't really move. So because of that, over here in our query, we never write just the component type directly. Instead, we have a helper class that essentially kind of transforms the struct into some kind of reference type. So that type is called refrw, and this one takes in a generic for the actual type that we want to cycle through. So you have to put refrw in there in the query and also over here on the iterator. Yep, just like this. So ref really just means this is going to act as a reference, even though the underlying component, this one is a struct. By using this one, we are essentially turning that struct into a reference. So as we modify things inside of this variable, we're actually going to modify the actual data. And then RW, that really just stands for read-write, meaning we can read this component or we can write to it. And the other alternative is we have refro. This one stands for read-only, meaning with this one, we can only read from this, we cannot write to it. So now you might be asking, why would you ever limit yourself to read-only if you can read and write? And the answer is this will actually become super important later on when we work with the job system, meaning when we have code that runs in parallel on multiple threads. I will explain more when we get there, but the general idea is you can only write to something from a single thread, whereas you can read data concurrently from multiple threads. So for example, if we have 100 entities and we're running some job that reads data on all those entities, then we can have, for example, 10 threads all reading data at the exact same time. Whereas if we are using a refrw for read and write, if so, in that case, then all those entities could only be processed in a single thread because you cannot have multiple threads write to the same data at the same time. So in general, you should only request the level of access that you absolutely need. Basically, the more refros you have, the better. The more refros you have, the more parallelized your code will be. So if you only need to read something, definitely make it a refro. But if you need to read and write, then go ahead and make it refrw. In this case, we are trying to make the unit move, meaning we're actually going to need to write a brand new position. So because of that, let's go ahead and use refrw. Okay, so yep, here we have our nice system with our query. And now, like I said, the code inside of this for each, this will run for every single entity in our world that has a local transform component. And just quickly, let me make one more note on multithreading. Right now, this code is not multi-thread at all. This for each will just run on the main thread no matter how many entities we have. So if we have 1,000 entities, then this for each will run through all of those 1,000 entities on the main thread one by one. Making something an I system and writing a for each, that by itself does not make it multi-thread by default. We're only going to make this code multi-threaded when we implement jobs in a few lectures. So I just want to very quickly point that out. Okay, so here we have our for each. Now, like I said, this will cycle through all the entities that have a local transform component. And now inside of here, we can do whatever we want to this local transform. So as a quick test, let's just move everything to the right. So let's access the local transform. And now inside we have two nice properties. We have the value RO and the value RW. Again, same thing, read only or read write. In this case, we want to write to the position. So let's grab the RW and we're going to write onto the position. So let's modify this field. Let's put the position equals, and the goal is to move right. So let's grab the current position. So local transform. Right now, we just want to read, so let's grab the value RO to grab the current position. And now we want to move it onto the right, so let's just add a new float3 onto it. And by the way, float3, this is a special type that is part of the unity.mathematics library. So let's go up here, add using unity.mathematics. And over here, we can define a new float3. This mathematics library is what I mentioned a while ago on how it's super fast and specifically designed for dots and bursts. So this float3 over here, this one is basically a vector3. Meaning inside we have floats for x, y, and z. So really just like a vector3. So in order to move it onto the right, for this, let's construct a brand new float. Let's put it 1 on the x to move right, 0 on the y, and 0 on the z. And yep, so we add this onto our position and we save the brand new position. So just like this will move to the right by 1 unit. Except, as I'm sure you know, when moving anything, you want the movement to be frame rate independent. So over here, let's make sure to multiply by time.delta time. However, again, dots also has a special time.delta time. We should not use this default one. This one for the standard Unity engine. We want the one that exists in the dots world, not the game object world. So instead of time.delta time, we go through the system API, go through this class, access time, and finally delta time. So yep, just like this. Okay, so here our code is done. So we have a for each doing a query on everything that has a local transform. And this code inside of here is going to run on every single entity that has a local transform component. it is going to grab that one and set it to basically the same thing, moving right by 1 unit. Okay, so let's go ahead and save and let's test. So hit on play, and yep, right away it does work. There's the unit constantly moving right. Alright, awesome. Except it's actually not entirely awesome. So this is working, our unit is moving, but it's actually not just our unit. As test over here on the hierarchy, let's go inside the subscene and let's construct a brand new, let's say, cube. Let's create a cube and let's put it over there. Okay, so we have our unit and we have a cube, and now if we hit on play, and yep, look at that, both the unit and the cube, both of them are moving right. And not only that, but actually the child mesh object, that one is also moving right. That is why the unit seems to be moving at double the speed as that one. So basically everything is moving right. Now this is actually a key point about dots. It's how systems do not care what a certain entity represents. The system does not care, does not know that this is a unit and this is a cube. It does not know any of that. If an entity has components that match the query, then the system will run logic on that entity. So basically how you define whether something is a unit or a rock or something like that, the way you define that is by adding components onto it. By the way, there's also a systems entities window. So if we go up here on the menu, let's go into window, down into entities, and open up the systems window. And yep, this one over here is going to show all the systems that run all the time. So let's go ahead and hit on play in order to see these in action. So let's hit on play. And now if we find, yep, here is our unit mover system. And over here under entity count, we can see 3, meaning our system is being applied to 3 entities. So that's the cube, that's the parent game object, that's the parent entity, and the child entity with visual mesh. So naturally, this isn't what we want. We want to just apply the movement onto the unit. So over here, this should be saying 1. This systems window is sometimes useful, so let's leave it open. Let's just put it over here next to the console. Okay, great. So now let's figure out how to make our movement apply just to the entity that we want. In this case, that's actually going to be super simple. We can just add another component to our query that only exists on the unit. So we can just use the move speed component that we already created. This one only exists on the unit and only on the unit parent object. So that one should perfectly target just the unit. Over here in the code, let's add some more components over here into our query. And the way we do is very simple, just add a comma and then another type. In this case, we want the move speed component. Again, importantly, it's a move speed, not the move speed authoring. Nope, over here we're working in the dots world, so we want the dots component. And again, we need to define either refRW or refRO. In this case, we only want to read the speed from it, so let's use refRO just for reading. So we add it over here, and then also need to add it over here on the first parameters. And when we have more than one, we need to put this inside parentheses. So let's open parentheses over here, close them over there, then do a comma and add the move speed component. Also for readability, I like to add some new lines. So add a new line for every single component, then new line over here on the in, and then on the query components. And yep, just like this, it is nice and readable. So we are doing a query with local transform and move speed. And importantly this is an AND operation, meaning our query over here, it is going to be looking for entities that have both of these components. They need to have a local transform and a move speed component in order to run this code. But at the same time, it is not an exact match, meaning it can have more components than just these two. It just needs to have at least both of these. Also, after the query, after we open and close the parentheses, afterwards we can add a bunch more options. We can type with and we can see all kinds of things. For example, we can use with none in order to specify this should only run on entities that do not have the following components. We can use with disable. This will make it include enableable components that are disabled, and so on. As you can see, we have tons of options. We're going to use these a bunch later on to make some more complex queries, but for now, let's keep it simple. We just want these two components, local transform and move speed. Since our unit is the only thing that has both these, then this should only run on the unit. Also, one quick note in terms of syntax. So you can write code like this. This is personally what I prefer, to be very explicit with exactly every single type. However, if you prefer, you can also just use var. So just type in var before that parentheses, and then over here do not define the type, just define the names, just like this. And yep, this is valid code, this is valid syntax, this works exactly the same. Some people prefer this. Unity actually uses var a lot in their own documentation. Now personally, I am not a fan of var. I like my code to be as explicit as possible so there are no questions. I want to be very, very clear on what type my variables are. But again, that's really just a personal preference kind of thing. So if you do like var, then you can definitely write your code just like this. But I will be sticking with my preferred method of being more explicit by defining all the types exactly. Okay, so far so good. So we have our query, and the query is going to run on entities that have both of these components. Now let's just use the move speed value directly in our logic. So instead of moving right by 1 unit, instead of that, let's read the value. So let's go inside the move speed, go inside the value RO because we only want to read it, and let's grab the value field inside of it. So yep, just like this. Let's go ahead and save. And back here in Unity, let's modify the authoring component and make it move at a speed of maybe 5. Okay. Now let's hit on play and see. And if there it is, now our system is only applying to that unit. It is not applying to the cube. It is not applying to the channel mesh and anything. Now it is only running exactly on the thing that we want. So it is only running on the entity that has both a local transform and a move speed component. By the way, we can also edit this value in real time. So over here, I can click and drag to modify it, and yep, it does work. And also if we're in the other inspector, so let's go in runtime mode. So here is all of the components, move speed, and I can also play with this, and yep, all the changes work. Now this is another example of dots data-oriented design in action. We can very easily modify the data, and then by doing that, when the systems run logic on this data, it will then have a different behavior. Alright, great! So here our unit does move towards the target. We've achieved movement by directly moving the transform, but to make the game feel a little bit more interesting, we're actually going to want to use physics in order to move this unit. So let's add that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to move our unit using physics. This is going to be quite easy actually, thanks to how Unity handles the built-in physics components by default. Okay, so here's what we have so far. The unit is constantly moving, so it has a component for the move speed, it has a system called the unit mover system, and it is moving the unit, so that's it, very simple. Except right now it is only moving by moving the transform directly. We want the unit to be able to interact with other objects, so let's make it using physics. But before we implement physics, let's just add one tiny thing. So over here right now the unit is moving, but it looks a bit odd as it's facing forward and moving left. So let's make it rotate towards the move direction. So here we are in our unit mover system. Okay, we have the local transform, our move speed component. Okay, great. So in order to rotate towards that direction, first of all, let's actually calculate the move direction vector. So we have a float for a move direction vector. Actually, this is a float 3, which again is pretty much the equivalent of a vector 3. It's just in the special mathematics library. So that one, first of all, requires the target position. So let's actually define it, as opposed to over here, we're just moving right, or actually just moving towards the move speed. So let's define a float 3 for the target position. This target position will eventually be an actual proper position, like for example the mouse position or whatever position we tell this unit to go to. But for now, again, let's just make it move to the right. So target position, just go into the local transform, onto the value RO, just for reading. Let's grab the position and add a new float 3, and just go to the right by 10 units. Okay, so this is our target position, and calling in direction, some super simple math, so just target minus the current position, so that's the local transform, dot value RO for reading, and let's grab the current position. So yep, this calculates our move direction vector, except again, as I'm sure you know when it comes to vector math, over here this vector will not be normalized, so let's make sure to normalize it, to set the magnitude to just 1. When working with the normal vector 3, usually you can just call dot normalize, but over here this one does not have that. So normalizing a vector in the new mathematics library, for that one you assign the vector, go inside the math class. Again, this is the one inside unity.mathematics. Inside of this one there is a normalize function. So this one takes in a parameter, so we pass in our move direction, and it returns the move direction but normalized. Okay, so yep, so with this we have our move direction, and then let's just use it over here. So instead of recalculating the direction as well, let's just set the position, and let's do position plus equals, let's add on to the position. Let's move towards the move direction, multiplied by the move speed. Let's grab the value RO for reading, and let's grab the move speed value, and then finally the time dot delta time. Okay, so yep, just like this, we should be doing the exact same thing, so really just moving right. Let's just quickly verify. In order to actually make it move right, let's make sure that the move speed component does have a positive value. Otherwise, if it has a negative speed, then naturally it's going to move to the left side. So let's select our entity inside our subscene, and let's go into our authoring component over here. Just make sure it has something like 3. Okay, let's test. And if there it is, unit moving right. Okay, great. Now let's add the rotation. So adding the rotation when we have a move direction, this is actually surprisingly simple. On the local transform that we've been using, on there we have the position, but then we also have a rotation. We have a rotation as well as a bunch of functions to rotate by a certain amount. In this case, we want to set the rotation to something. Now in this case, this rotation field, this one is a quaternion. And again, note how it's quaternion written like this. It's on lowercase, not uppercase. This is the mathematics quaternion. So to get a quaternion for this move direction, it's actually surprisingly simple. We can go inside the quaternion class, and then we can use the function loc rotation. This one takes a forward rotation, so let's pass in our movement direction, and then an up vector. So here we can just do new float 3, 0, 1, 0. So this is our move vector, or we can actually use a constant, and the constant is going to be the math.up, and this is actually a function. This one will return the exact same thing, 0, 1, 0, and yep, like this, it should work. Okay, so with this, let's do a quick test. But also one thing, definitely make sure that you have the child object. Definitely make sure this one is exactly like this, everything on 0. It should be on position 0, 0, 0, rotation 0, 0, 0. If you do it like this, it should point in the right direction, but if you apply some kind of rotation here, then it won't point exactly. So make sure all of these are on 0, and let's hit on play. And if it does work, look at that, there's our unit moving right and facing right. Alright, awesome. Okay, so now we have achieved our movement by just moving the transform. But to make the game a little bit more fun, we want to use physics. We want our characters to be able to interact with other physics objects. So let's do exactly that. As usual, let's set up our unit over here with normal components. So let's select the parent game object. And this one over here, let's give the unit a shape. So let's give it a regular capsule collider. Then let's set up the settings. We can see over here on the scene view. So let's make it a little bit higher. So with a height of 2. For the radius 0.5, yep, that looks good. And let's just lift it up a little bit so it doesn't touch the floor. Let's say 1.1. Okay, yep, so there's our unit collider. And again, just like this, just by attaching a capsule collider, just this will automatically convert into dots physics. We can already see down here, yep, the unity.physics collider, this one will be added. So with this, we have a collider. And then for actually using physics, we also need a rigid body. So let's add that one, a rigid body. And again, just by adding, it added a bunch of big components down here. Then for the rigid body settings, over here for the interpolate, we want it to be nice and smooth, so let's make it interpolate. Then we don't want this unit to fall down, so let's make sure to disable gravity. And over here on the constraints, our unit should really only move on the XZ axis, so let's freeze them on the Y. We don't want them to move up or down. And same thing for the rotation, since we're going to rotate them manually. Okay, great. So that's our setup, again, using normal game object components. And if we put the inspector over there into runtime mode, and yep, here we do see all of the various components. Now our goal, like I said, is to move this unit using physics, meaning for move it, we actually want to modify the velocity, and yep, we can see it right here. This is the component we want to modify, the physics velocity. This one has a linear for the linear velocity, and angular that affects the rotation. So instead of manually moving transform, we want to be able to set this linear field directly inside the physics velocity. So back in our code here, in order to be able to modify the component, we just need to add it over here in our query. So let's add another one. In this case, we want to modify it, so let's make it a ref rw and call it the physics velocity. And yep, it is this one, again, inside unity.physics, so let's make sure to add this namespace. So yep, this is the component that we want, and let's also add it up here. So we've got the ref rw physics velocity. Okay, yep, so we added a new component to our query. And now down here, for the rotation, we still handle it normally. But for the movement, instead of moving the transform directly, instead of that, let's go inside of this one. Let's go inside value rw because we want to write to it. And we're going to modify that linear field. And the linear velocity, this one is going to be set to our move direction multiplied by our move speed. So move speed, let's grab it just for reading, and let's grab the value. And yep, that's it. Again, here make sure to not include time.delta time. Here, this is really just setting the velocity, is not actually moving the object. Then the physics system afterwards, they will apply the time.delta time, or actually the fixed delta time. And that is what actually moves the object, so make sure you don't include it over here. And also, since our units are going to collide with each other, that's actually going to mess things up and actually trigger some rotation. Later on, we're going to implement some proper collision avoidance logic. But for now, while that is still going to have tons of collisions, we don't want it to completely break everything, so let's make them not rotate. So here, let's make sure, even though we freeze the rotation, even with that, it will still rotate if it forces some collisions. So let's manually just set the angular velocity into 0. So we can just go inside float3 and access float3.0. Okay, yep, just like this, it should work. So instead of modifying the local transform position, instead of that, we are just assigning a velocity. So let's save, and now let's test. And if there it is, the unit is still moving exactly as intended, except now it is doing so using physics. Now we can actually verify that. So in our scene, let's add some objects. So inside the empty subscene, I'm going to add a bunch of cubes. So let's construct a brand new cube. By the way, you don't need to follow this part. This is really just for testing. Just make sure that all of this is working. So I'm just going to place a bunch of cubes. Place them like this. One over here, one over here. Then place a bunch more on top and a bunch more on top. And for all of these, let's also add a rigid body component. Just make sure they fall down, rigid body, just like this. Okay, so with this, we have a bunch of cubes. Our unit is going to go right and should interact directly with those cubes. So let's try and test, except nope, that didn't actually work. The cubes fell down and fell down through the ground. And actually, that makes this an excellent time to mention how dots physics and game object physics, those are completely separated. Those are two completely different worlds that do not interact with one another. These cubes that we just created, these are placed inside a subscene, meaning these are going to be converted into entities. They're going to be using dots physics. But the ground, this one is still a normal game object outside of the subscene, meaning this one is using just normal game object physics. So that is why the cubes went through the ground. That is because they are working on completely different physics systems. It's as if for the cubes the ground does not exist, and it's as if for the ground the cubes do not exist. Because again, both physics were like completely disconnected. Now in order to see this working, it's actually very simple. Let's just drag the ground directly inside the subscene, and now they should all be baked into dots physics. So now let's test. And okay, yep, they stay there, the unit goes, and if there you go, the unit does move and does interact with those cubes. Alright, awesome. Okay, so here we are using dots physics. The unit moves, it goes through, interacts with those objects, and everything works great. And again, remember how dots physics and game object physics, those are two completely separate worlds. So let's revert to what we did for this testing. Let's put the ground back outside, and let's delete all of our testing cubes. Yep, just like this. Okay, so here we set up our unit mover system, which is a query for some components that match exactly what our unit has. Then it used that to move that unit. We saw how to do it by moving a transform directly, and then by moving it using physics. However, right now our unit is moving to a fixed point. It is constantly moving to the right. So let's implement some logic for making it move towards the mouse position. So let's do that in the next lecture. Alright, quick intermission. I just want to ask you, how are you getting along with dots? Does the concept of entities, components, and systems, does that make sense? What about the baking system? Are you finding it relatively easy to write code in a data-oriented mindset? Dots is a very new technology, and I tried as hard as I can to make the course have a really nice smooth learning curve. So I want to hear from you if you are managing to learn everything correctly. I found that during my own research, once I started understanding the core concept behind dots, everything suddenly became much easier. Nowadays, after all my research, after learning a ton, now I can very easily picture a new system in my head and already think about all of the components and how do I organize them in order to make whatever I want to do. So do let me know in the comments your thoughts so far. Feel free to post any questions you have and I'll do my best to help. So pause the video to do that, and then let's continue on to the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to get the mouse where on position so we can tell our unit to move there. We're also going to learn about one very important topic, which is deciding what system should be using dots and which should be normal mono behaviors. Alright, so let's get our mouse where on position. Now, how to do this is actually quite simple in technical terms. The more interesting part in this case is where do we write this code? Now, when I was first researching and making the prototype for this course, I started by making it a normal I system using dots. And it did work. I had some logic working on a system. I would store the mouse where on position in a component and read from it from various other systems. Then I added the selection logic on top of it. And again, I got it all working with dots, but the whole process was definitely becoming needlessly confusing and very convoluted. So that's when I remembered how you don't have to build everything using dots. Always remember how you don't have to go 100% dots or 100% game objects. You should mix them and use the right tool for the right job. So the rough general rule that I came up with is actually quite simple. For things that are not performance critical, or simply don't run all the time, or only run on a single object, so things like mouse where on position, or the unit selection manager, or the resource manager, inventory, and so on, for those, write them as normal mono behavior scripts. And then for things that do require maximum performance, or impact on lots of objects, like for example moving units, for that do use dots. So that's the rough guideline that we're going to follow throughout this course. Following that makes things quite a bit simpler and makes it easier to decide when should something be dots or a mono behavior. So with that said, let's make our normal mouse position script. We're going to make a normal script, so let's go inside the script folder. Let's actually make another folder for the mono behaviors, and let's right click inside of that one, make it a normal mono behavior script, and let's call it the mouse where on position. Then as always, let's make a normal game object to run it. So an empty game object with the exact same name. Again, outside of the subscene, this is a normal game object. Let's attach the script onto it. Let's reset transform, put everything nice and clean, and open it. Okay, so now here let's use some super simple mouse where on position logic. Now there are various ways we can do this. We can either use physics or not use physics. So let's do the simpler approach without physics. First, let's make a function, so make it public so that everything can get this. We're going to return a vector3, and let's call it getPosition, so this will return the mouse where on position. Now in here, let's begin by constructing a ray from the camera. So we can access camera.main, this is going to be our main camera. And from there, we can call the function screen.toRay. This one basically takes in a screen position and converts it onto a ray object. And for the screen position, we can get the mouse screen position by using input.mousePosition. Also, by the way, here using input.mousePosition, here we are using the input manager instead of the input system. Now, if you're seeing some kind of error in the code here, that is probably because you don't have input manager enabled. Although if you downloaded the exact same project files, it should already be set up correctly. But if not, let me just show you. Let me just return something just so this one doesn't throw an error. So just return that. Okay, let's save. So here in the editor, you can go into edit, then go into project settings. Then on the left side, let's go over here onto the player tab, then scroll down inside the other settings tab. And if you scroll down here, we should be able to see, yep, the active input handling. And over here, you can select to use the input manager or the input system, or you can select to use both. Personally, I really like using both. The input system is really awesome, but also quite a bit more complex, whereas the input manager is super easy to use. So while you can write this same logic using the input system, personally I really like the input manager just for its simplicity. And of course, always remember you can always refactor your code. So this is actually how I normally build all of my games. I start off with the simplest approach possible, and then later on, eventually I refactor it. So in order to be able to do that, let's make sure both are enabled, which again, should already be done by default. So back to our code here. So we have this, and this one is going to return a camera ray object. Let's actually name this mouse camera ray. So it's going to be a ray that starts from the mouse position and is pointing directly as the camera is pointing. So now with this, we just need to know where does this ray intersect our game plane. So for that, let's construct a plane, like using the plane class. To define a new plane, construct a brand new plane. This one takes in a normal and the origin. So for the normal, let's use vector3.up. We want the plane to be facing upwards. And for the origin, vector3.0. Okay, that's our plane. And now with this, we can simply do a raycast against this plane. So let's go inside the plane, do a raycast using our mouse camera ray. Then this is going to return whatever distance we hit. So let's return out float and just call it distance. This one is also going to return a boolean, whether it hits something. It should always hit something, but let's put it inside an if. Then if it hits something, then we can simply go inside the mouse camera ray and we call get point. This one basically returns a position along this ray axis at a certain distance. So let's just use our distance. And yep, this is going to be the mouse worm position. And if it doesn't hit, which should never happen, it should always hit something because the camera is always going to be pointed slightly downwards. But still, just make sure this code compiles. If not, let's return vector3.0. Okay, that's it. Pretty simple. We construct a ray object starting from the camera and using the input mouse position, that's the screen mouse position. Then we construct a plane directly on 0, 0, 0 pointing upwards. We do a raycast against that plane and we get the position. So this should be working. Let's do a quick test. Up here, let's do an update just for testing. So private void update. On update, let's just do a debug.log on this get position. Okay, that's it. Let's test. Okay, so here we are and we can see in the log, and right around here is around the origin. And yep, we do see down there the position. It is close to 0, 0. As I move to the right, yep, it is increasing on the X and on the Z. And as I move over here, lowering on the X and on the Z. So yep, everything does look perfect. All right, great. So here we have one method for doing this. This is just using math, no physics, nothing like that. This is really great and really simple if you have a flat game plane like we're going to have in this game. But for example, if you wanted to use a non-uniform terrain mesh with different heights, if so, then using physics would be a better method. The way you do that is actually quite simple. It's very similar to this. You would go inside physics and do a raycast. This one takes in a ray as well, so we can use the same mouse camera ray. And then we can use this version of the function that just returns an out raycast hit for the raycast hit. This one also returns a boolean, so if it is true, that means it is going to hit something. And if it hits something, then we just return the raycast hit, go inside it and access the point. This is going to be the position where it actually hit. Then if you want, you could also add an external layer mask. So you could use this version with the layer mask and use that to make sure it only hits the terrain collider. And with that, then yep, this would be working exactly the same, but using physics. So depending on what game you're making, you have two options. You can use physics or not use physics. Now in this case, our game is actually going to have a flat play area. So for that, we can just use the simpler, just math-based method. And yep, that's it. Here we have a nice function that returns our mouse worm position. Now let's actually use it. Let's get rid of our testing update over here. And now on the unit mover system, over here, instead of constantly moving to the right, over here we want to move towards the mouse position. So here, let's grab the mouse position. And in order to make it easy to access, let's actually make the mouse worm position a singleton. So back in this class, let's make the standard thing for making this a singleton. Now, since this is an intermediate course, I'm assuming you already know what exactly is a singleton. Basically, it's a super easy way to access a global reference, of which there exists only one of them. So here we can just make a public static of the type mouse worm position. Let's call it instance. Make it a property with a public get and a private set. Then we just implement the normal awake for our mono behavior, and on awake, set the instance equals this. Okay, that's really it. Now we can easily access this instance, and through there, then we can call this function. So let's go back over here onto our unit mover script, and when getting the target position, let's go inside the mouse worm position, access the static instance, and call get position. And yep, just like this, the unit should be going towards the mouse position. Let's make sure to save both files. Wait for Unity to compile. However, after we compile, we actually see an interesting error over here on the console. This is a burst error. It is telling us we cannot use burst inside of this function because inside it we are calling a managed function. We are calling our muzzle position.getInstance. Once again, when using burst, we cannot access any managed data. So this is why you have to be careful when not using just structs. If you don't, you get this issue, which means the code will still compile. We can hit on play and it will work, but it will not compile using burst, meaning the code will still run, just slower. Now, right now, in this example, we can really just ignore this error, since later on we're going to get the target position in a different way, but this is a great reminder of the limitations on burst. And when working with dots, don't get too scared if you see some burst errors, because again, they don't stop compilation, they're really just warnings to make sure that you know that burst is not working, so your code is not running as fast as it could be. But in this case, it should be working fine, so let's test, click on play, and if there it is, there's our unit moving, and it is indeed moving towards the mouse. So I place the mouse wherever, and the unit goes perfectly towards the mouse. Alright, awesome! So everything is working perfectly, but two things. First of all, the unit is going towards the target all the time. Now, usually in an RTS game, you want to be able to actually control it. It should really only move towards the mouse position when I click on it. And secondly, the rotation is way too snappy. It rotates to the target position 100% instantly. We want to make it look good, so let's make it smoothly rotate instead of being such an instant thing. Doing that is actually quite easy. So over here in our unit mover system, we are setting the rotation, and we are setting it directly to the final rotation. If we want to add some interpolation, we can actually use the slurp function. There's a function for it inside the math library. Again, that is the normal math library. Inside of this one, we have a slurp. Again, do not confuse that with the mathf library. It is not that one, it is the math library. So here we have slurp, and slurp, by the way, means spherical interpolation. So basically it interpolates from one rotation into another one, so we can use it to very easily smooth out our rotation. This one takes a starting quaternion, an ending quaternion, and then a time. So for the start, that is going to be our current rotation. So let's go inside the local transform. Let's read our current rotation. Then for the target position, that is going to be the one that we are calculating here. And finally, we have the t for the time. In this case, we can just use delta time multiplied by some rotation speed. So system API.time.delta-time multiplied, and let's define up here some kind of rotation speed. Let's put it some like 10f and use it like this. So then we assign our rotation into this. Okay, that should do it, and this should now make the rotation nice and smooth, so let's test. Okay, there's the unit, and yep, as I move the mouse, even if I move really quickly, the unit still moves at a relatively nice, smooth pace. Okay, great! So now to solve the other problem, we only want it to move when we click. For that, we're going to need two things. We need to store the target position instead of setting a new one every single time, and we're also going to need to test for a click. That is actually going to be an interesting challenge, so let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to get the unit to move to the mouse position, but only when we click. This requires refactoring our component and creating another non-dot script. Okay, so here we have our unit rotating and moving towards the mouse position, but we want it to only move on mouse click, not all the time. So let's solve that. And for that, we're basically going to need two things. So we need to store the target position instead of setting a new one every time, and we also need to test for a mouse click. Now first, for storing the target position, as always in dots, you store data in components. So let's actually refactor this move speed component to include a bit more data than just move speed. Let's rename this. So we can right click directly on top of the symbol, and let's click on rename, which will automatically rename everything. So let's rename this, instead of move speed, just call it unit mover. So this is our unit mover component. So rename that one, and let's also rename the authoring component. So let's rename it, and this one is going to be the unit mover authoring. Okay, so yep, everything has a different name, and now the unit mover system, this one is also using the unit mover. Let's just rename this one over here, so unit mover. So yep, that field has been renamed, the unit mover has been renamed, and over here we're not using it. Okay, so far so good. Then back in Unity, make sure the file itself did change. It should be called unit mover authoring. And if we go inside the unit itself, yep, it should still have it. And if we hit on play, yep, everything should still move. Okay, great. By the way, here, make sure your unit is not on 000. Move it just a little bit. This is important because otherwise you will get an issue with the math.normalize. If the move direction is 000, then this one ends up with nan, not a number, and that causes all kinds of issues. This will no longer be an issue once we add the stopping logic later on in the course. But for now, just make sure the unit is not on 000. So now on this one, let's add some more data. And actually, let's also rename this one. Instead of being value, this one is going to be the move speed. And same thing on the unit mover authoring, move speed. Then here in Unity, let's select the unit and make sure that it has a move speed. So there I go, reset to 0. Let's put it on 5. And again, play again. And yep, it still works. Okay, great. So now here on the unit mover, now we can add whatever extra data we want. Like for example, we can add the rotation speed. Like previously over here, we were using a local variable, but it makes more sense for that data, that value to be defined over here. So let's do a public float for the rotation speed. And again, let's also define it on the authoring component so we can pass it in. So our rotation speed equals, go inside the authoring component and grab the rotation speed. Then on the unit mover system, over here on this one, instead of using a local variable, instead of that, let's use the one that we get from the thing. So we get the quaternion local rotation, and then for the t, we've got time.time multiplied by, let's go inside the unit mover component. Let's read from it, so let's access the value RO, and we want the rotation speed. Okay, so now our component should have some more data. And if there's our component with rotation speed, let's put it a bit faster. Let's say 15, let's test. And yep, it is still rotating with the rotation speed. Okay, great. So this is working. Now all that's left is to deal with making sure that it only goes towards the mouse position and only on click. Now, technically, over here on the unit mover system, on this one, we could add that logic. So we could test over here if input.get mouse button down. So when the player left clicks, if so, we can say the target position equals the mouse over position. So technically, we could do this. We could write this directly over here, directly inside of the unit mover system. This would technically work, but then it would also become quite messy. One of the main goals of dots is for your systems to be focused on doing just one thing. So for this system, which is called the unit mover system, this one should really only be moving the unit. It should not care about giving unit orders. It should only move regardless of where that order, where that target position came from. So let's make sure this system stays focused on just that, just moving units, not on giving orders. For that, let's make another script that will basically handle the unit selection and giving them orders. And again, we have the same question we had a while ago. So do we make that a normal I system, or do we make it a mono behavior? Again, going back to general guidelines that I mentioned a while ago, basically how you should use normal mono behaviors when we have something that only happens rarely or is not performance critical, and only use dots when it's something that involves tons of units or requires tons of performance. In this case, for the unit selection, at most the player is going to be selecting their units, let's say 10 times per second. So it is not something that is going to run 60 times per second. The logic for unit selection is not performance critical. So for this one, let's make another regular mono behavior. So let's right click on the mono behaviors, create a brand new mono behavior script. And for this one, let's call it the unit selection manager. Also, as a personal rule, I decided to name all the mono behavior scripts, name them all manager. And then for the dot systems, name them all system. Again, not a requirement, just a nice convention that I find very useful to follow. Okay, so let's make a game object to run the script. So a new empty game object, give it the exact same name. Let's make sure to drag the script and reset the transform and open. Okay, so now here, let's make a normal update. So private void update, so the standard update. And now here, we do want to test for the right mouse click. And again, we're going to be using the input manager. So input get mouse button down, mouse button with an index of 1, that is the right mouse button. So again, here we're using the input manager, again, just for its simplicity, just because it is so simple to use. But later on, we can refactor this to use the input system. Okay, so here we've got a right mouse button click. And when that happens, let's grab the mouse worm position. So vector3 for mouse worm position. And we just go inside our mouse worm position class, access the static instance, and call get position. Okay, great. So with this, we have the mouse worm position. Now the goal is to tell our unit to move straight towards this point. So this is actually an excellent time to learn how we can interact with the dots world directly from the game object world. We already saw the opposite over here on the unit mover system. So this is an I system, this is a dot system. But on this one, we already managed to interact with a regular game object, a regular mono behavior. We just use a static instance in order to access it. Now in here, we want to do the opposite. We want to access the dots world from a mono behavior script. This one is going to be a little bit more complex. Basically, the goal here is to give the unit the target position, which means we want to find all the units, all the ones that have a unit mover component, and set their target position. So to do this, the first thing we do is create an empty query with all of the components that we want to find. So it's really the same thing that we have over here. We're doing an empty query for various components. So over here, let's query for that. However, we cannot use system.api if we do this query for, let's say, the unit mover. If we do this, nope, this does not work. It says you may not use system API outside of a system. Basically, this system API, this really useful class, this one can only be used inside of systems. So over here, since we are outside a system, we need to do something a little bit different. We need to manually create the query with another method. So what we can do construct a brand new entity query builder. Yep, this one right here. This is how we can build queries. Now this one takes in a parameter for an allocator. And a bit strangely enough, it is not exactly this type, or rather the type that we're going to use. The one that you should use is called allocator. It is this one right here, the one that exists inside unity.collections. Let's go ahead and use this one. Now allocators are very important. They are basically defining the lifetime for the memory that is going to be used by this object. It is very, very important that you choose the right allocator so you don't end up with memory leaks. Over here, the main ones you're going to be using are either persistent or temp. Now, for example, here, if you were to make it persistent, then Unity will reserve some memory for this object, and then it will keep that memory around until you manually dispose of it. So if you were to make something persistent and then you do not dispose of it, then over here we would be creating a new object, we would be instantiating new memory, doing that every single time we press the mouse button. That would essentially end up with a memory leak and the game would eventually crash. So if we were to use a persistent allocator, then we need to make sure to clear the memory. But we have other allocators, and the important one is over here, temp. This one is going to be the shortest one. This one is going to be automatically disposed at the end of the frame, so you don't need to manually dispose this one. In general, you should always pick the smallest allocation possible. It is more performant to make a temp allocation as opposed to a persistent allocation. So while technically over here we could use either one, we could make it persistent and then dispose of it, or alternatively we could make it persistent and then cache it inside a field. Both those options would work, but using the super simple temp, this one, like I said, is automatically deallocated. So in this case, where this code isn't insanely performance heavy, for this case using temp makes it work perfectly fine whilst being quite a bit simpler. So let's go ahead and use the temp allocator. Okay, with this we have created a new NT query builder. And now with this one we can do similar to what we did on the system API query. We can add the components that we want this query to include. So let's call the function with all to include all of the components that we want to include inside of this NT query. In this case, we only want to set the unit mover target, so let's just grab the unit mover. And if that's it, here we have a valid NT query builder, but like name implies, this one only builds an NT query. It is not an NT query itself. So after defining all the components that we want to use, afterwards, let's call the build function, and this is what will actually create the final NT query. And this one takes in a parameter for an NT manager. So this means we need to access the NT manager for our world. And the way we get that is actually quite simple. We can access the world class. This one exists inside unity.entities. And then inside that one, we have the default game object injection world. Basically, dots can have multiple worlds. This is how, for example, dots multiplayer works. You have a server world and a client world. So in advanced use case, you can create multiple worlds and do some really complex things. But by default, it is always going to have the default game object injection world. This is the world that we've been working on so far. When we constructed the new subscene inside of our hierarchy, all the objects over there that are going to be baked inside of this one world. So we can access this default world, and then inside of it, we can indeed access the NT manager. So let's grab the NT manager, just store it, NT manager, and it's exactly going to be that one. And then over here, we construct the query with all of our components. So we want the unit mover component, and we build an NT query, and this is going to be the NT query for our NT query. All right, yep, that's it. So here we have our final NT query that we want to use. Now all we need to do is really just cycle through it. Now there are two main methods for cycling through an NT query. If we go inside the NT query, inside we see the functions. There was one called toEntityArray. Like name implies, this one will create an array containing all of the entities that match this query. It will have the objects of type entity itself. Or alternatively, the other one we have is toComponentDataArray. This one will return an array containing references to a specific data component. By the way, both of them, both this one and the toEntityArray, both these will return the same size. The NT query does not change. So this means that we can actually cycle through one of these arrays, and using the same index, we can either access the entity or we can access the component data. So if you had a query with multiple component types, and then you want to cycle through those multiple component types, you would just call this function multiple times for each component type you want, and then again, everything will be on the exact same index. Now in this case, we really just want to update the target position on our component. So let's use toComponentDataArray and grab the unit mover. Yep, just like this. Although one very important thing here, make sure you're using this function toComponentDataArray, not the other one. There's also this one, toComponentArray. This is not the one you want to use. This one is meant for working with classes and returns a normal array. The one that you want to use is this one, toComponentDataArray, which returns a native array, and this one does work with iComponent. So don't make this mistake, make sure you use the correct function. And yep, so this one is going to return a native array of our component type, so native array of our unit mover component. So let's call it the unit mover array. And since this one is going to construct an array, because that we need to actually input the parameter. And again, it's going to be our allocator. So again, same thing that I said a while ago. You can use whatever allocator you want, but in most cases, you probably want to use temp. Okay, so yep, so this is going to return an array that contains all of our unit mover components. And again, note how it is not a regular array, so it's not a unit mover array like this. Nope, instead we have a native array. Now this is a type that exists inside the unity.collections namespace. This is similar to the normal C# array, but this one is made specifically to work with dots and burst, whereas normal C# arrays, those are objects, so you cannot use those inside a burst. You can use native arrays directly in there. Okay, so with this we have our unit mover array. Now this is going to work just like a normal array, so let's do a cycle through it. Let's do a for int I equals 0, while I under the unit mover array.length, I++. And the reason why I'm using a for instead of a for each is just in case in the future we want to use that index to go through either the empty array or some other component. So okay, so with this, now we can grab that component. So we can grab that one on this index, and that is going to be a unit mover. Yep, here we are reading the component. And now let's just tell this unit to go towards this position. So that means we also need to refactor our unit mover component. We need to have some kind of target position. So let's make another field, make it a float3, since this is a position for our target position. And float3 exists inside of the unity.mathematics. So let's go ahead and use this one. In this case, we don't need to add it to the authoring component. This one is going to be set manually through code. And then over here on the unit mover system, instead of defining this target position, instead of that, let's just go inside the unit mover component, read it, and read the target position. So yep, now this unit should be moving towards this target position. And over here, back in our selection manager, on this one, we can just go inside the unit mover, set the target position, and set it to the mouse wheel position. All right, yep, like this. Let's go ahead and test. But before you do, I want you to pause the video right now and ask yourself, will this work? Will the unit actually go towards the mouse wheel position when we right click? Just pause the video and think about it for a second. Okay, so let me just save all the files to make sure they all compile. Let's wait for compilation to finish. And now let's test. So let's hit on play. Okay, the unit is going to 0, 0. Let's just ignore the rotation. Now I right click and nope, nothing happened. Target position is not changing. I can inspect the unit and go over there onto the runtime mode. And we can find our custom unit mover component. There it is, and yep, target position is on 0, 0, 0. So even as I right click, nope, it does not change. So the problem is right here. I wonder if you managed to notice exactly what the problem was. So the issue is, once again, here we are working with structs and not classes. It's a whole thing about value versus reference types. Here, when setting the target position, when we do this, we are just modifying this copy. We are modifying the copy stored in the array, and note how this is not a value RW. So like here on the move system, the reason why we can modify the fields inside of it directly, like for example here, the local transform modifying the rotation, the reason why this works is because we are using this special type, the ref RW. But over here on this code, we just have the normal unit mover type. This is not a reference to anything. So over here, we are just getting a copy. By modifying this one, we are just modifying the copy and not actually modifying the data that is stored in the entity. So this is why the unit was moving, this is why it wasn't updating. If we do want it to update, then we need to modify it, and after we modify it, we need to save that data back onto the entity. So one way to do that is to access the entity manager. So let's access that one, the entity manager, and then we call the function setComponentData. This one takes in an entity, so let's actually get the entity as well. So let's go inside the entity query, and inside that one, let's call toEntityArray. Once again, let's use the allocator.temp. This one is going to return a native array of entity for our entity array. And now with this one, like I said, it's on the same index. So in order to update the component on this same entity, let's access the entity array on the same index, and we're going to set it to this new unit mover component. So here we grab the unit mover, we are grabbing just a copy, then we are updating the target position just on that copy, and finally over here we are actually updating the value directly stored on the entity. So yep, like this, let's save. And over here, the game is playing, I right click, and yep, now it does work. Right click, and yep, down there we can see the target position. That one is indeed updating as I right click. Okay, great. So as always remember how when working with structs, you are usually dealing with the copy and not the original data. So if you do something like this without using the special refRW type, without that, you are likely working with a copy. So if something does not change, if something does not happen as you intended to, always think about this because this is probably the problem. It is probably because you are modifying a copy and not the original position in memory. Okay, so this code is working, but let me also cover one sneaky issue here. So here we are reading the component and then we are updating it. But technically, we could remove this. We could get rid of this and then over here just create a brand new unit mover component and inside set the target position equals our mouse wheel position. So yep, this technically looks like it should work, and it should also be faster because we are not spending any time reading the component. We're just cycling through it and just setting it to new target position. However, let's see, does this actually work? Let's test. So here we are, and I right click, and nope, it does not work. Or rather, actually it did work. If we inspect the unit, if we scroll down and we look inside the component, yep, it did update the target position. So if I right click, you can see that one is indeed updating correctly. However, the issue is that while the target position is being correctly set, over there the move speed and the rotation speed, those are being left on 0. This is yet another very important thing you always need to keep in mind. So over here, when we construct a new instance of this type, like this, we only gave it a value for the target position. We did not explicitly assign a value to the move speed or the rotation speed, and if we don't do that, then those fields are simply going to default to 0. So that's what happened here. This is another thing you always need to remember, always need to be aware of. If you only want to update a single thing inside a component, if so, then instead of constructing a brand new component, instead of that, you should do what we were doing a while ago. So you should first read, then update, and then update the data. So first here we are reading, we are updating the copy, and then we are saving that copy directly onto the end. This way you can modify just one field and it's going to keep whatever other data is inside of this component. Also, just one more note here. So this code is working, it updates the target position and does save it on the entity. In this case, this is perfectly fine since this code is not going to run constantly. This is only going to run whenever we right click on our mouse. But technically, over here, we are writing to our component for every single entity, meaning if we have 100 units selected, we are going to call this function setComponentData 100 times. Like I said, in this case, it's perfectly fine because this code is going to run pretty regularly. But if you really want maximum performance, if so, then another alternative to this is we can cycle through the unit mover array. We can update it with new target position, and then over here, we do not set the component data. Instead, we just save the new unit mover directly on the array. Again, we need to save it back, otherwise we are just working with the copy. So we are updating the data that is stored inside of this array, but by itself, this will not update the entity. This is just modifying this local array. But if we do this, which is going to be pretty fast, after this, we can go inside the entity query, and inside this one, there's a really nice function called copy from component data array. This one takes in a native array, so we can pass in our unit mover array. And yep, just like this function over here, this will basically update the data on all of the components that match this entity query. So instead of doing one write instruction per each entity, instead of that, we update all of the data inside of this array. And then at the end, after doing all of that, we do pretty much just one write instruction. And just that one is going to update all the entities with all the data inside of this array. So now if we test, everything should still work the same. So here we are, and I right click, and yep, it does change position, it does move, everything works perfectly fine. Alright, awesome. Now, just for fun, let's duplicate our unit and test with a whole bunch of them. So here, let's just manually duplicate them a bunch of times. Let me select the unit. So just put on over there, and so on. By the way, this is really just a temporary test, so that is why I'm not bothering to make this unit into a prefab just yet. We're just doing a simple test. Okay, so with this, I have a bunch of units. Let's hit on play. And if there they are moving, and I right click, and yep, they all go there, they all go up there, down there, and so on. They are all following the target position, so I can give orders to all of my units. Again, that's the whole thing about dots. It applies the same logic to all the entities that match the query, regardless of how many entities you have. All the ones that have that query are currently getting the target position assigned, so they all go towards there. So yep, with this, everything is working great. Now, if we leave them on a target position, they still get a little bit messed up. That is because of the physics. They're constantly trying to go to the exact same position, so things get a little bit messy. We're going to solve that later on when we implement some stopping logic and multiple move positions and collision avoidance and so on. We're going to handle all of that in the future, but so far everything is working pretty great. We can click and all the units go exactly where they're supposed to. And in this lecture, we also learned the very important concept of how not everything has to be dots based. You can make some dot systems and you can make some monobehavior systems. Everything works fine. We also learned how to interact with the dots world from the normal monobehavior world. So we've already learned quite a lot over here. Let's just remove these testing units. Okay, they are working fine. All right, let's just leave it with one. And right now, our game, our basic logic, all of this is working good. But so far, we're only been using the main thread. So we're not yet taking advantage of all of the massive power that dots brings. Now that the move code is fully working, now let's learn how to use the job system and bursts in order to make this move code insanely fast. So let's learn how to do all of that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to create a job and use bursts so our movement code is insanely fast. We're going to look at the results before and after to see the really massive difference that it makes. Okay, so here we have our unit. I can right click and tell it to go to some position. So yep, everything does work. And here we have our unit mover system. So all of our logic is over here on update. We're doing a simple for each cycling through the query, meaning that all of this code, all of this is running just on the main thread. So for example, if we have a CPU with 16 cores, then 15 of them are going to be completely idle, doing nothing, just wasting time. Only one of them is actually going to be working. Ideally, we don't want that. Ideally, we want all the cores in the entire CPU to be doing some work, so our game is as performant as possible. Now, in order to write multi-threaded code, we could use normal C# code, we could manually create threads and give them tasks, but like I said on the lecture on What is Not, writing good native multi-thread code is extremely difficult and it is very easy to make all kinds of mistakes. So thankfully, Unity has created the job system, which makes that process much easier. So let's see, how do we create a job? Now, first thing we do is define a struct, and we can define it anywhere, but it makes sense to define it next to the system where we're going to use the job. So here on the exact same file, let's define it. Although if this were a job that would be used in multiple places, then we would probably define it in a proper file. But this unit mover job, this will only be used over here by unit mover system, so it makes perfect sense to define it right here. Okay, so let's define a struct, so that's the first thing. Then jobs are also going to have some source generation, so let's make sure to define it as a partial struct. Then we use a name, let's call it unit mover job. Personally, I like to append job to the name, but again, not a requirement. And now finally, we implement an iJob interface. Now you can just write iJob and you can see all kinds of interfaces you have. These are all going to run slightly different. Remember how I said that all of the components that make up dots do not have to be used together all at once. So you can write multi-threaded code with the job system without using entities at all. In those scenarios when not using entities, when just doing some random normal multi-threaded code, for that you'd use either iJob or iJob4. Those are the two main ones. But when working with entities, for that we have the super useful iJob entity. This one is going to be really easy to use. Technically, we also have iJob chunk. This one is also related to entities, but this one is for more advanced use cases. It is more performant, but requires you to do a little bit more setup. Whereas the iJob entity, this one runs super fast and is really easy to use. So let's use this one, iJob entity. Let's go ahead. Now for this to work, we really just need to write a void execute function. So just like this, and now in this function, on the parameters, over here we include whatever components we're going to need. So let's copy exactly the same query that we have up here. So we need the local transform, the unit mover, and the physics velocity. So let's add those. So local transform. Then we have the unit mover, and finally the physics velocity. Okay, that's our three components. And now here we also need the same thing that we define up here. We need to define them as either read-write or read-only. However, down here on the job, this one uses a different syntax. Although actually, technically, you can use the same syntax, so you can use refrw. Technically, you can use this, but the Unity docs, they recommend something a little bit similar. So instead of using that, if we want to make something as read-write, for that, we write the ref keyword. This is the ref C# keyword. This one basically means that this field won't be received as a reference. And since it is received as a reference, even though this is a struct, it means we can write to it. And then if we want something as read-only, like for example the unit mover, we only want to read this one. For that, we use the in keyword. So yep, ref for the local transform, so we can modify it. In for the unit mover for read-only. And for the velocity, we want to write to it, so let's make it as ref. Okay, yep, just like this. Again, technically, you can use refrw and refro and it will work, but the docs recommend this syntax instead. So like this, we have defined our execute method. And basically, when we set the job to run, it will automatically create a query with all of these components. It will do all of that just like the system API up here, and will run the execute for each entity that matches that query. So now our goal here is to do literally the exact same logic. So let's just copy the same code. So just copy down here, paste it. And the only difference is over here, we don't have the refrw or refro, so we don't go through the value ro. Instead, we just modify it directly. So just get rid of this, get rid of this one, this one, this one, this one, this one, and this one. Okay, so yep, so here we have exactly the same code. And the other difference is what we see here, we have an error. And this is actually the general limitations that exist inside of jobs, meaning that jobs mostly have to be self-contained, meaning they cannot access data outside of it. Now technically you can pass in an array and then access different positions in memory and something like that. But in general, jobs are self-contained, meaning they need to have all the data that they need in order to execute their function. Now this limitation of jobs being mostly self-contained, this limitation is actually what helps write super fast multi-threaded code without causing all kinds of chaos. If the job only works on data that the job has, then it's super easy to make it run parallel in multiple cores at once. So the error that we have here is because we cannot access the time.time from here, And the way we solve this is super simple. We basically just define a field on job. So up here, let's just define a public float delta time. So just a perfectly normal field. And then down here, instead of going through system API, we just use that field. So yep, that's it. No more errors. So now basically when we construct our job, we simply need to assign the delta time and everything will work perfectly. So let's actually do just that. So up here on the on update, let's construct a brand new job. So a unit mover job. Let's call it unit mover job and construct a brand new unit mover job. And now inside of it for the delta time, over here we can indeed access system API.time.delta time. And yep, so that's our job all set up. Let's make sure to comment out the other random query code. Okay. So up here we have defined our job. Now all we need to do is really just run it. And we actually have multiple ways of doing that. Now the most straightforward one is go for the unit mover job and just call run. Now this one will run the job directly on the main thread. So this kind of was the main point behind jobs. You should probably only use this one just for testing or debugging. Essentially, this will end up pretty much the same thing as we had previously. The main goal of jobs is to make multi-threaded code. So usually the one that you want to use is the one that is called schedule parallel. This one will schedule the job to run on all the entities that match the query in parallel. Meaning if you have lots of entities, it will run the job on multiple threads at once, and each entity will be responsible for updating a few entities. Although quick note, just something to keep in mind, which is actually something that I only learned after doing a bunch of research. This one, schedule parallel, this will split the logic in multiple jobs based on the number of entities. So this is really perfect if you have tons of entities doing some logic, but if you have just a handful of entities, so if you don't have many but you have a complex job, if so, they are likely all going to run on the same thread because you don't have enough entities to split it. So just keep that in mind, that's how the job system works. If you have some really super complex logic, but you're only running it on a handful of entities, if so, then this will basically run just on one thread. So in that case, you probably want to split the logic into multiple jobs yourself. Okay, so just with this, we can test and see that it works. So here's our job, we construct it, we schedule it, and let's comment out the rest. Okay, let's save. And over here, let's hit on play and try to move the entity. And yep, everything still works perfectly. All right, great. So the unit is still moving exactly the same, except now it is moving using a really nice job. By the way, what we just did here is actually what we're going to do a lot throughout this course and what you should probably do when building any kind of new system. First, make it work just with the normal for each, just with normal main thread code. First, get it working like that. And then once you have that logic working, then you refactor it into a super fast job. Okay, so this is working. However, we still have one thing missing. We're currently not using burst. Now, adding burst is thankfully super simple. All we need to do is up here on the job itself, let's add the attribute burst compile. And yep, that's it. That is literally it. Just by doing this, our job will now run with burst enabled, which is going to make it insanely fast. So let's save and let's test. Just also here in the entity, make sure you go into the menu, burst, and make sure that compilation is enabled. If you disable it, then even if it has that attribute, it will not use burst. So make sure this is enabled. Let's test. And there you go. Everything still works fine. Now let's actually see the difference that all of this makes in real terms. Now this code that we have here, this one is really simple. So it is going to run insanely fast no matter what. So it's actually a little bit tricky to see the results, just because again, everything is going to be insanely fast. For a test, I'm going to duplicate this unit a ton of times. And before I do, let me just get rid of the capsule collider. Just because right now we really only want to test our movement code, not any physics system. Just make sure that it's still working, and yep, it still moves. Okay, great. So now I'm going to duplicate this into a ton of units. Okay, so here I duplicated 10,000 entities. Now my Unity editor is a little bit slow, so to make it a little bit faster, let's use the power of dots. Let's close the subscene for editing. And again, now everything is being baked into super fast binary data. So yep, now there it is, and now the Unity editor is working a little bit faster. And we can verify that we have 10,000 entities. So let's hit on play, and down there we can see, yep, the unit mover system is working on 10,000 entities. Okay, great. Now over here in our code, let's make it run the slowest possible. Let's use the normal for each without jobs. So let's actually comment out this one right here, comment out the job, and let's uncomment out the for each. Okay, so we're going to use the normal code. Let's save this. So we are not using jobs, and also let's go up here and make sure to not use burst. Okay, now for seeing how fast it goes, let's go into window, then go into analysis, open up the profiler. So here it is. Now I'm going to hit on play and capture a certain frame. So they're all moving, capture a frame. Okay, here it is. And let's see how fast it is. And yep, here we have our unit mover system in total running on 10,000 entities, and it is taking 9.13 milliseconds. Okay, that's great. And right now it is not multi-threaded. So we can see down here, all of these threads, all of these jobs, all of them are empty. So this is where we can see all of the threads that I have on my PC. All of these are completely idle, just wasting a ton of time, whereas only the main thread, that's the only one that's actually running this logic. So this is normal C# code just running on the main thread, okay? Now back in code here, now let's enable jobs. So let's go ahead, comment out the system, and let's enable our job like this. So let's see with this. Although here, let's also make sure burst is disabled. Okay, burst disabled, just using jobs. Let's play. And now let me move them and select a certain job. Okay, so here's a frame, and now gotta zoom in order to actually find it. And yep, it is actually right here. I had to zoom into the maximum in order to find it. Like I said, the code is super fast, so even though we have 10,000 entities, right now it is running on 0.01 milliseconds, as opposed to the 9 milliseconds we had previously. Now over here, we can see our jobs. So we can see all of our worker threads, and we can see all of them. Yep, the code is being split across all of these threads, and all of them running at the exact same time. So because of that, previously we were taking 9.1 milliseconds, whereas now if we add them all together, 30 instances over 30 threads, in total it is taking 8.3 milliseconds, but in reality it's just taking 0.3 milliseconds. Because again, all of this is all working at the exact same time. So as opposed to having just one thread and running all the logic for unit A and then unit B, instead of that, both threads are working at the exact same time, so within the same amount of time, they are running twice the amount of work. So right away, you can see the huge improvement you get with multi-threaded code. By taking advantage of all the cores in the CPU, your code can become massively faster. Like, it's not literally just 2 times faster or 3 times faster, but literally over 10 or actually over 20 times faster, from 9 milliseconds to 0.3 milliseconds. And now for the final piece of the puzzle, let's enable burst. So over here, we create the job, and over here, we make sure we add burst compile. Then in Unity, let's go into jobs and enable burst compilation. Okay, that's it. Let's hit on play again. And now let's find what, and you can already see over there in the graph how quickly it moved. Now I need to zoom all the way out and then all the way back in. Okay, and let's see if I can find where it is. Okay, I found it. So right here for scheduling the job, this one is pretty much as fast as it was a while ago, which is pretty much instant. So scheduling the job just takes 0.014 millisecond. Again, keep in mind these are milliseconds, not seconds. It is taking 0.01 milliseconds. So with burst enabled, scheduling a job is pretty much instant. Now let's see if I can find exactly where the job is being executed. And yep, it's actually over here. And yep, here is the job, and we can see all of them running in parallel. And by adding burst, we got yet another 10x performance improvement. With just the job system, it was taking 0.29 milliseconds, and now in burst, it is taking 0.035 milliseconds. Like it says here, the total amount of time is 0.84, so that's the total amount of time, but since it is running in parallel, the whole thing runs in 0.03 milliseconds. By the way, the green color over here, that's how you can easily see which things are using burst and which are not. Green means burst. So here you see the insane power of dots. Honestly, no matter how many times I see it, I can't help but be impressed. As long as you follow the data-oriented design and you keep in mind some limitations, as long as you do that, your exact same code can run multiple times faster. And again, it's not just 10%, 20% faster, or even 100%. No, it is 10,000% faster. It really is insanely impressive. Watching these results always impresses me. So originally, our code running on a single thread, that one was taking 9.13 milliseconds. Then we added multi-threading with the job system, and we got it down all the way down to 0.29 milliseconds. And then finally, we enabled burst, and in the end, the exact same code runs in 0.035 milliseconds. So we went from 9 milliseconds to 0.03. I don't even know how many percent that is faster, but it is something like 300 times faster, again, for the exact same code doing the exact same logic. And again, what I mentioned a while ago, what we did here is what we're going to do throughout this course and what you should do. Meaning, get your logic running just on the main thread, just using a for each system query, get it working, then refactor it to use a job system, apply burst, make it schedule as parallel, do all of that, and all of your code will run insanely fast. Okay, so yep, everything worked. Let's just clean up our testing scene. And by the way, here we can see all the units. Really nice to see 10,000 units, all of them moving for the same place. Okay, great. So now let's clean up this test. We really don't need 10,000 units just yet. So I'm opening up the subscene, gonna select all of them and get rid of all the units except for one. And yep, we're back to having a single solitary unit. Press on play, and yep, everything still works perfect. Let's just make sure we remember to re-add the capsule collider. So the capsule collider, let's put it on a Y of 1.1, radius of 0.5, okay, and height of 2. Okay, our unit is back. Now, just before we end this lecture, let's do just one tiny thing. Let's add some simple stopping logic. So right now, if I hit on play, you can see the unit gets a little bit bugged. That is because it is constantly trying to go to the position 0, 0, but the unit is already on there, so it gets all messed up. Thankfully, adding some stopping logic is actually quite simple. So over here in our job, we are calculating the move direction, so the target position minus the current position. And now, before we normalize this vector, before we do that, then this vector actually has a size. It actually has a length. So we can grab the move direction.length, although actually it's not done like this. We go math, we use math.length, and we have either length or length square. This is actually an important thing, and it's yet another performance thing. Basically, the way the actual value, the actual length is calculated, by doing that is first by calculating the length square, and then by doing a square root on that value to get the final length. Now, doing a square root, that is a relatively expensive process, so if you don't absolutely need the actual value, then really just use a square. In this case, we don't really care, we just want to compare if it is close enough, so we can just test for a squared value. So let's use this one, that is super fast, so we get the length of the move direction. And then really just want to check if it has reached the target position, so let's define a float for a reached target distance squared, and let's put it at something like 2 units. Then we simply do an if the length of this vector, if it is under this amount, then we have reached the target position. And if we have reached, then we simply just want to stop moving, and the way that we do that is super simple. We just set the linear velocity back into 0. So for this one, float 3.0. We set it to that, and of course we stop executing, so let's add over here a nice return. Okay, so yep, that's it. The unit should now be stopping, so let's test. And here we are, and right away we don't see that bug. If I click to move, go there, and yep, it does stop as it gets within a certain distance. Okay, great. Alright, so here we'll learn how to convert a normal main-threaded system into a super performant multi-threaded burst compiled system. This makes our movement code super efficient, but so far we have no control over which units we want to control. Right now we're just using the same unit or all the units at the same time. So let's handle a way to select our units individually, and let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to select our units so we can choose who we give orders to. We're going to use what is called an enableable component, which will let us toggle it on or off depending on the state, and depending on that state, we are going to give orders to those selected units. Okay, so far, all our logic for moving the unit works. I've got just one unit here, I can click, and yep, the unit does go towards the target position. It goes there perfectly. It works with one unit and also works with multiple units. All of them go towards the target position. Now, before we make some duplicates again, it's probably time to make this unit into a prefab. So first of all, let's keep things nice and organized. Let's make a new prefabs folder called prefabs. Let's drag the unit on there, okay. And also let's select the unit, and over here for the collider, let's actually make it a trigger, just to make it so that we don't have any issues with collisions right now. Again, like I mentioned, we're going to add collision avoidance and some proper move positions later on, but for now, let's just enable this so we don't have any issues. And make sure you make this a trigger directly over here on the prefab, so it should apply to all units and not just this one unit, okay? Now we can duplicate them, so let's duplicate a bunch of them, position them a bit like this, just having a bunch of different units, okay, great. And if we test, yep, they're also moving, click, and yep, all of them go towards the target position. Okay, great. But that's actually a problem. All of them are moving. Now in an RTS game, you really want the player to be able to control which units to move instead of just moving all of them all the time. So we need some way to tag some units as being either selected or deselected. Then when giving the move order, when doing that, we can make sure to only give those move orders to the units that are actually selected. Now when it comes to tagging units, we have multiple options. The first one is with a simple component tag. Let's create one just to see how that works. So in our authoring scripts folder, let's go ahead create. And by the way, for making a new authoring component, we can create a mono behavior script and go through that whole writing process, or we can go over here into entities, and this one already has a Baker script. So let's see this one, just see what this template has. Let's call this the selected authoring. Okay, let's open and see. And yep, this is what it creates by default. So it creates a mono behavior class and then creates a Baker class that implements Baker and the bake method. Now, honestly, personally, I still prefer the format that I have over here. I think this one makes it look a little bit cleaner. So I've got the authoring class, it has the public, everything looks nice and proper. We've got the Baker class inside of it, and then the component down here. So technically you can use this template if you want, but me personally, I prefer this format over here. So I'm going to basically follow this. So over here on this one, first of all, I like to be explicit, so let's make it as public. Then we've got the mono behavior. Then inside we've got the Baker class. I like to call this one just Baker and make it public. Okay, so yeah, but again, personal preference. Personally, I prefer this format. Okay, so now let's make our actual component. Let's make the usual thing. So this one needs to be a struct. Then for the name, let's call it selected. And then we implement iComponentData. And that's it. That's all it takes. Here we have just a tag component. meaning it's a normal component, a normal iComponent data, and it simply does not have any fields at all. It really just exists so it can be used to tag objects. Then over here on the bake, we really just add it. So let's grab the entity, let's call get entity, and for the transform usage flags, let's default to using dynamic, okay? Then we call add component. We're going to add a component onto this entity, and it's going to be a new selected component. Yep, that's it, super simple. We've got our authoring component, we've got the baker, and we just add our component, which does not have any fields, so this one is just a tag component. Let's go ahead and save this. And now let's add that component to the unit. And also, again, make sure you select the prefab so that it applies to all units. So don't add it to just one of these units. Let's add it to the prefab itself. So over here, let's drag the select authoring component. Yep, just like that. And just like this, we can already see what that does. So let's select one of the units inside of our subscene. This one, yep, does have the select authoring. And on the inspector, let's swap it into runtime mode. And yep, right here up top here, we have a section for tags. And we can see, yep, here we do have our selected tag. Okay, great. So this is how tags work. Tags are really just empty components. They don't have any extra data, and they show up over here on this special section. So this is one way we could handle the selected logic. And basically for selecting units, we would add this component. Then for deselecting, we would simply remove this component. Now, technically that would work. However, adding and removing components is what is known in dots as a structural change, and that is something you should actually avoid as much as possible because it is a quite expensive operation. Basically, the way dots works in the background is it creates what are known as entity archetypes. So an archetype is a unique identifier for all the entities in a world that have the same unique combination of component types. So for example, all entities in a world that have component types A and B, those share the same archetype. And then entities that have components A, B, and C, those have a different archetype. This is a really important thing to know. Dots in the background does a lot of work to place all of those entities of the same archetype together in memory. Again, that's how it works so fast. But since the archetypes are based on a specific set of components, because of that, if you add or remove a component, you are going to be changing the archetype. And doing that, like I said, is what is known as a structural change. And like it says here, moving entities between archetypes, that is a resource-intensive operation and reduces the performance of your application. Essentially, when you do a structural change, like for example, you have types A, B, and C, and you remove the C, when you do that, then whatever entities used to have A, B, and C now just have A and B. So now those entities need to be copied onto the entity archetypes that have A and B. Basically, doing a structural change requires lots of moving things about in memory in the background. This is a resource-intensive operation, so you should avoid using it as much as possible. So for this particular scenario, since we're going to be selecting and deselecting units quite a bit, for that, instead of adding or removing a component, which again would trigger a structural change, instead of that, we're going to be using something really awesome called enableable components. This is basically a component just like this, except it's as if it has just a boolean inside of it that defines whether it's enabled or not. But unlike just storing a regular bool inside one of these components, unlike that, if you have an enableable component, those can be used in many special ways without having to read the entire component data. Now, the way we make something as an enableable component is super simple. We literally just implement another interface. It's called enableable component. And if that's it, we don't need to add any extra data. Just by adding this, it will already work. So let's go ahead and save. Let's wait for it to compile and then look at the entity. And yep, there it is. There's our selected component. And now you can see it does have a nice checkbox. This checkbox lets us easily either enable or disable this component. And since the whole thing we're doing here is just flipping a Boolean bit, we are not adding or removing components. So because of that, setting this to either selected or deselected will not trigger a costly structural change. Okay, so we have our nice enableable component. Now let's see how this actually works inside a query. So let's create a simple testing system just to test out some things. So inside the systems folder, let's right click, go inside the entities and create new iSystem. Called just testing system. Okay, so now here, let's get rid of the create and destroy. We don't need those. Okay, so now on the update, on this one, let's go inside the unit mover and let's basically just copy the for each that we had here, just to copy basically that query. So let's copy and paste it over here. Okay, everything worked. Again, if you're seeing some errors, it's probably because your Visual Studio did not automatically write the using statements. So make sure those are all there and this works. Okay, great. Except here, we don't want to do any of this logic. Instead, let's just count the number of units that this query applies to. So let's do an int unit count. Let's default it to 0. Then on the for each, let's increase it ++. And finally, do a debug.log. And let's print out the unit count as something. And by the way, this is actually an error that happens every once in a while. Basically, when I wrote debug, instead of implementing Unity Engine, for some reason, Visual Studio is defaulting to importing this class, system.diagnostics. That is not the one that we want. We want the debug class that is inside using Unity Engine. Kind of like that, and we have the normal debug log. Okay, so let's run this and see how many units have all of these components. It should be the same number of units. And yep, here in the log we can see we have 8 entities that match those components. And looking here we can see, okay, we have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, great, everything is correct. Now let's include our enableable component inside of this query. So one way to do that is to literally include it in the query. So over here, let's add another component. We're going to go with ref ro, and let's choose the selected component. Then let's also add it up here for the selected. Okay, yep, like this, let's test. And again, this burst error is normal. That is because we are doing a log on that value. But again, it's just a burst error, so let's ignore it and play. And yep, it still says the exact same thing. By default, the component is going to be enabled, so it makes sense that it still says the same number. Although actually, we can modify this. So over here, we can add the new select component, but if we wanted them to default to being not selected, for that, over here, we can call set component enabled. This one pass in the entity, so our entity, and then let's set it as false. And for passing in the component type, we just need to use generics, so pass in the selected component and set it as false. So let's save. And yep, now they show 0 units. And if I select one of those units, and over here on the inspector, make it in runtime, and we can see over here it's selected, and we can manually toggle this box. And as I toggle, yep, there you go, that one goes to 1, toggle again, and goes down to 0. So yep, that works. And again, remember, one very important thing is how whether this one is toggled or untoggled, the entity still has this component. It still belongs to the exact same archetype, except now this component is simply marked as either enabled or disabled. And by seeing the number 0 here, we're actually already seeing another interesting thing. Over here in our query, we're querying for everything that has a selected component, but note how if it is disabled, this one actually says 0. That is because this query over here, when we query for something with a select component or any enableable component, when we do that, that entity is only included within this query if that component both exists and is enabled. So if the component is disabled, this code will not run for that entity. It needs to be present and needs to be enabled. Alternatively, if you wanted to query for entities that have a enableable component but have it disabled, if so, then instead of this, let's get rid of that one and this one right here. Okay, back to what we had previously. Now we can add the option with disabled and pass in the component, so selected. So yep, let's select this. And yep, there it is, 8. Now that query is only included entities that have that component disabled, and right now by default all of them are disabled. If I set this one as enabled, there you go, now it says 7. So like this query will only apply to entities that have the component and have it disabled. If it does not have the component or the component is enabled, if so, then it does not run this logic. And yet another thing we can do is simply query if the component exists on the entity. So for that, we can use with present. Let's see. And yep, there you go. Now it is saying 8. And if I go into one of these and I set it as selected, yep, it still says 8. So the entities are being included within this query, regardless of the state of the actual component. Enabled or disabled does not matter. As long as the component exists on the entity, it is included within this query. So these are the various options that we have for dealing with enableable components. As we go on in this course, we are going to use quite a lot of these options. So now that we can actually select the units, now let's actually use that selection logic within our move logic. Now, thankfully, like we saw, it's actually super simple. Let's just go over here on our testing system and comment this out. Let's leave the file created just in case we need to do some more testing in the future. And now let's go over here onto the unit selection manager. This is the code where we are giving orders to our units. And over here for the query that we are constructing, we are just looking for the unit mover component. So in order to be able to give orders just to select the units, that's super simple. Just add a comma and let's also include the select component. And again, like we saw by default, this query will only include entities that have that component enabled. So that's exactly what we want. And just like this, without modifying anything else, it should already be working. This query will only include entities that have both a unit mover and a selected enable. So then all the logic over here just runs within those entities that match that query. So let's test. Okay, here we have our units. And if I right click, and nope, not a single one of them moves. Okay, that's great. That's exactly as intended. Now if I select just one of them, let's say select this one, and over here on the inspector, I'm going to manually set it as selected. And now I right click, and if there you go, now just that one unit moves. Just one that is selected, that is the only one moving. Now if I go select a different unit, now mark this one as selected, and click, and if there you go, now both selected units are now moving. Alright, awesome! So our basic selection logic is really working. We can toggle this select component, and depending on that, we are moving whatever units we want to move. Now in the next two lectures, we're going to make it selectable with a mouse, instead of manually clicking over here on the inspector. But for now, this is looking good, it's working. So let's just add a visual to it. For that, let's go into our unit. And again, let's make sure we work inside the prefab so it applies to all of them. So let's double click on this prefab, go inside of it. And now let's right click on the unit. Let's create an empty child game object, call this the selected, and now let's apply a visual. So here we actually have two options. So the simplest one is to add a sprite renderer. And by default, let's select this circle sprite. So there it is right there. Let's just rotate it to face upwards and make it a little bit bigger. Okay, something like this. Now let's go ahead and save the prefab. Let's just increase it on the Y by a little bit, like 0.1, just so it doesn't collide with the floor. Let's go ahead and save the prefab. And yep, all the units have that. Press on play, and yep, they all still work perfectly. So this seems like it's working. Our sprites are being rendered. However, it is not actually being rendered by dots. Like I mentioned in the first few lectures, only a few built-in components are automatically supported by dots. Mesh rendering works, so our meshes over here, those are being rendered by dots. Physics also works, that one is also running on dots. However, for rendering sprites, if we actually select one of these objects, so let's select this select game object, and we'll look over here for the components, and we see these strange components. Companion link, companion transform. Basically, this is what happens if you bake an entity with some component that isn't yet supported by dots. It creates all of these companion components, and what these do is essentially the game keeps both the game object and the entity both alive at the exact same time. The entity will simply drive the game object behavior. So this is working, but it's just not as efficient since we are basically back to using game objects. We have an entity, but the entity is linked to a game object. Now in this case, our solution is actually pretty easy. All we want is really just to render a sprite. So instead of using the sprite render component, instead we can just use a mesh render. So let's go back inside our prefab unit, and for the selected, instead of using a sprite render, get rid of this one. Let's add the simple, the mesh filter, and the mesh render. Then for the mesh, let's choose a default quad mesh. And for the material, let's go inside the materials folder. And up here is the select material. Let's go ahead and select it. And yep, there you go. Right away, it does work. The only thing is, I believe this one is pointing downwards. Yep, so let's just flip it over. So make sure that over here on the rotation, yep, let's put it 90 on the X, put it 0.1 on the Y, and for the scale, let's make it a little bit smaller, so let's say on 2. And yep, that's it. Now, since we're using a mesh filter and mesh render, which again, they work with dots, because of that, this will be using the super fast dots renderer, just like all our other meshes. So let's go ahead, save the prefab, go back outside, and yep, there it is, all our units with all rendering being done, and we can select the selected, and yep, it does not have any of the companion components, it has the normal rendering components. Okay, so with this we have added a visual. Now let's show or hide it depending on whether the unit is selected or not. And this is actually an interesting problem to solve. Our visual is over here, it is a child object, meaning it's actually attached to a different entity than the one that has the selected component. So as we are doing our query for the selected component, we are going to cycle through just this parent entity. It is not going to cycle through the child one that has the visual. So as we select or deselect, in order to update the visual, we basically need a reference to that visual entity from the parent entity. Now thankfully, this is actually pretty simple to do. We can go here on the select component, and directly on the component, let's set a new field. Let's make it of type entity, and let's name it the visual entity. Yep, just like this. So now the question is, how exactly do we get that reference? And the answer is simply through the baking system. However, if we were to just add an entity field directly up there, if we do this, if we save, if we look over here in the editor for the selecting, nope, it does not have that field. If we make something of type entity, it does not show up over here in the inspector. However, if instead of making an entity, let's make this of type game object, called the visual game object. If we do this, yep, now it does show up a normal game object field. So now we can assign it. And again, make sure you're working inside the prefab. So let's open, go inside the prefab. And over here, now we can just click and drag the select game object. And yep, that works. Let's save, let's go back outside, okay. So now we do have this field assigned with the correct reference. And now the question becomes, how do we convert a game object onto an entity? And once again, thankfully, because of the baking system, the answer is super simple. We just use literally the exact same getEntity function. So over here, when constructing the selected, let's assign that one. So we're going to want to assign the visual entity. And over here, we call getEntity. And for the first parameter, we'd pass in the game object we want to convert. So let's go inside the authoring component, grab the visual game object. And then for transform usage flags, let's make it dynamic. And yep, that's it. So this will basically take this game object and convert it onto an entity and assign that entity over here on the visual entity field. Now we can verify that this did indeed work. Let's save it. And over here in the inspector, again, make sure you drag the reference, but make sure you drag it from inside the prefab. And now if we select one of these entities over here in our hierarchy, and if we go onto runtime mode, again, slight bug, let's select a different one. And there you go, it does show up. And now we scroll down. And yep, there's our selected, and we can indeed see it does have a reference to the selected entity. That's the entity with ID 129, so we can manually go inside of this one, select the selected, and see, yep, entity, it is indeed 29. All right, awesome. So with this, we have a component, and that component does have the correct reference to the visual entity that we want. Now with that, we have all the info we need in order to show or hide it. So let's make a system to do just that. So on our systems folder, let's right click, go into create a new iSystem, make this the selected visual system. And over here on this one, let's cycle through all the entities that have a selected component. So we're going to do system API.query, so the same thing we already saw. Let's grab the selected just for reading. We don't need to write anything to it right now. Let's grab the select component. So that's going to be our query, and let's put this inside a for each for the ref RO of our selected component. And we have the selected in this query. Okay, so this is going to cycle through all the entities that are selected. Again, keep in mind that whenever you include a query, it is only the entities that have that component and the component is enabled. Then for actually showing or hiding, for that, we're going to be playing around with the scale on the local transform. So let's go here onto the select component, and let's also define a field for the show scale, basically how big we want this to be. If we want to hide it, we're going to put it on 0. But if we want to show it, let's put it on something, and let's also expose this over here and pass it in on the baker. Okay, like this, let's save this one, just set it in the editor. So here in the editor, let's select the prefab itself. Let's scroll down, and for the show scale, let's put it on 2, because that was the 2 that we used over there. Okay, great. So back in our select visual system here, we have the query running through all the entities that have a select component. And now we want to grab the local transform for the select visual. However, again, it is the local transform of the visual entity, meaning it is not the one inside of this query. This query is basically going to give us the parent, but we want the local transform of the child visual. So the way that we grab a component for a different entity, the way we do that is we access the system API, and then we have a bunch of get component functions. We can do this one, which is just going to return our component. But in our case, we actually want to get the local transform to then modify it. So let's actually use this one, which returns a ref RW of that component. So let's call get component RW. We're going to grab the local transform component. And for the entity that we want is the one that is inside selected. Let's read the value and read the visual entity. So yep, this is going to be returning a ref RW local transform for the visual local transform. Okay, we have this one. And now with this, we can simply make it visible. So let's go inside the value RW for writing, and let's set the scale, go inside the selected, let's read the value RO, and let's grab the show scale. So yep, this code right here should be making the units that are selected actually visibly selected. Although right now, you might be thinking an interesting thought. You might be thinking, isn't this code actually losing the benefits of dots, since we are essentially accessing a reference that points to a completely different position in memory? And the answer is yep, that is indeed correct. Technically, since we are getting and setting a component on a completely different entity that is not within this query, because that this code will not be as fast as if we were just doing a query. But two things on that note. So first, this code isn't super complex, so even though it's technically going to be slower than if we weren't using this, technically it's not really going to be an issue. And secondly, in a few lectures, we're actually going to implement a really nice event system, which means this code will only run when the units are selected or deselected, and not on every single update. So performance on this system isn't really going to be an issue. And this is also a great example of how, when working with dots, technically you want to take as much advantage of the massive speedups as possible. You want to really only access components in the memory that is tightly packed. But in some cases like this, you always need some kind of random memory access. That's normal. It would be pretty much impossible to make a game that completely avoids any kind of random memory access. So while it is something you should avoid as much as possible, it is also fine to use in certain scenarios. Okay, so like I said, this one should be cycling through it and should be making the visuals visible. Let's test to make sure, let's save this. And here in the editor, let's make them essentially deselected by default. So let's go inside of this prefab, let's double click, go inside on the selected, and let's set the scale to 0 so that it's essentially hidden or deselected by default. Okay, great, now let's test. And yep, right now by default, none of them is showing deselected visual. Now if I were to select a unit, and over there manually let's select it. And by the way, if you make something as enableable, but you add some extra logic inside of it, some extra data, if you do that, then it no longer shows up over here on the tag section. If so, then it shows up as a normal component, but it still has this nice toggle. So right now the unit is not selected, and if I click, and if there you go, the select visual did show up. If I select a different one and set this one as also selected, let's go down, select, and if there you go, now both of them have the select visual. Alright, awesome. Except one issue. If I now deselect this unit, so let's deselect it, and move, and okay, so it is not moving, but the visual is still there. It is not hiding. So over here for hiding, it's actually super simple. We can do pretty much a very similar query, so let's copy this and paste it up here. Except instead of just looking for components that have the selected enabled, instead, let's use with disabled, and we're going to look for the select component as disabled. So this one is going to run on all units that are selected, and this one on all units that are deselected. And for the show scale, let's just put it on 0 to make it deselected. Okay, that's really it. Super simple. Let's save. Okay, let's test. And yeah, by default, all of them are deselected. None of them are selectable. Okay, great. Now I select one of these, and let's manually make it selected. So down here on the selected, enable this. And if there you go, that one is now selected. Now let's deselect it. And if there you go, the visual disappears, and I can no longer give orders. So I can select this one, set it as selected, select another one, set it as also selected. Now I have both of them, control, they both have the visual, deselect this one, and only that one has a visual. Alright, awesome! With this, we can now easily select any entities we want. The visual updates to show whether they are either selected or deselected, and depending on whether they are selected or deselected, we can give them different orders. Okay, great. So with this, we have our basic unit selection working, except we are manually selecting them by clicking over here on the inspector. We should really implement some logic by selecting them by using the mouse in-game, so let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture we're going to set up the UI and learn how to create a selection area so that we can finally select multiple units. Alright, so our selection logic is working. We can only control units that have the selected enabled, so if I select one of them, I can manually assign it as selected, it shows visual, and I can control just that one. But of course, we don't want to select the units by clicking on the inspector, we want to do it directly in-game. So let's set up the logic for selecting units using the mouse. And we're going to set up a standard RTS multi-select mechanic, meaning click on one place, let go on another, it creates a selection area, and then we want to select all the units within that area. Okay, so over here on the Unit Selection Manager, in order to check if the player is actively selecting an area, for that let's just listen to the left mouse button down and up. So up here, let's do an if input.get mouse button down on the 0, so the left mouse button, and same thing for the get mouse button up, also for the 0. Okay, just like this. And again, like I mentioned previously, we can later refactor this to work with the input system. Okay, so we have the mouse button down and up. Now to get the selection area, we basically just need to store the position on mouse down and on mouse up, and then do some math to find the actual area. So let's define a field to store it, a private, let's make it a vector2 because screen position only has X and Y. Let's call it the selection start mouse position. So we have this one, and then when we press on mouse button down, let's set it to input.mouse position. This is going to contain the mouse screen position. That's exactly what we want. We want this one and not the mouse run position. Nope, we want the screen position. Okay, great. Then on end, let's do the same thing. Define a vector2 for the selection and mouse position. And same thing, input.mouse position. Okay, so now let's test. Let's do a quick log. So do a debug.log and say up and showcase this one. And up here, let's say down and show the other one. Okay, yep, like this, let's test. Okay, so the logic is going to be on screen coordinates, and based on the screen, up here near this lower left corner, it should be around 0, and on the top right corner, it should be around 1080p. So let's see that, so let's click over here, and yep, it is down 37, so that is pretty close to 0. Now I'm going to go all the way up there, let go, and yep, 1900 by 1000, yep, pretty much 1080p. So wherever I click, it does match perfectly, click, let go, and it does pick the correct size. Okay, so far so good. Our basic logic is working, so we know when the player presses, when they let go, and we know the positions of those. So with that, now let's set up the UI. So in the hierarchy, outside of the subscene, let's right click. We're going to go into the UI and let's construct a brand new canvas. Now I'm going to set it up like I normally do with all of my games. So for the random mode, yep, let's leave it on overlay, so this is all correct. Then over here on the canvas scaler, let's swap it from constant pixel size. Let's go with scale with screen size. And over here for the reference resolution, I like putting it on 1080p, so 1920 by 1080. And over here, fully match with the height. Okay, yep, this is the setup that I normally use. So with this, let's see what this does. So let's right click on top of the canvas. Let's construct a brand new UI image. And yep, there it is. There's the image just like that. So with this setup, basically this means that UI elements will scale if the vertical size of the window changes. So if I make this window smaller, yep, there you go. You can see the white square. That one is scaling up or down depending on the size. However, this will not scale if the horizontal size changes. So like this with this, and if I swap it out to free aspect to make it really wide, swap it, and yep, there you go, everything still stays with the exact same size. So this is how I normally set up the UI in my games. That way I just need to make sure it all fits on the squarest possible resolution, so something like 5x4. If everything fits over here, then it's going to fit on pretty much any resolution. And if the vertical size is smaller, it's just going to automatically scale. Okay, so that's really it. We have our correct UI setup. Now inside the canvas, let's get rid of this image. Let's right click, let's create a brand new game object. Call this the Unit Selection Manager UI. On the rect transform, let's make sure to make it occupy the entire window. So you want to select this one to stretch, but let's also press on Alt so that it modifies both the position as well as the width and height. So hold down Alt and click over here. And if there you go, it should be stretching with everything on zeros. Okay, great. Now inside this one, let's make an image. So let's right click, construct a brand new image. Let's name this the selection area image. For this one, we want to anchor it on the lower left corner. We want to anchor and also modify the pivot. So now we want to hold down Shift. So hold down Shift and click on the lower left corner. And if there you go, over here, the pivot should be like this. The anchor should be like this, everything like this. Okay, great. This is really important. If you don't anchor it on the lower left corner, it is going to look weird. And then finally for the visual over here for the image, let's go with a nice green. So something like this. And then just make it a little bit transparent. So something like this. Okay, great. So our UI visual is set up. Now let's set up the script to run this. So on the project files, again, let's keep things organized. So let's right click on the scripts folder, just make another folder, call it the UI. And now inside of it, let's construct a brand new model behavior script. Again, another thing about dots versus game objects. When working with UI, you probably want to use normal game objects, normal model behaviors. So let's call this the unit selection manager UI. Okay, let's select the object. Let's attach a script and open it. Okay, so now here the first thing that we want is to store a reference to our visual. As always, let's keep our code nice and clean. Since we are not working with dots, we are not working with a data-oriented design. Because of that, over here, we should be using good, clean code, object-oriented principles. So let's define it as private for a rect transform. Let's define the selection area rect transform. And to make this exposed in the editor, let's keep it private and make it a serialized field like this. Again, since this is an intermediate course, I'm assuming you already know about this attribute and why I'm doing this. If not, I have a video on this topic. Basically, you want to limit access as much as possible, so you should not make your fields public. If you do, you're going to enable read and write access from anywhere in your entire codebase. That is not a good thing, you should avoid it. So you should default to making it private, but if you make it private, it does not show up in the editor. So to solve that, we add this attribute. It keeps the field private, so no other class can modify this field, but by having this attribute, it is going to be exposed in the editor. So over here, let's make sure to save. Now here in the editor, wait for it to compile, and let's make sure to drag this reference. Okay, so far so good. Now we want to update the visual based on logic. And again, let's keep our code nice and clean by keeping this UI class as decoupled as possible from the main logic class. You should always keep your systems as decoupled as possible, especially when it comes to UI. You generally want the UI class to depend on the logic class, but not the other way around. Technically, your game should work just fine without any UI at all. Doing that will help you quite a lot in managing complexity. So we're going to set up that connection between the logic class and UI class. We're going to do that using events. So over here, back to the unit selection manager script. Let's fire off some events that the UI can hook onto. So let's define a public event of type event handler. This is the standard C# event that exists inside system. Okay. Let's call this one on selection area start. And let's make another one. This is on selection area end. Okay, we have these two events. Now let's just fire them. So over here, when we start, let's invoke this event. So question mark, invoke with this and event args.empty. And same thing for this one. When we let go on selection area end, invoke it with this and event args.empty. Okay, so far so good. Then of course we need the UI class in order to be able to listen to these events. For getting the reference to this object, technically we could make another serialized field, or over here on this one, we can just make it as a singleton. Let's do that just in case we also need to access the script from other scripts. So making a singleton, super simple. So public static of type unit selection manager. Let's call it instance. Make this a property with a public get and a private set. So yep, there's our singleton, and to set it, let's make the standard private void awake. On awake, set the instance equals this. Okay, great, we have our singleton. And now back over here in our unit selection manager UI. On this one, let's listen to that one on start. So private void start. Over here, we can access the unit selection manager, access the static instance, and we can start listening to these events. Basically for this, my general rule is you should use awake for initializing each particular script. And then whenever you want to access an external reference, like over here on the UI, we are accessing a different class. For this, make sure you do it on start. Just by following that super simple rule, that is going to help you avoid a ton of code timing issues. So over here, let's listen to this event. So plus equals, let's give it a proper name. So the unit selection manager on start, and same thing for the on end, on selection end. Listen with the unit selection manager like this. And if there you go, we have both of them. Let's just do a quick log just to verify that this is indeed working. So with this one, let's print out this one. Okay, like this. Let's save everything. And now let's test. So here we are, and now left click, and if there you go, there's the down and the event was fired, and now let go, and if there you go, the other event. Okay, great. Now let's set up the visual. First, we actually want to show it on start, so let's actually put this one up here, makes a little bit more sense. So on start, we want to show it, and on end, we want to hide it. For that, it's actually super simple. Like the simplest way to show or hide is really just enabling or disabling the game object. So let's exit the game object, set active. This one we want to show, so set it to true. This one we want to hide, so set it to false. Okay, great, very simple. Also by default, let's start with it hidden. So over here on start, let's also hide it. Okay, that handles the show and hide. Now for the size and the position, let's go over here on the logic class. And on this one, let's basically make a function to calculate the current selection area. So let's go down here, make a nice function. Let's make it public since we're going to access it from the UI. Let's call it getSelectionAreaRect. And for this function, we're going to use a super useful data structure that is the rect that exists inside Unity Engine. This one represents a rectangle, which is exactly what we want. So this is absolutely perfect. Let's do this. And over here, we're going to return a brand new rect. This one takes in an X and Y. That is going to be the lower left position, then a width and a height. So for this, we really just need to calculate the lower left corner and the upper right corner. Now, initially, you might think to just use this position right away, the selection start, you might think this one is going to match up as the lower left corner, but that is not necessarily correct. The player might indeed click on the lower left and let go above, but they might do the opposite. They might start clicking above and let go below. So the start point is not necessarily going to be the lower left corner. Thankfully, that's a super easy thing to do. Let's define a vector2 for the lower left corner. For this one, let's construct a brand new vector2. And over here on the X, we can simply use mathf.min. This one returns the minimum between two values. We can grab the selection area start, grab the minimum of that X, and then for the end, we need to grab it over there. So let's grab the current end, the current map position. Go inside this one, .x, grab the minimum, and same thing for the Y. So grab the minimum of both Ys. Yep, that is going to give us the lower left corner. And let's do the same thing for the upper right corner. So the upper right corner, except instead of the minimum, we just use the maximum. Okay, great, that's it. So now with this, we can easily construct our rect. So for the X, that is going to be the lower left corner.x. Then for the Y, lower left corner.y. Then for the width, we can simply go upper right corner, grab the X, subtract the lower left corner.x. That is going to give us the width. And same thing for the height, except just using the Y. All right, that's it. Some pretty simple logic to calculate the exact selection area. So now with this, we can go back over here on the UI script, and let's make a function that is going to update the visual. So private void, let's call it update visual. On this one, let's grab the rect. So let's access the unit selection manager, the instance, get the selection area rect. So that returns a rect for the selection area rect. And with this rect, this has actually become super easy to use. Let's just go selection area, grab the rect transform, and we just set the anchored position. We set it to a new vector2, and it's going to have the selection area rect.x, selection area rect.y. So this is going to be the lower left corner. And again, this is why it's so important that you anchor it, the pivots correctly. It has to be on the lower left corner so that when we modify the anchored position, it is going to be positioned on the lower left corner. And finally, we just need to modify selection area rect transform, modify the size delta. And for the size, let's do another vector2. We're going to go selection area rect, grab the width, selection.height, just like this. Okay, yep, that's really it. So now let's just call this function. So when we start, let's go ahead and update the visual right away. And then we need to update it as long as the visual is visible. So up here, let's make a private void update. And on update, if the selection area is visible, which we can actually use just the game object, if this one dot active self, if that one is active, if it is visible, if so, then update the visual. Okay, yep, that's it. So basically we just need to calculate the rect, use it in order to display the correct size on the selection, and then use events to show and hide. So yep, let's save both files, let's test. Okay, here we are, and it starts off as hidden. Okay, great. Now I click over here and I move over here. Yep, and it does show perfectly the square. Let go here, and yep, does work. Do the opposite, starting above, going down, and yep, does work. So we can start clicking from anywhere and stop anywhere, and everything works perfectly. All right, awesome. Again, if yours is not behaving exactly as intended, if so, the first thing you should do is select the area image and make sure the anchors are set correctly. It should be anchored on the lower left corner and the pivot also on the lower left corner. And on the parent object, this one should also be set to stretch to occupy everything. So it should be set up exactly like this. And in the code, make sure you are doing this math all correctly. If you do all of that, then yep, all of this should be working right. Okay, so far so good. Our visual selection logic is all working perfectly. We can perfectly draw exactly the square we want to select. All that's left is actually selecting the units underneath. So for that, basically we need to figure out which units exist within this area and which ones are outside of it. And there's actually one interesting point on this one. When I was first researching this topic for the prototype on this course, instead of using screen positions like we saw, instead of that I initially used world positions. So instead of storing the start screen position, I was storing the start world position and then the end world position. However, since the camera has perspective, that did not work. If you use screen positions and you click over here and then click over here, if so, then it is going to select this area. However, if you use world positions and you click over there and you click over there, if so, then it's actually going to end up with a selection area kind of like this. So it is going to end up with a skewed rectangle. Depending on the field of view on the camera, it is going to be more or less skewed. So the proper way is like this, using screen positions, and now we can finally figure out which units are within these screen positions. And the way we do that is actually quite simple. We just need to cycle through all the units have a certain world position, we convert that world position into a screen position, and then simply see is it within this screen position area. So let's do that. So back over here on the unit selection manager script, over here when we let go of the mouse, we need to figure out which units are inside it. So let's just get rid of these testing logs. We no longer need those. Okay. So now let's do a query looking for our units. So we're going to do something very similar to what we have here. So let's actually copy paste this code. So we grab the NT manager from default world. Yep, same thing. Then we create a new NT query. And now for the events over here, instead of unit mover, we're going to need a local transform. We're going to need that so that we have the world position, which we can then convert. And then we don't want to select units that are already selected. We want to cycle through every single unit, so let's get rid of that one and just keep the local transform. But again, you might be seeing this might be an issue. All the entities that have some kind of transform, they are going to have this one, whereas the goal is obviously to only select units. So now is probably the time when we should create some kind of tag component to define what exactly is a unit. Otherwise, local transform is going to include anything, even environmental objects. So let's make a tag component for units. Let's just make sure this code compiles. So let's just comment out this for a little bit. Okay, let's save. Now here, let's make our new mono behavior. So inside the authoring, let's construct. And again, if you want, you can use this pre-made Baker script, but personally, I prefer building it from scratch. So let's do that. Call this one the unit authoring. And over here, the simple thing. So let's make a public struct, call it unit. This is going to be iComponent data. And for now, it's really just going to be an empty tag component. So yeah, all we need is the Baker to be able to add it. So a class Baker, let's implement Baker with unit authoring. So the usual standard thing. Then over here, let's implement the abstract class. We need to grab our entity. So get entity, get it with transform.dynamic. Okay. And finally, add component. On this entity, let's add new unit component. Okay, that's it. Let's save. And over here, let's select the unit prefab. Again, select the prefab, not an individual unit. And on the prefab, let's add the unit authoring. Okay, great. So now back in our unit selection manager, over here we have our query. So we can look for things that have a local transform and then also a unit component. That way we make sure that they are actually going through units. However, enemies are also going to be units, but they're not going to be selectable. So we want to also include the select component within this query. But if we just do selected, if so, this is only going to query for entities that are already selected. That is not what we want. We want to be able to select units that are deselected. So instead of including it in the query over here, instead let's use one of the options. Let's use this one with present. This one means that the component has to exist regardless of being enabled or disabled. So let's do this with present of the selected component. Okay, great, just like this. So now let's construct our arrays. So we're going to have an NT array. Yep, that makes sense, but not a unit mover. Instead, we want the local transform. So let's name this the local transform array to component that array of a local transform. Okay, now let's cycle through that array. So cycle through the local transform array. And now here we do something. Let's grab the local transform for this unit. So the unit local transform, go inside the local transform array on this index. Now within this unit local transform, within it we have a position. This is going to be the world position. So now the goal is to convert it from a world position onto a screen position. And for that we can access the camera, so camera.main to find our main camera. And we can use the function world to screen point, which does exactly that. So let's pass in our world position. And this one is going to convert into a unit screen position. Okay, so we have the screen position of the unit. And now we can very easily test, is this position inside the selection area? Now, thankfully, the actual rect type, this one already has a function perfect for that. So we can just go up here, let's call the function, and inside we have a contains function. Test if this one contains the unit screen position. And if it does contain, then the unit is indeed inside. Also, by the way, over here, since we are cycling through an if, let's make sure we cache our selection area. There's no point in doing this all the time. So up here rect for the selection area rect, let's call the function, and then over here we just use it. Okay, great. So basically this means that unit is inside the selection area. Now this one, we just want to select the unit. So that is going to be super simple. We just access the entity manager, and then there's a function called set component enabled. We want to set the selected component. we want to select on this entity, so let's access the entity array on this index. And in this case, we want to set it to true. And yep, that's really it. So we cycle through all the entities, we do our query, they need to have a local transform and a unit, and they need to have a select component. Then we cycle through all of them, we grab the local transform, we use the world position, we convert that world position into a screen position, and with that screen position, we test if it is inside the selection area, and if it is, we set the select component as true. Okay, so that's really it, this should be working. The only thing remaining is we need to deselect the units. We're really just going to deselect all of them and then only select the ones that are inside. So doing that is quite simple. Let's just do a query for all units that are already selected. So let's do another query before this one. And on this first query, we're going to look for things that are already selected. So just selected, no need for with present. So just like this, a super simple query. Then we just convert them into an int array, and then we cycle through that array. So for int I through the int array.length, cycle through it, go through the entity manager, and set the component enabled for the select component on this entity. So on the entity array, on this index, and set it to deselect. And down here, let's just reuse that one. Okay, yep, that's really it. So we deselect all of them, go through the selection area, and select the ones that are inside of it. Okay, so that's it. Let's save. And now let's test. Okay, here we are. And first, the visual still works. Okay, let's try selecting one of these. And there you go. It did select. It selected all of those. Now select these. And there you go. It did select that one. And yep, there you go. It does work. So I can select all of these, and everything gets selected perfectly. All right, awesome. By the way, here our code has a slight bug. So right now playing it, this one does work perfectly. So I can click anywhere, drag it, and yep, it does generate the exact perfect square. However, this one is only working perfectly if you have the game scene over here set up exactly to full HD. If you switch to any of these other ones, for example, if you put it on free aspect, and now if we try, and no, it no longer works. It's off both on the starting point as well as the entire scale. The logic still works, so if I click and drag here, the visual doesn't work, but the logic does work. I can select the units, but the visual is definitely a bit off. Now, this actually has to do with the scaler. So if we select the canvas, over here we set up the scaler, and we set it up to scale with screen size with a reference resolution of 1080p. So with this, if the game window over here is set up exactly on 1080p, if so, then it perfectly matches the canvas scaler, so the canvas itself doesn't have any scale. We can see over here the scale is on 111. However, if we set it to anything else, even if it is, for example, 16:9, which keeps the same aspect ratio but lowers the resolution, with this, yep, now that does scale the canvas. And this is exactly what is causing that issue. So we need to incorporate this scale in our logic. Now, thankfully, that's actually pretty easy to do. We just need to take whatever position and scale we have and just divide it by this value. So over here in the code, let's just add a reference to our canvas. So let's add a new serialized field of a canvas. And here in Unity, let's just drag the direct canvas reference. Okay, great. And then over here, the code is going to be super simple. So it's over here on the update visual. Like I said, we just need to divide by that value. So we can grab the canvas. Let's access the canvas transform and grab the local scale. And from this, let's just grab the X. All three of them, X, Y, and Z, those are going to be scaled exactly the same amount. So we can just grab any of them. So let's grab the X and say this is the canvas scale. We get this, and then we just need to divide these two by that. So here, divide by the canvas scale, and this one as well. Okay, yep, that's it. This should now work. So here we are, first of all, on full HD, and if I click and move, yep, it does work. And now if I swap it out to free aspect ratio and move, and yep, now it still does work. So I can put it on any aspect ratio, anything we want, like 5:4, and yep, it does work. Put it on 16:9 with scale, and over there the canvas is indeed scale, and yep, everything does work perfectly. Alright, awesome! By the way, I only noticed this bug thanks to feedback from a student, so if you do find anything not quite right in any of the lectures, definitely let me know about it so I can fix it. So the selection is working, and of course the move logic, that one is also still working, so now we can select, we can define which units we want to move, give them orders, and everything works perfectly. Okay, great! So here we set up unit selection, we also set up the UI, and we created the logic for creating a selection area and actually selecting the units. With this, we can select any number of units and then give them some orders. However, there's actually one annoying thing here. If we want to select just one unit, if I click, nope, it doesn't really work. We need to draw a square, even if it is a tiny square, in order to finally be able to select the unit. So just by clicking doesn't work, need to do at least a tiny square that occupies the origin, and if it does occupy the origin, then it does select the unit. Now this is a bit annoying. We should be able to just do a simple click and select an individual unit. Doing that is relatively simple, but also means we need to learn about dots physics queries, which is actually going to be a lot of fun. So let's implement that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to handle the logic for selecting just one unit. And the way we're going to do that is with a Raycast. If it hits a unit, then we select just that one unit. So this means that we're going to need to learn about how to do physics queries using dots. Okay, so we already have the selection area working. I can select a bunch of units, do a little square, and select all the units within that area. Then I can just give them orders, something like that. However, we cannot easily just select just one, so I click on this one. Nope, doesn't work. I need to do at least a slight square in order to be able to select it. So let's hold this. Let's use physics and a Raycast to test for single unit selection. Now, physics in dots is actually surprisingly easy to use. But before that, first let's add some logic to test when should we use physics, meaning how to define when the player is trying to select just one unit versus selecting multiple. For that, essentially, we can check the size of the selection area. So if the selection area is at least a decent size, if so, we're going to engage the select multiple mode. But if it is small, like something this tiny, if so, then we're going to select just one single unit. Okay, so let's add that logic. Now first, let's deselect all of them. Okay, that makes sense. So we handle all of the deselection. And then for selecting, let's grab the selection area rect. And from that one, let's calculate a selection area size. So float selection area size. And for the size, let's just do selection area rect. Let's grab the width and add the selection area rect dot height. Now technically this isn't going to be an area. If it was an area, we would do multiplied as opposed to plus. But we're not actually trying to get a specific number. We're just trying to get something. And if we multiply, we end up with a huge number. So either way it works, but let's go like this just to have a simpler test. So let's define a float for the multiple selection size minimum. Let's say something like 40 units. We need to test this. And basically, let's define a boolean for is multiple selection. And basically, we're going to be doing multiple selection if the selection area size, if this size is bigger than the multiple selection size min. If it is bigger than that, then we are going to do a multiple selection. And if it is smaller, then we select just one unit. So let's just do a log on this one. So debug.log. Let's print out the multiple selection. And let's also print out the current size, just so we can see if the value 40, if this one does work right. Okay, let's save. Okay, so now here, let's look at the log. So basically, if I do a big one like this, it should select multiple. So yep, that is true and has a size of 1,000, okay? And if I make something like this should probably be, something like this should be the smallest. So let's see how big is this square. It's about 100. So if it is something like this, about 50. So yeah, 40 pretty much means just a tiny, tiny square. So as long as it's a little bit bigger than this, then we're going to select multiple. If it's smaller than this, we're going to select just one. Okay, so I think either 40 or 50, that one seems pretty good. Okay, great. So if I just click, that is going to be pretty much 0, select 1. If I do a square, then select multiple. Okay, good. So now we have this simple boolean. So if we are doing multiple select, then we're going to do this multiple select logic. And if not, then single select. Okay, sounds good. Now over here, let's learn how to do a Raycast. So for that, the first thing we need to do is grab something known as the physics world singleton. That is an actual type, physics world singleton, this one, this type, which exists inside unity.physics. So up here, let's go ahead, make sure to include that. Okay, so we need to access this type, and this exists inside an entity. So the way we're going to find that is by doing a query to get that type. Now for that, we can do the exact same thing that we did up here. Create a new query builder. With all, we would write this type and then simply get it. That would work perfectly fine, but let me also take this time to show you a different way of also creating an entity query. So this way works fine using an entity query builder. That works. But another alternative approach is to go through the entity manager. So we go through this one, and on this one, it has a function called create entity query. So now this one has a different syntax. So instead of taking in the types as generic, instead we write the type directly as a parameter. And this one takes in an actual type object, meaning it is not just physics world singleton. It is not just like this. This is a syntax error. We need to pass in the type. So let's use the type of keyword in order to convert that into a type. So yep, just like this. So this is doing essentially, let's copy this one, just see the exact same thing. So create new entity query builder with all of the physics world singleton, just like this, and build the query. So basically both these lines are doing the exact same thing. So feel free to use which one you prefer most. Okay, so this one will return an entity query, and that query is going to contain entities that have the physics world singleton. And like the name implies, this one being a singleton means there's really only one of them. So technically, we could take this query and do the same thing that we were doing up here, convert it to an entity array or to a component data array of this type. We could do that and then simply access the component that is on position 0. That would work, that would get us the component, since again, this one is only going to have one. But the entity query, this one also has some helpful functions, like one called getSingleton, which does exactly that. So we call getSingleton, this one takes generics of a physics world singleton, just like this, and yep, this is going to return an object of type physics world singleton. So that's it, so we construct the query looking for this object, and then this one automatically finds the single instance, the single entity that has this component, and we get it over here. So with this, we have the physics world singleton, and now inside of that one, there is something called a collision world. Let's store this one, so a collision world like this, and now it's inside of this type. If we go inside dot, and up here you can already see we have functions for doing a box cast. We can cast some collider, cast array, check a sphere. We've got a bunch of overlaps, overlap sphere, capsule, and so on. So basically, this is where you can do all kinds of physics queries. We're going to use these quite a lot. Now for this one, for the click, for this we want a simple raycast. So we can just use this one over here, cast ray. Let's see what parameters this requires. It takes in something of type raycast input. So let's construct this type. So a raycast input, construct a new raycast input, okay. And now for the data inside of this one has a start, that's a float 3, so it's a world position. It has an end, which is another float 3, and then has a filter. So for getting the start and the end, that is actually quite simple. Again, we're trying to do a raycast from the camera's position. So like we did on the script for finding the mouse world position. So over here on this script, we use the camera in order to convert a screen position onto a ray. And then from this ray, we can call getPoint to get a point on any position within that ray. So over here in our code, we can do exactly that. So let's grab a ray for the camera ray. So here we go inside the camera, get the main, and let's call the function screen.point2ray. This one takes a screen position and converts it into a ray. So for the screen position, let's use input.mousePosition. Okay, yep, that's it. However, here we actually see an error. It is saying ray is an ambiguous reference between unity.physics.ray and unityengine.ray. Basically, the unityengine.ray, this is one for the game object world, and Unity Physics, this one is from Dots Physics. Both of those namespaces contain a ray class. So one solution is to go up here and get rid of one of these. We could get rid of the Unity engine, but then we would have errors whenever we use debug.log. So down here, let's just write the full name. So this one, screen.point2ray, this one is going to return a Unity engine.ray. So let's write the full name. So Unity engine.ray, just like this. So we have the camera ray, and then from there, we can call the function getPoint. This one takes in a distance and basically returns the point at that distance along the ray. So for the start point, we want to start pretty much at the camera position. So let's start on 0f. And then for the endpoint, let's do the same thing. And basically, we just need the point that is far enough away. Now, technically, we could do a raycast in order to find the perfect distance that the unit is from the camera position. Or you can just simply put a huge number. Either one is really going to work fine. So up here, let's just put a bunch of 9s, and that is more than enough to actually collide with the unit. So to do that, and the final parameter is the filter. This one is of type collision filter. This is a special dots type. Let's construct a brand new one, a new collision filter, which by itself also has 3 parameters. It has belongs to, collides with, and the group index. Now these are essentially layers, or rather layer masks. So the ray is going to belong to this layer, and it's going to collide with this layer. The layers over here are the ones that you define on the game object itself. So if you go back over here into Unity, let's select actually our prefab instead of any of these. Okay, select the prefab, and over there in the inspector, we can see the layer drop-down menu. So we can click on it and we can add some more layers. So for example, over here for layer 6, for the first empty one, let's define this one as our units layer. So just write units. Now here we just need to memorize this number, so this is going to be in layer 6. And now we can select the prefab again, select the prefab, not the ones on the scene. And on this one, let's swap this one from the default layer onto the units layer. And nope, we do not want to apply to children. The only thing that matters is the object that has the collider, which is going to be this one. So let's go ahead. Yep, okay, so this one is now on the units layer, which again is layer number 6. So here in the code for defining that is exactly what these are going to represent. We use those layers to say that this raycast is going to belong to a certain layer and is going to collide with a certain layer. And by the way, for the group index, this is basically a special override. This one is just a number. You can see it's just an int. So if you put a number here, like number 56, and then you have another object that has the exact same group, then the raycast will always collide with that object, regardless if it belongs to a different layer or does not collide with that layer. So basically the group index is always going to be an override, but in most cases we don't really need to worry about this one. So we can just default this to 0 like that. Okay, so now for these two that are important, the belongs to and collides with. So how exactly do we set these up? This one is actually a uint, so an unsigned int, but this one is a bitmask number, meaning that the layers are defined by the digit position in binary. So over here we do not put 6, this is not correct. Like I said, this is a bitmask number. So a bitmask means that essentially the layers are going to be defined by the digit position in binary. So here we have an 8-bit number defined. It has 8 bits. All of them are on zeros. So if we were to use this as the belongs to layer, then the raycast would not belong to any layer, because again, everything is on 0. So if we want to hit layer 0, then we need to flip this bit. So we need to flip this from 0 onto a 1. And yep, this would be the layer mask for hitting things on layer 0. And if we wanted to hit things on layer 5, so this layer 0, 1, 2, 3, 4, and 5, so we want to modify this one, and we would flip this bit into a 1. Then if we want to hit both layer 0 and 5, if so, we just put both of them on 1s. So this is a bit mask. Basically, the layers, instead of being integers, they are essentially just positions on a bit mask. Those are either 0 or 1, depending on what layers you have selected for either the belongs to or the collides with. So over here, as to how exactly do we construct that bit mask, we start with number 1, which, going back to our diagram here, 1 is really just this. So a bunch of zeros with 1 at the end. So we start with number 1, and then we bit shift, so put 2 angled brackets. This is called the bit shift. In this case, we want to bit shift to the left by the number of our layer. So if we wanted to shift this to the left by 3, then we do it just like this. So essentially what we're doing is first we define a 1, and then we take this 1 and we essentially want to move it to the left. So move to the left by 1 position, 2 positions, and 3 positions. So yep, that logic is doing exactly this. It is finally generating this number. So here in the code, if the goal is to collide with everything on layer 6, if so, then we need to do this, and we do not do this. That is a completely different thing. So let's do 1 bit shift by 6. However, we also should not put the 6 here. You shouldn't really hard code magic numbers like this. Magic numbers are only something you should avoid. Magic numbers is really just a number that has some special hidden meaning that is hard to decipher. So in this case, right now we just wrote this code, so we know that this 6 means the units layer. But if we leave it like this, we are definitely going to forget what it means. So instead of hard coding a magic number, let's use a properly named local variable. So up here, just define an int for the units layer, say 6, and then over here in our code, do it like this. Yep, now this makes quite a bit more sense. Except we also see that we have an interesting error. This telling us we cannot implicitly convert from int to uint. That is because the belongs to, this one is a uint, it is not an int. So this one is a simple solution. We take this one, instead of using a 1, which is an int, let's append the word u. And if there you go, now this one is assigned as a uint. Okay, great. So this is how we construct a bit mask. And actually for this one, we want this raycast to belong to every layer and collide with that one. So let's actually swap this. So let's put this one like this. We want the raycast to collide with only things on the units layer. And over here for the belongs layer, simplest thing is to really just make it belong to every single layer. The collision at the end of the raycast will be whatever matches both these. So to make the raycast belong to all layers, that is also pretty simple. We start with number 0, which again, going back to this diagram, the number 0 is literally everything on zeros. So all the bits are 0. In order to get all the bits into 1, we really just need to invert them. And the way we do that is with a tilde. So that one essentially takes all of these zeros and converts them all into 1s, meaning that the raycast will belong to every single layer. And again, this one should be a uint, so let's append u just like this. Okay, so yep, that's it. And just another quick mention that you might not know about that relates to over here the belongs to and collides with as to why this has both of these instead of just having the collides with. For that, here in Unity, we can actually go into edit and let's go into project settings. Then on the left side, let's go into physics, the physics settings. And yep, over here we see what is called the layer collision matrix. Here we can define that some layers do or do not interact with some other layers. So that is why over here the Raycast has that option, so you can make it belong to a certain layer and only collide with certain layers. Okay, great, so here is our Raycast input. So we define the start point, that is going to be the point directly in front of the camera. The end point is going to be a near infinite distance falling along the ray. And for the filter, we're going to make this Raycast belong to every single layer and make sure it only collides with the units layer. And the group index, this one is just default. Okay, great, so like this, now we can use this Raycast input on the cast ray. And now for the other parameters, so here we have multiple versions of this function. So you've got this one, which will output a Raycast hit. This will output just a single closest hit. Or we have this version. This one returns a native list, which is going to be a list containing every single hit that gets hit along this line. Now in this case, we really only want to select a single unit, so let's just grab the closest unit. So let's define an out Raycast hit for the Raycast hit. And again, Raycast hit exists in both the physics engine for the game objects and dots. So let's be explicit. In this one, we want the dots. So unity.physics.raycast hit. Okay, yep, so here is our correct ray. Now this function will return true if it hits something and false if nothing is hit. So let's do this into an if. So if this Raycast, if it hits something, if so, then we want to look inside the Raycast hit. And over here, we can see the entity. So we can find out which entity did we hit. Now, technically, since we made sure that it only hits things on the units layer, because that we can be pretty sure that this one is going to be a unit, but still, if we want, we can just ask the entity manager to verify. So we can, for example, go entity manager. Inside that one, we can check has component, and we check does it have a unit component. And yep, so if this entity has that component, then hit a unit. Okay, and that's really it. So now we can just go into the entity manager, call set component enabled, set the selected component on this entity, so raycast hit.entity, set this one into true. And yep, this should be working. So as you can see, it is really simple to do a physics query in dots. You just have to set up the data for the raycast or the overlap sphere or whatever, and you just call a function. And of course, before that, the more complex part is just having to go through all this. We need to construct an entity query, we need to get the physics world singleton, and then get the collision world. So it's a little bit more wordy than the normal game object physics, where you just do physics.overlap box and so on. So doing it in dots is slightly more complex, but still it is pretty understandable. Just grab the physics world singleton, get the collision world, and from there you can do all kinds of physics queries. Okay, so let's test and see if all of this is working. Let's make sure to save. Okay, so here we are. Those are all the units. I'm just going to try to select just this one. So just a click, and if there you go, it does select just that one unit. Now select all of them, move them all, it works. Single click, select, and so on. So I can select individual units, or I can select all of them and tell them where to move. All right, awesome. Now it looks a bit odd that all the units are moving into the same place. On the next lecture, we are going to generate the proper move positions. So let's re-enable just the collision just to see what that problem is actually going to solve. So over here, let's just go inside the unit prefab, and on the capsule collider, let's make it not a trigger. So let's make it so that it's solid. And yep, it is playing. They all go into the same place and they all hit one another. So they no longer go into the exact same position. And now I can select, can move a bunch of these, and yep, everything does work. Okay, great. Everything works, but of course, selecting multiple units and clicking still looks odd because again, they are constantly trying to go into just one position. They're constantly pushing each other around. So instead of telling them all to go to the exact same position, instead of that, we should write some simple code to generate some valid target move positions. So let's do exactly that on the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to dynamically generate some move positions so our units don't all try to go to the exact same spot. Okay, so right now we have units that we can control. I can click to select an individual one, select a group, and all of it works. However, right now, all the units, those are all trying to go to the exact same position, which leads to all this piling up. They get all kinds of collisions, it looks really strange. Basically, the more units we have, the worse this is going to get. Now, there are actually many ways to solve this problem. So one way is to sort of leave it like this, and then simply make the unit stop moving when it gets to the target and then allow it to be pushed around. So that's one option that could work, but another option that I think is best is to generate some proper move positions. So just like in many RTS games, you have formations. That's basically what we're going to build here. We're going to dynamically generate some positions in the code and send each unit to a slightly different position. Now there are many shapes we can generate, so RTS games usually have some kind of rectangle formation. Sometimes they have circle formations. You might see some arrow formations and so on. So you can really go as simple or as complex as you want. In this case, let's go with a very simple circle formation. So we're basically going to have our target position right down the center, and then we are going to generate rings around that exact same position. And on each of those rings, we are then going to generate a bunch of positions within that ring. And the further we go out in the rings, the more positions we can generate. So by following this logic, even if we have just 1 unit or 10 units or 100 units, everything will work. We're basically going to slice the ring into as many times as we need. We're going to basically slice the ring into how many positions we want to have. So in this case, let's say we make a slice here, then make another one here, make another one here, and another one here. The way we do that is first we start with the vector pointing right, so we have this vector, and then we're basically just going to add some rotation onto it. So we have this vector, this is going to be the first position on this ring, then we're going to rotate this vector down here, that is going to have this vector pointing down here, and that is going to be our second position. Then once again, rotate the vector down here and gives us that position. So we do that, and then for the second ring, we really just use a bigger vector, just going a little bit bigger, and same thing, we still rotate and so on. Okay, that's the rough logic. Now let's implement it. So over here on the unit selection manager script, let's make a function to generate our positions. So let's write private, and for the return type, technically we could return a normal vector3 array. We could return this, that would work. But instead, let's actually return a native array. Make it a native array of float3s. Again, native array, that is a native collection that works with dots and bursts. So let's make this one and call it generate move position array. Then for the parameters, so first we need to know the target position, so float3 for the target position. And then we're also going to need to know how many positions do we want to generate, so an int for the position count. Okay, sounds good. So now here, the first thing we do is create the array with this size. So native array of type float3, this is going to be our position array. Let's construct a brand new one. Let's use allocator.temp to make it temporary. And for the size, let's define it with the size of position count. Okay, yep, just like this. Then we can simply test if we are requesting 0 positions. So if position count equals 0, if so, then we don't really generate anything. So let's just return the position array. If not, then let's keep going. So if we're generating at least one position, then the very first position on the array, so on index 0, this one is going to be the target position. We always want to make sure that we want to use that position. And then let's do another if. So if the position count, if it is 1, then this one is really all we need. So let's return the position array. Okay. And if not, then let's finally generate all the other ones. So first, let's define some settings. So we basically need to define the ring size. So how far away is each ring from the origin? So let's find a float for the ring size, and let's use a number like 2.2, okay? Then we also need to keep track of which ring we are currently generating. So let's define a ring int for 0. And let's also keep track of which position index we are trying to assign. Now, since we already assigned the origin over there on index 0, let's start with the position index and start off as 1. Okay, great. So now here we're going to run our generation logic while the position index, while that one is under the total position count. So basically keep generating until we have all of them. So that makes it perfect to use a while. So while the position index, while that one is under the position count, while doing that, then we're going to generate a bunch of positions. So it's over here that we want to cycle through all the rings and calculate all the positions. First thing we should define here is how many positions we're going to have for this ring. As the ring expands, we can see it has more area. So as it expands, we want to have more positions. So we don't want it to just be fixed. We don't want to have just 4 positions on every single ring. We want to have some kind of minimum and then some kind of bonus depending on the ring. So let's define an int for the ring position count. That's how many positions we want to have in this ring. Let's define a minimum of something like 3 and then add, let's say, ring times 2. So on the first ring, on ring of 0, we are only going to have 3 positions. Then on the second ring, ring of 1, it's going to have 3 plus 2. On the next ring, it is going to have 3 plus 4 and so on. Okay, so now that we know how many positions we want to generate for this ring, let's actually go through them. So let's cycle through all those positions. Let's use a simple for. So int I starting on 0, while I is under the ring position count, I plus plus. Okay, we're cycling through all the ring positions. And now here, like I said, we're going to have a vector. We're going to start with a vector pointing in some direction, and then we're basically going to apply some rotation. Then keep increasing that angle until we have all the positions generated. So let's calculate what is this angle, which the first one should be an angle of 0. We should just get the vector. Then for this one should be some kind of angle and so on. So for calculating the angle, it will be whatever is the index of the angle. So are we trying to get on position index 0, 1, 2, 3, and so on? We're going to take that, and basically for calculating this angle, we just need to divide the entire rotation divided by the number of positions we want to have on this ring. Okay, so here for calculating the float angle, for this one, let's take, once again, start with the index, and then multiply it by the angle, which is going to be the entire ring split by some amount of ring positions. So let's grab math.pi2. Pi2, this one is the entire ring. Again, this is all in radians. And we divide this by the ring position count. So yep, this one gives us the angle that we want to apply for this one. And now with this, we can calculate our ring position. So what is going to be this ring position? So it is going to be the target position plus we take our vector pointing to the right. So that is going to be a new float 3. And for the size of this vector, it is going to be based on the index for the ring multiplied by the distance. So that is going to be the ring multiplied by the ring size. Except for the first one, we also want it to be offset. If we use a ring of 0, then it's just going to spawn in there. Nope, we want to spawn in here. So over here, let's use ring size multiplied by, and then use a ring plus 1. Just make sure that even on ring 0, we still offset by the ring size. And yep, we just want the vector pointing right, so just like this. So this is the vector, and then we just need to apply a rotation to that vector. So let's actually define up here a float 3 for the ring vector. And we're going to start off with this one like here. And for the rotation, we can use math and call the rotate function. This one takes in a quaternion and a float 3 vector and simply applies that rotation. So now we just need to take this angle, which is in radians, and convert it into a quaternion. So for that, we can use quaternion and call the function rotate y, because we are working on a top-down, so we want to rotate on the y angle, and rotate by this angle, and use this quaternion and that vector. Okay, so yep, so this is the ring vector, and we just apply that offset onto that one. And yep, that's really it. So we start off with a vector pointing straight right, we apply some rotation to it, and then we take that final vector, apply it to the target position, and that's how we get our ring position. So again, going back to the diagram here, we have this vector pointing right, then we apply some rotation, and we get this ring position. And since we are doing this inside of for and inside of while, this logic is going to generate every single grid position. So now that we have our ring position, all we have to do is add it onto the native array. So let's just access it on the position index and assign to this ring position. We assign it, and then let's make sure to increase the index like this. And after generating one position, we can see is this in last position. So let's test if the position index it is bigger or equal to the position count. If so, then we have generated all of them. So let's just do a break to get out of this for loop because we don't need to generate any more ring positions. So that breaks out and ends up down here whilst inside of the while. And at the end of the while, what we need to do is make sure to increase the ring index. So we go on to the next ring. And of course, if we have generated all of them, this is going to be false. And we're finally going to exit the while. And then over here, we just return the completely filled position array. All right, yep, that's it. So this was a bit of math, but I hope it was understandable. Again, we generate some rings outside of it, calculate a vector, apply a rotation, and doing that, we generate as many ring positions as we want. This function can work with 1 position, 10 positions, 100 positions, everything works great. So the function is going to return a native array, so now up here in our code, we just need to use it. So let's go over here onto the right mouse button, so this is where we are giving the units the orders to move. So after we get the entities and the unit mover, let's call that one. For the target position, that is going to be the mouse worm position. So this is going to be our origin. And for the position count, we can go, for example, grab the empty array, grab the length. And yep, so this one is going to return a native array of float 3. This is going to be the move position array. And since this one is going to have the exact same size as all of these arrays, then over here, when assigning the target position for this specific unit, let's go inside that array on this index like this. So yep, that should be correct. Just like this, all the units, each unit should be going to a different position. So let's make sure to save and try it out. Okay, so here let's select just one unit, tell it to move. And yep, just a single unit still goes towards the target position. Okay, so far so good. Now let's select a bunch more units and right click. And let's see, and yep, they do go to different positions. And we can see a sort of ring forming. So there's the unit down the center and all these 3 over there. Let's select all of them, tell them all to move and see where they go. And yep, like this, we can see the second ring coming around. So as they all move around, they all go to different positions. They all generate, and whether it be with 1 unit or multiple units, they all go to different positions. This code works with 5 units, 10 units, 100 units, everything works right. All right, awesome. Now the only thing is the units are still pushing each other around, especially if we move through them, they are trying to push things around. Now later on, we're going to solve this with some basic collision avoidance. And of course, later on, we're also going to implement pathfinding. So instead of the units going straight, they are going to follow the path and avoid obstacles. Right now, they just move straight with no concept of walls or anything. So we're going to implement all of that later on, but for now, this is looking good. We generate the move positions, tell them to move, and they all go towards the target position. Okay, so our logic is working. Our game is really starting to take shape. We can select any number of units, give them orders, tell them to go here, you go here, and everything works. So now it's time to learn one very crucial thing, events. Specifically, how to handle events in dots, which is actually a very interesting topic. So let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn one way for how we can handle events in dots, meaning how to know that something happened in a specific frame. One way we're going to use this is to make sure that our visual selection logic only actually updates when it needs to update. Okay, so here let's learn how to do dots events. Events are one of my favorite tools in programming. In my games, I use events a ton to keep my code nice and clean and minimize code coupling as much as possible. With normal C# events, you can keep one class completely decoupled from the other one. Usually the main way that I use them is to separate the UI code and the logic class, like we already saw in this course. This way, the UI class is tightly coupled to the logic class, since it does need to have that reference. But the logic class, this one is completely decoupled from the UI class. It does not know that any UI class exists anywhere, does not know and does not care. This is really awesome and helps you quite a lot in managing code complexity. The more decoupled your code is, the better it is. So events are awesome. However, since dots is data-oriented, that means events are actually quite tricky to do. Usually when working with an event, you access some kind of object reference, then you listen to that event, and the event itself is a delegate, which is another object. So in dots, we're not working with objects, so we can't use delegates or references or anything like that. Instead, we need to figure out some way of doing a data-oriented events. Now this was actually really tricky for me to figure out, how to do events without objects. I tried doing some research but couldn't find much on the topic of data-oriented events. So I'm not 100% sure if my approach is the best one possible, but it does work quite nicely, so let's see it. Since we cannot have objects and attach listeners to events, instead let's define a component, and that component is have a bunch of booleans. Then we are simply going to turn those booleans into true whenever some event happens, and then at the end of the frame, we're going to erase all of those booleans. Then if we want to essentially listen to an event, we just need to play some system to read the state of these booleans right before the reset system. Okay, so for storing the boolean, let's store what it actually makes sense. First, let's handle the events for when the unit is selected or deselected. So for that, it makes sense to put it here on the selected component. So we've got the visual entity, the show scale, and over here let's add some booleans for events. So let's make a simple bool, one for on selected, another one for on deselected. Okay, great, we have our two nice events. Now to quote unquote fire these events, let's go here on the unit selection manager where we are selecting our units. Let's scroll down to find where exactly we are deselecting all the units. So over here, let's also get a component for all of our selected. So entity query, let's go into query, get the component data array, do it of type selected with allocated.temp. Okay. So this is going to return our native array of type selected. And over here, let's do the logic for grabbing and updating it. So let's do the same logic that we had previously. This one that we did over here, where we get the array, we update the data, and then we call this in order to update it. So let's go up here and do exactly that. So let's go inside the select array on this index. Let's grab the selected. So we grab the selected, then go inside the selected, and this is the deselection logic. So let's set on deselected equals true. Then again, let's update the component inside the array. So selected equals this. And finally, go into the entity query, and let's copy from component.array, and let's copy in the selected array. Okay, that's it, just like this. However, actually, this event is going to throw a really interesting error. So let's see what it is. Let's make sure to save it. Save this one and also make sure to save the select authoring, save all the files. Then let's wait for it to compile. And now let's see that error. So here we are and it's working fine. If I just click anywhere empty, so click and let go. So here we are and everything is fine. Let's select some units. Okay, works. Now when I click here to deselect, let's see. And if there it is, there we have our error. So here in the console, the error is saying length of the input array is a size of 8 and does not match the length of the query, which now has a size of 0. Now this is a really interesting error. It actually took me quite a bit to figure out what exactly was happening here. Basically this code over here, copy from component.array, this one is trying to update 8 positions. That's how many positions we have over here on the select array. But the entity query, this query is now matching with 0 units. And this is because over here we are cycling through the entities and we are setting the selected into false. By doing that, we are modifying how many units are actually selected. So when we then access this to do this, it is basically going to rerun this query. And since we set them all as false, after running all this logic, then this entity query will no longer find any selected units. So this is a really sneaky, really tricky error. Always keep in mind when working with enableable components, if you disable them, they will no longer be included in queries. Now, thankfully, the fix for this is actually super easy. We can just do it the slower way, meaning let's get the component and update it. So let's get the selected, set it to true, and then instead of updating the array, let's go entity manager and call set component data on this entity array on this index, and let's update it with this selected component. And we do that instead of this. Okay, that's it, let's test. Okay, here we are, let's select a bunch of them, it works, deselect, and yep, it also works. No more errors, so I can select, deselect, select one, deselect, and yep, everything works. Okay, great. Now for the selection logic, let's go down to where we are selecting our units. So here we are selecting multiple and selecting a single one. So for example, let's go over here on the selecting a single one. This one's going to be super easy. So on this one, entity manager, let's get the component data. Get the component data of type selected for the Raycast set.entity. So we want this entity selected. So that's the selected like this. And then we just update. So in this case, the unit is being selected. So on selected, set this one to true. And then again, entity manager, let's set the component data on this Raycast set.entity and set it with this selected. Okay, so that is going to update the single unit. And up here for updating multiple, up here is where we can actually do the exact same thing we were doing a while ago. Then over here for the multiple selection, let's do the exact same thing. So we're going to get the entity. In this case, it's on the entity array index I. Get that one and update it with this one. Okay, great. So this should be working. Let's save. And now let's test. Okay, so everything is playing. Let's select one of the units. So let's select this unit over here. And over here with the inspector on runtime mode, let's scroll down until we find our selected component. Yep, there it is. And right now the unit is neither selected nor deselected, so both events are set to false. And now if I go ahead and select that unit, yep, there you go, the unit is selected and the onSelect event, that one was indeed triggered. And finally for deselect, just click here. And yep, there you go, it got deselected and the onDeselect event did work. Alright, awesome. So here we can see that our events are indeed working. When we select, they get selected, deselect, we get deselected. Now the next step is to make it reset. So let's build a system that will do that. So let's go inside our systems, let's create a new entities, new iSystem. Call this the reset events system. And now on this one, let's keep just the update, so just like this. And here it's going to be super simple. So we just want to cycle through all the events and set them all back into false. So let's do a system API.query. Let's do a query. We're looking for the selected, and we're going to want to modify it. So ref rw for the selected component. So this is going to be our query. So let's do a for each the ref rw on the select component called selected in this query. Except again, remember we're working with nibblable components. So if we do this and then we update the events over here, if we do that, it is only going to reset the events on the ones that are currently selected. Whereas we want to also reset the on the select event. So instead of just including the ones that are just selected, instead let's add over here the option with present of the selected. So yep, this way anything that has a selected component will be included here. So now we just go with the selected, the value rw for reading and writing, and set on selected into false, and same thing for the on deselected. Okay, that's really it. Super simple, super basic. Just like this, the code won't work, it won't reset events. However, it won't exactly work like we want it to. So like this code is indeed going to cycle through every single selected component and will reset it, but it is not necessarily going to do that at the end of the frame. So now is a great time to look at the systems window once again. Let's hit on play and just see. So here we have all our systems. Let's look inside the update, the simulation system group. We have all of our systems. For example, here is the select visual, the unit mover, and here we have the reset event system. Now the order in this list, this one is very important. So basically this system is going to run, then this one, and then this one. So the code is going to run from top to bottom. However, note how this one is not at the end of the frame. We got lucky that the event just by default happened after these two custom systems, but it could have happened just before this one. I'm going to talk about how the system ordering is semi-random in a little bit, but importantly is we can actually manually modify the order. We can tell it to update before or after any system. In this case, it's already running after all of our custom systems. So the goal is to run at the end of the frame, but just for testing, let's say we want to run before the testing system. So here in our system, we can simply add an attribute, and we can write update, and we have two of them, update before, to run before a system, or update after. So in this case, like I said, we want to update before the testing system, so let's use this one. Then this one takes a system.type, meaning we have to write type of, and then the system name. So in this case, the testing system. Okay, yep, like this, let's see. And if there it is, look at that, it does work. So now our reset event system is running before the testing system. So with this, we can easily update and set it to update before or after any kind of system. And another thing we can do is look at these folders. These are what are known as system groups. So we can also tell our system to run within any of these folders. For example, like I said, the goal is to run our reset event system at the end of the frame. So we can place it over here inside of this one, inside the late simulation system group. Let's do exactly that. So here in the code, instead of the update before, let's use another one. Let's just write update in group. And same thing, this one takes a type. So let's write type of, and we want the late simulation system group. Okay, yep, like this. Let's save and let's test. And if there it is, our reset event system, that one is running inside the late simulation system group. And with this, we have indeed achieved our goal. It is running at the very end of the frame. So we have the update, this is where we run most of our logic. Most of our systems are going to go next to these ones. And by putting it on the late simulation, it is always going to end up after all of these default ones. Okay, so far so good. So we already have some code setting an event to true, and then we have another one that is resetting the event to false at the end of the frame. So all that's left is really just something to listen to that event in the middle. Now in this case, our main goal is to update the visual when the unit is selected or deselected. So let's go here onto the selected visual system. Right now, this update is running all the time. So on every single update, it's cycling through all the entities that are selected or deselected and always updating the transform. That's pretty wasteful, so let's make it only update when the state actually changes. So for that, let's make a different query. So we're going to have a for each. We're going to run through the selected, except instead of with disable, just with present. We want to run through every single entity that has the select component. And then over here, we just check if selected.valueRO, if the unit is selected. If so, then we're going to show. If not, then we're going to hide it. So this one is the on the selected, and on the unselected, we are going to do this. And if the events are false, we're not going to do anything. And over here, we can avoid trying to get this. So we only do that semi-expensive call. We only do this one if we actually modify the transform. So yep, that's it. This is the code. We can now get rid of these. So with this, it is still going to cycle through every entity that has a selected component. But if the state does not change, then it really just checks a boolean, which is a super fast operation. If nothing happens, then it is not going to bother running this relatively expensive call, neither to do this on the transform. Now let's just add some logs just to test that this is indeed working. So let's do a debug.log, except it is not the systems diagnostics debug. Let's use the unity engine.debug. Okay. And this one on selected, Make sure this one only triggers exactly as intended, and this one is the on deselected. Okay, that's it. Let's test. Okay, yep, so this is the logic. Now, we technically have one potential issue here that may or may not happen, but let's quickly test. So here we are looking on the console and nothing is happening. So just by default, we can see that code is not running on every single update. So if I click somewhere, nope, nothing happens. Only if I select one, yeah, there you go, it did select that unit. Now I can tell it to move, I can deselect, and yep, that one did work. I can select a bunch of them, yep, unselected, deselect, undeselected. Okay, so that's great, everything did work. But while it did work on my PC, it might not have worked on yours. That is because of over here the order in the systems. That order is semi-random, meaning it is not guaranteed to be the same across all PCs. But for every PC, it will always have the same order. That is what I mean by semi-random. So if on my PC, if I stop and I start playing again, I'm going to get the exact same ordering for the systems. On your PC, the order might be different, but it will also keep that order. Also note how what I'm saying here is related to the Unity editor itself, meaning if I were to make a build of the game right now, anyone playing in the build would get this system order. It does not change after building, only during edit time. So anyways, my point is that the order of the systems is not guaranteed. It might or might not have the order that we want. Since on the select visual system we are listening to the event, we need to make sure that this system runs before this system. And the easiest way to make sure that happens, and technically by default, like I said, by default systems will run over here. So since we placed this one on the late simulation group, by default we can assume that one is going to run before that one. And since the unit selection manager, since this is a mono behavior, it is not running on .swirl, that means that this logic over here, that one is going to happen before any of that logic. So technically over here we don't need to do anything, technically this should work, but still we should learn how to make it very specific to make this one run before this one. In the future we are going to have other dot systems that also trigger some events, and we need to make sure that whatever system is listening to those events happens after they are triggered, but before they are reset. So over here on the select visual system, let's just make it run before the reset event system. So up here, let's do the same thing. So update before, type of, let's update before the reset event system. Okay, just like this, let's test. And nope, it is actually not working. Here we can see an interesting warning. It says ignoring invalid update before attribute on the select visual system targeting the reset event system. The issue over here has to do with groups. Basically, you can only modify the ordering. You can only tell it to update before or after other systems that are within the same group. So the select visual system, this one is just in the simulation system group, but the reset event system, that one is on that one. So if we want to update this one relative to this one, it has to be running on the same group. So quite simply over here, we can just add both attributes. So we can add update in group on the type of, on the late simulation system group. So we do that one, make sure it updates in the group, and then make sure it updates before this one. So yep, this should work. Let's test. And yep, it does work. So there we have the reset event system, and over there we have the selected visual system. And we can see how the logic works. I can select some of them. And yep, visually it does work, it does update, it does fire off the event, and it only fires as many times as it should. Now deselect, now select that one, move that one, and so on. And yep, everything is indeed working perfectly. Alright, awesome. So here we have our nice data-oriented event system. It does not use delegates or objects or anything like that, but still achieves the same goal. We can have some systems do some logic just depending on some event. And by the way, let's get rid of these logs. So this logic is only going to run when the system is triggered. So this logic is only going to run when this event is triggered, and the event is always going to be reset at the end of the frame no matter what. By doing this, we also end up with the same decoupling benefits, meaning that, for example, over here on the unit selection manager, over here when we set this event to true, this script has no idea that something is listening to this event. Maybe it does, maybe it doesn't, it does not matter. This one just sets the event to true. On the reset event system, the same thing. This one does not care if anyone did anything with this event, it just sets it to false. In between, we can have or not have something that listens to those events and does some logic. In the end, we end up with something that works, select, deselect, and everything works perfect. Okay, so here we implement some really nice dots events. Our game's already looking quite nice, but so far all we have are really just our own units. It's finally time to add some enemies, so let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to finally create some enemies and define them as actually being some enemies. We're going to define a simple faction system so that we can have just a player and enemies, and maybe in the future we can add a bunch more factions. Okay, so far we have our units. We have the unit selection like you find in any RTS, so I can select individually or select a bunch of them and everything does work. But so far all we have are just these player units. There's really nothing to fight against, so let's do that now. For that we have two options. We can take this unit prefab and make the enemy prefab a completely separate prefab, or we can make the enemy be a prefab variant of this unit prefab. In case you don't know, prefab variants is kind of like inheritance in C#. So you can have a base prefab, then you can create a variant that extends that base and maybe override some settings. Now, since all our units are going to have quite a lot of similar components, let's go with that approach of using prefab variants. That way, whenever we want to modify something to all units, we just modify the base unit prefab and it applies the changes to both our friendly units and our enemies. Okay, so first let's actually rename this, call this the base unit. And now let's make a variant, and the way we make a variant is right-click directly on the prefab. Let's go into create and let's construct a new prefab variant. Let's call this the soldier unit. This is going to be our friendly. And let's make another variant. And again, right-click on top of the base unit. Do not make a variant of the soldier unit. Nope, make another variant of the base unit. So right-click. Let's create a new prefab variant. Let's call this the zombie unit. Okay, so we have our three types. Now for the differences, only the player soldier, only this one can be selected. So we can get rid of the select authoring from the base unit and from the zombie unit. So let's go on the base unit, and on this one, get rid of the select authoring. And also let's go inside the base unit. So let's double click. And over here, since it doesn't have the selected, it doesn't need this one. So let's also get rid of this one. But before we do, let's actually copy. So Control-C to copy it, let's delete it. And now let's go on the soldier unit. This one should have the selected. And yep, let's save the base unit. And on the soldier unit, Control-V and paste our selected. And yep, like this, all the settings should be already set up correctly. So the soldier has the selected mesh, and let's also make sure that the soldier has the selected authoring component. Again, not the base unit, just the soldier. And on this one, let's drag the select reference and put the show scale like it was on 2, just like this. So yep, like this, it should be correct. Let's go back out and save it. So on the base unit, this one does not have the selected, so it has the unit mover. Yep, all units are going to move. We've got the rigid body, capstone collider, and the unit authoring. Then on the zombie unit, it has exactly those same things. And on the soldier unit, it has those things, plus an override of an extra selected authoring component. So next, let's set up the zombie unit. So let's go inside the prefab. And over here, let's just modify the mesh. So for the mesh, instead of using the soldier aim mesh, let's use the zombie wonk mesh. Yep, that's the zombie wonk mesh. Just need to modify also the material. Instead of the soldier, let's go with the zombie material. And yep, there it is. There's our zombie. And so far, we don't need to modify anything else here. Then let's make it a little bit slower, just because zombies should be slower. So let's put a move speed of 3. Okay, like this, let's save the prefab, go back outside of it. And now let's just set up these ones over here on the world. So let's actually get rid of all of these. So delete them, because those were the base unit. We do not want to actually use the base unit. We just want to use the prefab variants. So over here, let's drag a soldier unit, drag it directly on top of the subscene. Again, make sure you put it on the subscene so that it gets converted into an entity. And now, yep, there's our soldier, and let's make a bunch more. So a couple more soldiers like this. Okay, we have a bunch of soldiers, and let's also drag a zombie unit. Again, drag it onto the subscene, and put the zombie over there. And yep, that should do it. Let's do a quick test to make sure everything is still working. So if you are playing, and yep, all of them are indeed working. So the soldiers, and I can also select them, I can move them around, I can select them individually or select multiple, and yep, everything does work. And on the zombie, if I try, nope, it does not work. I cannot select, which is exactly what we want. Okay, great. So far, everything is working correctly. So now let's make the actual enemy zombies. So for that, the first thing is, how do we exactly define that something is an enemy zombie? Or rather, we're eventually going to have multiple unit types, both for the player and multiple zombie types. So how do we define what is a player unit and what is a zombie unit? How do we define what exactly is the concept of a faction or a team? So the simplest answer, the simplest way to implement that is using a simple enum. So with that, then we have another question. Where exactly do we define and store that faction enum? Now we could make a component to just store the faction. That could work. But in our case, the concept of a faction is relatively simple, and all units will belong to some faction, all units and all buildings. So instead of a dedicated component, we can store the faction over here in the unit authoring component. Although for defining it, other things might also belong to a faction, like I said, buildings. So we want to have a field to define our faction inside the unit authoring component, but then we want to define the faction itself on a separate file. So let's do that, and this file isn't going to be a mono behavior or authoring or system or anything, so let's just make it over here on the scripts folder, create a brand new mono behavior script. Let's call it faction, and then over here we can get rid of all of this. We're just going to define a public enum, call it faction like this. And for our two factions, let's have friendly and zombie. Okay, yep, that's it, a super simple enum. This is the easiest way to define factions. So let's go ahead and save this. And then on the unit authoring component, over here on this one, let's just add a simple faction field. Okay, there's our faction, and let's make sure to expose it on the authoring component. So the same faction, and when we add a component, let's add the faction, go into the authoring and grab the faction. Okay, yep, this should do it. Let's save. And over here back in Unity, let's go to our prefabs. Again, there's no point in modifying the base unit. Let's just modify these two. So on the soldier unit, let's go ahead and make this one a friendly. And actually like this, it is going to inherit the one from base unit. So technically we can leave it like this, or we can actually force this to be an override, force it to always be friendly, even if we accidentally modify the base unit. We shouldn't really modify the base unit, but still, let's make sure this one is actually an override. And the way you do that is you really just force some change. So change to zombie, yep, now this one is in bold, meaning this one is an override, and now we can get back to friendly, and yep, now it has an override, and the override is being overridden as friendly. Okay, so that's the soldier, and for the zombie unit, let's change from faction into zombie. Okay, that should work. So now, anytime we want to check what faction a unit belongs to, we can simply grab the unit component and inside check the faction. Although sometimes it can also be useful to very easily look for friendlies or zombies. It might be useful to find certain objects through queries instead of having to cycle through every single unit and then check the data inside of this unit component. So in order to make it easier to query for friendlies or enemies, for that, on top of this, let's also make some simple tag components for our factions. So on the authoring, let's right click, construct a new model behavior script for the friendly authoring. And over here, this is going to be a super simple tag component. So just a public struct, call it just friendly. Let's implement iComponent data, just like this, no fields, and then the baker. So class baker, baker of friendly authoring, and we implement the baker script. Then over here, let's grab the entity, do get entity. As always, let's default it to dynamic, and then add component on this entity, a new friendly component. Okay, yep, super simple. Now let's also make the zombie authoring. So let's right click on the authoring, create the new model behavior script for the zombie authoring. On this one, let's do the exact same thing. So a public struct, call it zombie, iComponent data, simple tag component, and finally a baker class, baker of zombie authoring. Let's implement this one. And over here, as usual, get the entity equals our get entity. Let's add the component on this entity, a new zombie component. Okay, that's it. Let's save. Here, let's go on the soldier unit. And on this one, let's add the friendly authoring. Yep. Okay, this one will have the tag. And on the zombie unit, let's add the zombie authoring. Okay, so like this, both of our prefabs should be correctly set up. Let's do a quick test. So let's go over here on our testing system. And over here, let's do basically the same test that we had previously for the unit count. Let's count the units, except instead of this querying, let's just look for units with the friendly component. So just put friendly, just like this, friendly, and we don't need any of these. So let's get rid of all of that, just friendly like this, without the with present, just like this. Okay, so let's see how many friendlies are within our scene. Okay, it's saying 7, and let's see, so we've got 1, 2, 3, 4, 5, 6, 7. Yep, that is correct. And now let's swap it out for the zombie to check out the zombie tag. Let's see. And if this works, we do have just one zombie. All right, awesome. Okay, so here we created the concept of a faction. We also set up our prefabs and variants very correctly so that we can very easily have different types of objects. This is going to be super useful when later on we implement all kinds of different unit types. However, so far we still have no interaction between our soldiers and the zombie. They really just exist in the world. So let's handle logic for finding our targets in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to implement the logic for finding a target. Then after we find that target, later on in future lectures, we can actually shoot that target. Okay, so here we have all of our friendly units. We have the friendly ones that we can easily control, and over here we have a zombie. So both types, both factions already exist, but so far they are not interacting with one another. So let's implement some nice combat. Now for combat, before we actually do some kind of damage, the first thing we really need to handle is how do we find targets? So how does this unit know that this zombie is close enough to be attacked? Let's first handle that, finding a target for this unit. For that, let's make a simple find target system. So inside our systems, let's right click, create, go inside entities, a new iSystem. Let's call it find target system. And also for this system, we're going to need some data for the settings on how exactly we're going to find the target. Like for example, what is going to be our find target distance and so on. So let's make a component to handle that data. So on the authoring, let's go create a new model behavior script. Find target authoring. Okay, now with this authoring component, let's attach it to the base unit. So let's select our base unit, scroll down, and let's drag the find target authoring component. It's very important that we attach the base unit because all of our units are going to be able to find targets. We want the soldiers to find targets and also want the zombies to also find targets. Okay, so let's make our find target authoring component. For now, let's make it just a simple empty component. So a struct find target I component data. And for now, let's leave it just like that. Let's just do the Baker class. So as usual, let's get the entity, get entity. Let's make this a dynamic entity. And then add component on this entity, a new find target component. Okay, so far so good. We have our simple find target component. Now let's go over here onto the find target system. We don't need the onCreate, so let's just keep our onUpdate. And now on this one, let's think, what exactly does finding a target mean? It means cycling through our units, all the units that have a find target component. Those are the ones that should be looking for targets. We cycle through all of those, and for each of those units, for each of those entities, we're going to be looking for units that are nearby, and then also validating if it's a target. So soldiers should only target zombies, and zombies should only target soldiers. So over here, let's do our query. So system API, let's do a query. Now for finding a target, we're eventually going to check the target distance. So we're going to need the local transform. And this one, we probably only need to read it. So let's make it a ref.ro local transform. Then all the settings, those are all set up on the find target component. So let's also grab that one. Also ref.ro, just read for the find target component. And yep, with that, we should have our correct query. So let's just finalize this. So make the function, add the for each ref.ro, let's pass in the local transform, call it local transform. Then another one for the ref.ro, find target, call it find target. And let's also organize this, make this nice like this. In the system.query, let's add some new lines just to make it nice and clear, just like this. Okay, great. So we have our query. We grab the local transform. Let's just put this like this, the local transform in the find target. Okay, great. And now for actually finding the objects, for finding things that are nearby, near this unit, for that, we are going to be using a physics query. So we already saw how we did Raycast. Over here on the unit selection manager, we already use a physics query in order to do a Raycast. So to do that, first we grab the physics world singleton, then grab the collision world, and then call a function on it. So in our find target system, let's do exactly the same thing. First, we need the physics world. And over here, since we are inside a system, we can use the super helpful system API, which by itself already has an excellent get singleton function. So this makes it super easy to get the first singleton. So that's the physics world singleton. Let's grab this one. Okay, we have the physics world singleton, and then inside of it, we want to grab the collision world. Okay, yep, like this. By the way, it's important that I'm doing this outside of the for each, just so we don't waste any performance. We don't need to constantly grab this, so let's grab it just once and then cycle through all the units, okay? So now here, let's go inside the collision world. And the perfect one for finding units that are nearby, the perfect one in this case is doing an overlap sphere. This one will basically give us all the entities within a certain sphere area. So let's see the parameters for this one. It takes in a starting position. So for the position, that's going to be the position for this entity. So let's grab the local transform dot value ro dot position, okay? Then for the radius, this is essentially going to be the range. So for this, let's make a field on the find target component. So let's go on the find target, and over here, let's add that. Public float, call it range. Personally, I prefer the word range as opposed to radius. I think it makes a little bit more sense, especially in the context of finding a target. So okay, so here we have that, and let's just pass it in. Find target range equals authoring.range. Okay, so now on this one, we can use that. So find target, let's read it, read the range, okay? Next one we have is a native list of distance hit. This is going to be the list of all of the entities that this overlap sphere is going to hit. And once again, let's be smart about it. Instead of constructing a brand new list for every single for each, instead of that, let's construct just a list once and then reset it for every entity. So up here, let's make a native list of type distance hit. So distance hit list, let's construct a brand new one. And this one, as usual, let's make it temp so it gets automatically deallocated at the end of the frame. Okay, so you have the list. We're going to use this one. And also importantly over here, note how this has the ref keyword. So we need to make sure to include this. So ref for our distance hit list. And since this one is going to basically be reusing the list, let's make sure to clear it before we actually fill it up. Okay, great. And for our final one, finally, we have the collision filter. Once again, this like we already saw, let's do it so it only hits units. So you can do literally the same thing that we did over here on the unit selection manager. Just construct a new collision filter that belongs to all units and only collides with the units layer. So technically we could just copy paste this code. However, we should really not have multiple separate references to our units layer. That way, if we modify it, we would have to modify it in tons of different places. This one should really only exist in one place. We should not have any duplicated copy-paste code. So let's make a general class just to handle data like this. And before we create a new file, let's just save these. So over here on this one, let's comment out just so it compiles. And save this one as well, so save both these files. Okay, let it compile, and let's create a new one. So we're going to construct a new mono behavior. So let's go inside mono behaviors. Let's right click, construct a new mono behavior script. And this time let's call it game assets. This is the name that I personally really like for this class. Basically, this class is going to hold all kinds of assets and references. And this one is a normal mono behavior. So let's create a game object with the exact same name. Again, create the object outside of the subscene. Let's call it game assets. Let's drag the game assets component, reset transform, and open. Okay, so now in this class, we want to be easily accessible from anywhere. Usually the purpose of this class is to be an easily accessible library so that we can have with all the references that we need. So usually I like making this into a singleton. However, technically in this case, we don't really need this to be a singleton, but still let's do it just to be ready for the future. So let's make the usual singleton logic. So public static of type game assets, call it instance. Let's make with a public get and a private set. And then on the private void awake, we just set the instance equals this. Okay, there's our static singleton instance. And now the reason why I said it doesn't need to be a singleton right now is because we're going to make the units layer a constant, and constants do not require an instance. But still, this way this class is nicely prepared for the future. So up here, let's define a public const int for the units layer. In this case, we have unit layer 6. Okay, great. So now we have some data here. So back first over here on the unit selection manager, over here, let's refactor this code. Instead of using this local variable, instead of that, let's go inside the game assets and access the units layer. Yep. So now we can copy this code, go into the find target system, and on this one, let's define the collision filter like this. And we do use the game assets.units layer. So in case we want to modify the layer, we really just need to go into this class and modify this, and everything else will work. Okay, so let's uncomment this, and we can now include the collision filter on the last one on this one. And yep, that should do it. So now this will return true if it finds anything. And if it finds anything, if it finds at least one entity, if so, then the results will be populated in this list. So let's check if it is true. That means there is something within this area. And if so, then we basically just need to validate these entities. Again, keep in mind how here we are looking for the units layer, meaning this will actually collide with both friendly and enemy units. So we need to validate if they are a valid target. Over here, let's cycle through all of those. So for each of type distance hit in the distance hit list. Okay, we cycle through that entire list. And now for validating if it is a valid target, for that, we're going to define a valid target as essentially being the faction of the unit that we are cycling through here is an enemy of the unit that we are cycling through here. So that means we need to define what is the target faction. So let's go on the find target authoring component, and over here on this one, let's make a public faction, call it the target faction, and let's pass it into the baker. So target faction authoring.target faction. So now back in the find target system, over here we can now use it. So we can have the find target, and within that we can read and find the target faction. So now we just need to know if this unit over here, if this one does belong to the faction that is the target faction. If so, then it is a valid target. So we just need to know the faction of this one. So for that, let's go inside the system API. Let's get the component. Get the component of type unit. That's where we were storing our faction. And we want for distance hit.entity. So we want to grab the unit for this one. So unit, this is going to be the target unit. And then just check if target unit.faction, if it does match the target faction that we have in our find target component. If so, then this is a valid target. And yep, if it is, then we want to set this as our target. Now let's just do a quick test, just to make sure all this is working. So up here, let's do a debug.log on the distance hit.entity, and just make sure that, and here we have the usual error. For some reason, Visual Studio is importing system.diagnostics instead of Unity Engine. Okay, so we have that debug.log. And up here, let's just do a dash just so we can see which one is finding. That way we can see this message and then this message. Okay, so let's save everything. Make sure to save all the files, which by the way, the shortcut is Control-Shift-S, and it saves all of them. Okay, great. So now here, let's wait for it to compile, and we need to set up some components. So let's go into our base unit. And on this one, let's scroll down. And this one just needs to have the component. Okay, great. Now let's select the soldier unit. On this one, for the find target component, let's find targets within a range of something like 7 units. And this one, we want to target the zombie units. Okay. And then for the zombie unit, let's put the target range a bit smaller. Let's say just 5. And this one does want to target friendly units. Okay, so let's see if like this, if our logs are indeed working. Let's test. And okay, so by default, we're just seeing a bunch of dashes, so none of the units are finding any enemy. But as I move this unit closer, at some point this one should find the target. And if there we go, it does work. So one of those is indeed finding a target. And it is finding the target entity 182. Let's see if that's a zombie unit. And yep, there it is. Zombie unit is indeed 182. And if we get close enough to where the zombie also finds that one as a target, so let's go a little bit closer. And if there it is, it does work. So the zombie unit is finding 179. And if we select this unit, and if there it is, soldier unit 179. All right, awesome. So our logic over here is indeed working. Now we just need to figure out how are we going to store this target. And the answer is let's make a component just to store the target. We want to make a separate component as opposed to putting it inside the find target, just because other things are going to have different methods of finding a target. So let's have a component just to define a target. Let's go in our scripts on the authoring, right click, construct a new model behavior script, call it target authoring. And if this one is actually going to be super simple, let's make a public struct, call it target I component data. And for this one, all we want is have a target, and let's make it of type entity. So that's the target entity. And then let's make a baker, so public class baker, baker of type target authoring. However, this one is going to be basically just an empty baker, so let's implement that one. We do not have any data that we want to pass in from the authoring component onto the target. This one is just going to be set dynamically. So up here, let's just get the entity equals our get entity, and let's add a component on this entity, a new target component. Yep, just like this, we do not pass in anything. Okay, let's save. Back over here, let's add the target onto the base unit so that all units have a target. So up here, let's drag the target authoring. Okay, great. And now we can go over here on the find target system. And when we have a valid target, let's just assign the target. So on our query, let's add another one. We want to write to it. So let's put a refrw of type target. And let's add it over here on the query. So refrw target. Okay, so now down here, we set the target, grab the value rw to write, and the target entity will be distanceHit.entity. Okay, yep, like this. Let's get rid of these logs. So like this, it should already be working. Like we saw the target logic, that one is already working. So now we should be able to see the target being assigned on the target component. So yep, let's save. Okay, here we are. Let's select just the first unit. Okay, there's the soldier. I believe it is this one. Yep, it is moving over there on the local transfer. So it is this one. Okay, great. Now let's scroll down, find target component. Okay, let's see the target component. And if there it is, and right now it has none, it has no target. And as I move a little bit closer, as I get close enough, yeah, there you go, the zombie unit now is the target. And if we select the zombie unit, and now we look, let's find the target component. There it is, so far no target. And as I move a little bit closer, and if there you go, it does find the soldier unit as the target. All right, awesome, so everything is working perfectly. The soldier finds the zombie as a valid target, and the zombie finds the soldier as a valid target. And of course, this is working for all of these, so if I get all of these way too close, if so, and I inspect any of them, pretty much all of them are going to have down here on target, yep, they do have the zombie as a target. Okay, so our find target logic is working great. Although let me point out just one small thing. Here, as you might see, we are doing a for each, cycling through all the distance hit. And I do not believe that this one is going to be ordered by distance from the target, meaning I don't think that as we go through this for each, the first one is going to be the closest one. So technically, if we want to find exactly the closest target, if so, we need to add some extra logic here to make sure that the target that we select is indeed the closest. But for now, this is working more than fine enough. As soon as we find one target, let's break out of the for each. And so far, this should be working. Okay, great. So the find target logic is working. Our units are finding targets. Soldiers find enemies, and enemies find soldiers. Let's just add one more tiny thing over here to this logic. Basically, one of the best tips that I can give you on performance, one of the best tips related to either dots or game object, doesn't matter. It's a great general performance tip. So that tip is simply run logic less often than on every update. Now here, after we implement jobs and burst, after we do that, this code will actually be insanely fast. So technically we don't necessarily need it, but still we also don't really need to check for a target on every single update. The units move relatively slow, so there's no point in looking for a target 60 times per second. So let's add one of my favorite things, a simple flow timer. Let's do that to make sure we only find targets a few times a second and not on every single update. That is a super simple thing, so let's go on the find target component. And over here, let's just add two floats. So let's define a public float for the timer and another public float for the timer max. And for these two, really the only one we need to set is the timer max. The timer will set at 0 and then increase automatically. So let's just bake the timer max and set timer max, authoring.timer max. Okay, great. And over here on the find target, before we do any of this complex logic, before that, let's just go inside the find target, grab the value RO for reading. Let's grab the timer and we check if the timer is above 0. So if this timer is above 0f, if so, then basically timer not elapsed, meaning we do not want to find targets. So over here, let's basically short circuit this. So let's just do continue to continue onto the next entity. But of course, before this test, let's actually count down the timer. So since we're going to modify it, we need ref rw on define target. So let's modify this to ref rw. Okay, let's go in define target value rw so we can write timer minus equals system API dot time dot delta time. Okay, we count down the timer, then we check if it is elapsed. If it is not elapsed, then we just continue. We ignore this entity. But if not, let's reset the timer. So find target dot value rw. Let's set the timer equals find target. Now let's just read value ro and grab the timer max. So yep, that's it. And over here, let's add a log just to verify debug.log. Find target, just make sure this one is not being called 60 times per second. So let's save this, save both files. And now we just need to assign the timer max. So over here, let's select the base unit, scroll down to the find target. And for the timer max over here, let's put it on 3F, meaning it is only going to look for targets once every 3 seconds. So yep, let's play and see the logs. Okay, there it is. And right away they found the target, and now they are not finding, and now they found again, and now they are waiting, and in a little bit, yep, find some more, and so on. All right, awesome. So our simple timer logic is working perfectly. So let's put now a more proper number, so something like 0.2. So basically it's going to find a target 5 times per second, which I feel is more than enough. Okay, great. So now that we can find targets, the next step is to actually attack them. Our soldiers, those are going to be using bullets. They're going to be shooting them. So we need a system to handle that. And then we also need a component to store some data. So let's do the same thing that we did for the find target. Let's first make a component to store some data. So create new model behavior script. Let's call it shoot attack authoring. However, here we have an interesting thing. Not all units are going to shoot. Like our soldiers, they are going to shoot. They have a weapon. But the zombies, they are only melee. So in this case, we do not want to attach this component onto the base unit. That would make it so that every single unit can shoot. Nope, we just want it on the soldier. So on the soldier, let's scroll down and let's drag the shoot attack authoring. Okay, great. Now here on the script, let's make the standard component. So public struct shoot attack. This is an I component data. Okay, great. And let's make the standard baker. So public class baker shoot attack authoring. Let's implement this baker. Get the entity, get entity dynamic, add component on this entity, a new shoot attack. Okay, great. Now let's think, what data do we need? Well, the first thing is we do not want to shoot a bullet on every single update, so we need some timing logic. So let's do the same thing that we just did for the find target. Make a float for a timer and a public float for a timer max. And the only one we need to pass through is just the timer max. So let's pass through this one, go inside the shoot attack, open and close. This one equals authoring.timer max. Okay, like this, let's save. Okay, so here let's see the soldier unit, scroll down, find the shoot attack, yep, this one. And let's put it something like 0.2. So it's going to shoot 5 bullets per second, which should be a nice amount. Okay, so that's the data. Now let's make a system to handle our shooting. So on our systems folder, let's right click, let's construct a new entity, system. Call this the shoot attack system. And now here on this one, we want to cycle through all the entities that have both a target and a shoot attack. So let's do that. First, clear up these ones. And on the on update, we're going to want to do a system API.query. Query for everything with a shoot attack. And we want to update the timer. So let's do it a refrw for the shoot attack. And then for the target itself, let's make it refro. We're just going to read the target, just our target component. Okay, let's put this inside a for each ref rw of our shoot attack, call it shoot attack, and also for the ref ro for the target, and simply call it target. Let's just format this nice like this, and put this one and this one like this, close the parentheses, open and close. Okay, great. So now we're cycling through all the entities that have a shoot attack and a target. However, all the soldiers are going to have this target component, but that does not mean they actually have a target. So the first thing we need to do is check if the target actually exists. So for that, we can do an if. Let's go inside the target. Let's read the target entity. And we can basically compare this against a nice constant. So let's see if the target does not equal and the constant entity.null. This one represents a null entity. So essentially represents that we have no target selected. So here, let's actually put if it is null. If it is null, then we want to skip this. So continue. If it is not null, then we continue doing something. So down here, let's first count down the timer. So the usual thing that we just did a while ago. So let's grab the timer minus equals. Let's go system API.time.time. And then if the shoot attack, let's read it. Let's read the timer. If the timer is still above 0, then not elapsed. So let's continue. And if it isn't, then shoot attack. Let's grab the value RW for writing and set the timer equals the shoot attack. Let's read it, value RO, and grab the timer max. Okay, so that's it. So now down here is where we actually spawn some bullets, deal some damage, something like that. We're actually going to spawn the bullets in a little bit. In order for those bullets to deal some damage, we also need to implement an actual health system. But for now, let's just do a quick test, just to make sure this is working. So debug.log, and once again, this implemented system.diagnose, that is not what we want. So let's do using Unity engine. So do a debug.log and say just shoot. Okay, let's see if this log does show up. And over here on define target system, let's just get rid of this log. Okay, so let's test. Okay, so here we are, and no one is finding targets, no one is shooting. So now this one, as this one approaches, it should find the target and then should start shooting. And if there you go, shoot 5 times per second. All right, awesome. Okay, so here we added the logic for being able to find the targets. So our entities look for units around it and define if that unit is a valid target. If so, then it assigns it as a target. And actually, I only noticed that we have a bug with our select visual right now. So the bug is if I select all of these, sounds good. Now if I select the exact same units, now it looks like they are deselected. But if I move, yep, they are still selected. So it's a very simple bug. It's over here on the select visual system. Basically, if we select the units twice, if so, then both these events are going to be true at the second time. And if both are true, then it's first going to select and then it's going to deselect. So the super simple solution is just swap the order. So first handle deselection, and then if the unit is both deselected and selected on the same frame, if so, then it will have the visual. So if that's it, let's save, let's test. So now here, if I select a bunch of units and now select them again, and if there you go, now they do always show up as selected very correctly. Okay, great. And another bug that I also just noticed right now is if we click to select the zombie, yep, we have this error. Basically, the error is over here on the unit selection manager, where we have the logic for selecting just a single unit, where this one does the cast ray and so on. Then checks if it has a unit component, and then automatically assumes if it has a unit component, then it can be selected. Whereas that's not the case. The zombie is a unit, but is not selectable. So up here, let's just add another entity manager. Let's check if it has component, and let's check if it has the selected component. So raycast hit.entity. So this way, it is only going to select if it's a unit and is a selectable unit. So yep, let's save, let's test. Okay, here we are, and if I click on the zombie, and if there you go, no more bugs, everything works great. All right, awesome. Okay, so here we implement the logic for finding a target. So the units look for units that are nearby. They identify if that unit is valid, so if it is part of a target faction. And if so, then they assign it as a target. So it works for both the soldiers as well as for the zombies. And then the soldiers also have some shoot logic. They check if the find target was successful, if they did find a target. If so, then they count down a timer and they start actually shooting the enemies. So all that logic is working, except we don't have any kind of concept of health. So that means we need to build some kind of health system. So let's build that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to implement a really nice health system. When the unit is close enough, it will be shot and it will count down the health. Then when the health hits 0, it will destroy that unit. Okay, so we already built the shoot attack system. So as this soldier unit gets close, it will eventually find the target and start shooting. So as I move a little bit closer, yep, there you go, finds the target and starts shooting. Okay, great. So we already have this logic working perfectly. All it really needs to do is just deal some damage. So to define some health, let's make a health component. So on the project, let's go on the authoring, right click, construct a new model behavior, call it health authoring. Now let's make this one a simple component. So public struct, call it health, I component data, and let's make the standard baker. So baker of the health authoring. Let's implement the baker function, grab the entity get entity as dynamic. So the standard thing that we already did so many times, add component on this entity, a new health component. Okay, yep, just like this. So now what data do we need for the health? Well, the simplest thing is just some kind of health amount. So let's make it public. And now it's up to you to define what format you want to define for the health. Some people like to use decimals, so they like to use float. Personally, I prefer using ints. I think they'll look a little bit better. Let's call it health amount. Okay, so we have the health amount, and let's pass it in. So up here for the health amount, let's pass it into our health component. So this one equals authoring.health amount. Okay, so let's save this. And now back into unit. Let's select our base unit prefab. Let's attach to this one so that both soldiers and zombies, both of them have health. So let's go ahead and drag the health authoring, put it like this. And for now, let's just default all of them to have 100 health. Okay, that's good. Now we can go back on the shoot attack system. And over here where we are doing our shoot, over here, let's just deal damage to our target. So for that, first we need to grab the health system of the target. Now it's important, it's the target, it is not the one that we are cycling through here. So if we have a soldier shooting a zombie, over here we are cycling through the soldier entity, but down here we want to deal damage to the zombie entity. So let's first grab the health. So let's go into the system API, let's get component. In this case, we're going to want to modify the health of the entity. So instead of using this one, which just grabs the component, instead let's use this one, which actually returns a refRW. That way we can then very easily modify the amount. So this one, let's grab of type health. And for the entity, let's go inside the target. So the target for this one, let's read the target for the target entity. And this one is going to return a refRW of type health for the target health. And now we can simply deal some damage. So let's define an int for some kind of damage amount. And for now, let's make it just 1. Then let's go into the target health, grab the value RW for writing, and the health amount just counted down by our damage amount. Okay, so that should really do it. That should already be damaging our zombie. So let's save, and let's do a quick test. Okay, here we are, and let's just select the zombie unit, and let's inspect the health component. So let's see, where's the health? If there it is, we have the health amount of 100. Okay, now I take one of these soldiers, and as I move them close enough, they should start shooting. And if there you go, the health of the zombie does start going down. Okay, great. So this is working, the health amount is counting down, but let's see what happens when it hits 0. And yep, that's it. The answer is nothing happens. Basically, we need some way of handling unit death. So one way, we could handle it here. So after here, we can test, is the health amount under 0? If so, destroy the unit. Or as always, we can do it in a dedicated system. Both options can work. In this case, the better option is to use a dedicated system, just so later on we can have more options for things that can deal damage. So let's make a new system. Let's go in the systems folder, right click, a new entities iSystem. Let's call it the health dead test system. Okay, so now this one, let's make our standard update like this. Now this one, we need to do a query for all the health components. So system API.query, let's read the health. So refRO of our health. And that's probably the only one that we need. So let's just say for each refRO on the health like this. So the health. Okay, we have just one component. We cycle through on the health and then just check if the health value RO, the health amount, if that one is under or equal to 0. If so, then this entity is dead. So this is where we need to destroy this entity, which means it's actually a great time to learn one thing, which is how exactly do we get the entity reference? Here we are doing a query and we get the component of the query, but we don't actually get whatever is the entity that this component is attached to. If we go inside the health, nope, we have no reference to any of that. There's no reference to any entity. Even on the value RO, we still have no reference to the entity. So over here on the query, we are just getting components, and we can't really just write entity over here. This does not work. This is not valid code, but thankfully it's actually pretty easy. So after this, we can cycle through all the various options that we already saw, and one of them is called with entity access. So we use this one, and in doing so, then we need to add another parameter over here on the first iterator. So let's have the health, and then we have an entity parameter. Let's just comment out and format this properly. So let's put it like this, and put the N with a query like this. Okay, so yep, like this, it is working. So basically by calling this, you then have to add this entity field. And importantly, it needs to be at the end. We cannot place this one in the beginning. If I try putting that in the beginning and then the health afterwards, nope, this is not valid code. So if you use with entity access, you need to put the entity as the last parameter. So like this. Okay, great. So with this, we now have the entity that we are cycling through. Now we can just simply destroy it. And for destroying, we need to access the entity manager. And while working inside a system, over here, note how we have this system state. And if we access that state, inside there, we have the entity manager. So that is the entity manager where this system is running. And within that entity manager, we can call the function destroy entity. So like this takes an entity, so let's destroy this entity. Okay, yep, that's really it. However, this will throw an error, but let's try it anyways just to see. Let's save it. So here we are. Let's select the zombie so we can see it. Let's inspect the health of the zombie. Okay, like that. Let's approach with a bunch of soldiers. And they are close enough. They are shooting. And yep, the health is counting down. So let's see what happens when it gets all the way down to 0. So there you go, like that. And yep, we have an error. Here it is. It is saying structural changes are not allowed while iterating over entities. And then it says here, please use an entity command buffer instead. So again, the error is because destroying entities is what is known as a structural change. I already talked about what those are a while ago. I mentioned why we use an enableable component for the selected instead of adding or removing components. So here it's really the same thing, except instead of modifying the components, instead of adding or removing, instead of that we are destroying an entity, which again is also a structural change. When we destroy an entity, that means that dots on the back end has to reorganize all of the memory arrays. They always all need to be tightly packed. So if one entity is destroyed, it needs to move all the other entities in memory. Now if we do that here inside the for each, not only is it a costly operation, but it actually breaks our code in this case. We cannot be cycling through something and then basically modify that collection. Now the solution here is actually quite simple. We don't really need to destroy the entity immediately right here. Instead, we can essentially queue it up for destruction. So we can do all our health testing logic, we can identify which entities should be destroyed, and then after doing the for each, afterwards, then we can actually destroy those entities. So the way we can queue up commands is with something known as an entity command buffer. That's basically a buffer for queuing up entity commands. And for using an entity command buffer, we have two options. We can manually create a brand new one, or we can choose one of the ones that already exist. Let's see both options. So first, let's see the manual one. So up here before our for each, let's construct a new entity command buffer. For that, we do new entity command buffer, just like this. And this one, as so many things, takes an allocator, so allocator. And let's use the temp like we're used to. Let's just add the using statement for these up here. So using unity.collections, okay. So we have the entity command buffer, so like this. And then down here, when this entity is dead, instead of destroying it instantly through the entity manager, instead, let's just destroy it on the entity command buffer. So up here, let's call destroy entity, and let's destroy the exact same entity. Again, importantly, this is not actually destroying the entity right here. It is simply queuing up that command. And then down here, after we exit the for each, over here, let's access our entity command buffer, and let's call playback. And this one takes in an entity manager. So let's pass in state.entity manager, and yep, like this, it won't work. So we construct new entity command buffer, we queue up some commands on that buffer, and then we tell it to playback, which essentially means that the entity is going to run all of these queued up commands, and is going to execute them on this entity manager. So this way, we are no longer destroying entities in the middle of the for each. We simply queue them up and then destroy them all. Okay, so let's save and let's test. Okay, here we are. Let's approach the unit with all of these. Let's see the health amount going down. Okay, it's all going down, 60, 50, going down to 0. And yep, it did work. We did not have that error. If we look in the entities hierarchy, we can see, yep, the zombie unit is no longer existing. So that's great, that part worked. But we did have a different error. Like it says here, the entity does not exist. So we are trying to do something with an entity that does not exist. Basically what happened is the entity was destroyed, but then we still tried to do some logic on that destroyed entity. That's why we have this error here. And also, by the way, this is a great time to see something very important about debugging. Right now, if we select this error and we look down here, we can see this error log, this stack trace looks very strange. Look at all of these very strange names for the functions, for the class names, the lines, and so on. All of this looks super strange, and none of the links are clickable. So for example, over here, I can see some error happened on the shoot attack system, and usually you can click on this in order to go to the offending line. But right now we can't really see that. This has to do with the fact that we are using burst. Now burst makes it super fast. It applies tons of optimizations to your code, which makes them insanely fast. But at the same time, the downside is that it makes it quite a bit hard to debug. So if you're having trouble debugging something, then the simplest option is really to just disable burst. So let's stop playing. Let's go up top to jobs, burst, and let's not enable compilation. Okay, let's play again, and let's trigger the exact same thing, get them all close enough to shoot. And now let's wait for that unit to be destroyed and throw the error again. Here's the error again. And yep, now with burst being disabled, now the errors are much more easily understandable. They are easily understandable, and now we can actually click on it. So we can click and see the error was on the shoot attack system, line 28. So let's go inside this one. And up here is shoot attack system on line 28. So if you're having trouble debugging something, just go ahead and disable burst. Also, by the way, remember to re-enable burst after you solve that bug. Also here, we can see another very interesting quirk about how dots works. Like I said in the very beginning, dots works very much based on source generation, meaning we write a bunch of this code, and then dots, the dots compiler, is going to run through this code and going to add a bunch more things. So in between you writing the code and the final compilation, the code runs through a system which adds a ton more code onto your code. That is why we have to mark this as partial. So as to why that matters, is over here in the code we can see the error is on the shoot attack system on line 28, but over here on line 28 we are just defining a local variable. This line cannot possibly throw an error, so the error is actually not on this line, it's actually on this line over here. So it's on line 27, not 28. Now this is a little quirk of dots that it's very important for you to know. Because of source generation, the lines can look a little bit off. So it might tell me that the error is on line 28, but it might be on 27, 29, or any of the ones that are nearby. So if you are confused, keep in mind that the offending line might not exactly be the offending line. So if you have some error and you don't know what exactly is causing it, make sure you look at the lines nearby, not just the exact one that it's telling the error. Okay, so anyways, now that we've learned that, let's actually solve this error. So basically the problem is, like I said, is that the unit is still trying to attack an entity that no longer exists. So basically, as you cycle through multiple units that are shooting the same zombie, eventually one of those units is going to destroy the zombie, which then runs the health data test system, which is going to destroy that entity. But then the next time this one runs, the other entities that still have a target, the target is not null, it is simply pointing to a target of an entity that has since been destroyed. So we basically need to validate the data that we have inside the target component. And again, we could write it directly here, or we can make a dedicated system to do that. So let's do that. On the systems, let's construct a brand new, go into entities, a UI system. Let's call it reset target system. And for this one, let's cycle through everything that has a target. So doing a system API, doing a query, let's read and write on the target component. So for each ref rw on the target and call it target. Okay, we do that like this. So we cycle through all the targets, and then in here we can just validate the target. So if target, let's grab the value ro just for reading, grab the target entity, and we can basically check, does this entity still exist? So the way we do that is we can go through the system API and call the function exists and check if this one does exist or not. So if this one does not exist, if the target has since been destroyed, then let's simply reset it. So let's target value rw, set the target entity equals entity.null. And if that's it, this one won't clear the target. Now, the only important thing is we need to make sure this one runs at the end of the frame. And actually, I'm going to cover that specifically in a little bit after we see the alternate approach to this entity command buffer. But now let's just make it work. So let's just write update in group. So the same thing that we saw previously, type of on the late simulation system group. Okay, like this, let's save. So here, let's approach. Let's see if that one works. Let's see if the zombie gets destroyed. And if it did work, the entity was indeed destroyed. Now, it might not look like it, but it was. If you look over here on the entities hierarchy, we can see, yep, the zombie unit no longer exists. However, we still have a bug, which is the visual mesh. That one was not destroyed. We're going to handle that in a little bit. But the important thing right now is that we did destroy the main entity and it did not throw any errors. Okay, so before we solve that visual bug, let's just learn more about the entity command buffer. So here, this code is working. We made it work by using a custom created entity command buffer. This works. However, another option, which actually works best, is to use one of the preset entity command buffers. If we start playing the game, let's pause and let's look over here in the systems window. And if we scroll down, we can see we have a bunch of entity command buffer systems. So there's one over here on the begin simulation and one over there on the end simulation. Basically, we can reuse this one instead of creating a new custom entity command buffer. The benefit of this approach is basically to limit when you do structural changes as much as possible. So rather than a bunch of systems all doing structural changes in multiple places in the same frame, instead of that, we can all run all of those commands just at the end of the frame. So the way we do that is we access that entity command buffer, and that one only exists once, so that is going to be a singleton. So let's go through system API, call get singleton, and the type that we want is called end simulation entity command buffer system. And now here an important thing, it is not just like this. Nope, we need to access through this one and access the singleton that exists inside of this one. So yep, that gives us the singleton. And now within, we can call the function create a command buffer, and this one just takes in a parameter for an unmanaged world. So for that, we can access the one inside state.worldUnmanaged. And if that's it, so this will now give us an entity command buffer, so let's use that instead of creating that one. So yep, just like this, we do this, we queue up the commands as usual. And then the important thing is we do not manually call playback. Again, like I said, this one will run automatically at the end of the frame. Okay, so just like this, let's test. So here we are, and let's look over here on the entities hierarchy. So we have the zombie unit, and we have a bunch of soldiers. They are attacking the zombie, and the zombie's health going down. And if there you go, the entity was indeed destroyed, and no more errors. All right, awesome. And over here for the health data testing system, let's also put it to update on the late system group. All right, now let's solve the issue with the visual here. Basically, the parent object, that one is being destroyed. However, the child object, the one that contains the visual mesh, that one is not being destroyed. Now, this is actually a very strange bug that took me quite a lot of trial and error to figure out during my research. Basically, it's a weird bug that only happens to units that are placed directly in the scene during baking. If we were dynamically spawning this unit, if so, then this bug would not happen. That is what took me quite a long time to figure out. I will show in a little bit how this bug does not happen when we cover unit spawning, but for now, let's just solve it. And thankfully, the solution is quite simple. We just need to go into our prefab, and yep, and over here, we need to add a component. And it's a component called linked entity group. And if that's it, basically if you dynamically spawn a prefab, it is automatically going to add this component onto it. But if you don't dynamically spawn it, then it doesn't add it. So that is a very strange thing. But just by adding this, we should have the bug fixed. So let's do another quick test. And let's get the units close enough to destroy. And after a while, we should be able to see the zombie and the visual mesh destroyed. And if there it is, it did work. The zombie's gone and the visual mesh is also gone. All right, awesome. So now everything is perfect. Here we constructed a brand new health system and added the logic for damaging and destroying the target. Although our shoot logic isn't really shooting anything just now. There are no visual bullets, just an integer going down. So let's add that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to create some bullets. We're going to create the bullet object and the system. It will basically move towards the target and deal some damage. Okay, so we already have the shooting logic working. As the units get close, they find the target, they automatically find the zombie target, they start shooting, and yep, after a while, the zombie takes some damage and gets destroyed. So all the logic is working, the health is working, the find target is working, the shooting is working, all of that works. But right now there's no visual, there's no actual bullet. So let's do that. First, let's construct our object. So on the subscene, let's right click, construct a new empty game object, call this the bullet. Then inside, let's make a child object, let's make it a sphere. And on this one, on the inspector, let's put it on authoring mode, and let's get rid of the spherical either. So we just have a visual. And for the visual itself, let's go ahead and choose this bullet material. So yep, there it is, just a nice material with a little bit of glow. If you want, you can increase a little bit. So if you want, you can go over here on the emission, increase the intensity if you want to make it really glowy. I think something like this looks pretty good. And for the visual size, let's also make it a little bit smaller. This is way too big. Let's put it maybe something like 0.4, 0.4, 0.5, something like this should be good. Okay, great. So that's our basic bullet setup. Again, we have an empty parent game object where we're going to place the logic components and then a visual in a child object. Okay, let's actually rename this one to mesh. Okay, so now on the bullet, the goal is to spawn the bullet from the soldier's weapon and move it towards the target. And when it gets there, it will finally deal damage. So let's make a component to handle the data for our bullet. Let's go into our authoring components and create a new mode of behavior. Call it the bullet authoring. Okay, so now on this one, let's make the usual thing. So public struct, call it bullet. It's an I component data. For now, let's make it empty. Then a public class baker. Let's extend baker on the bullet authoring. Let's implement this class. As always, grab the entity, get entity, make it dynamic so that the bullet can move. Add component entity, new bullet like this. Okay, great. Let's go ahead and save. And back in Unity, let's attach it. So here on the bullet object, let's attach the bullet authoring. Okay, great. So now here, for what kind of data does our bullet need? Well, we're going to need some kind of speed. So let's make a float for a speed variable. And then we're also going to need to know the target in order to know how do we reach the target. So for that, let's store an entity for the target entity. We can do this, store the target directly inside there. Or alternatively, we can just reuse our target component. Both options work just fine. Let's reuse the target one. In case we need some more custom target logic, then we can add it here, but we can also reuse the component, so let's do that. So we have the speed, and let's also define a public int for some kind of damage amount. That way we can have bullets that deal very little damage, and others that deal quite a lot of damage. Okay, so now let's go ahead and pass these in onto the baker. So let's go for the bullet, set the speed, authoring.speed, and the damage amount, authoring.damage amount. Okay, great. So let's save this, and here in the editor, let's set it up. So for the speed, let's put it relatively slow just for testing. So let's put 2, and for the damage amount, let's say 5. Okay, that's great. Now let's also add the target component. And actually for debug purposes, we want to be able to drag a target, again, just for debugging, just for testing. So let's go inside the target here, and let's actually pass in the target entity. But again, in order to pass in an entity, we actually need a reference for a game object over here. So make it a public game object for the target game object. Again, this is just for testing. After we have our testing done, then we're really only going to set the target by using the actual target entity. But over here, target entity, let's call get entity, pass in the authoring component, grab the target game object, and call it dynamic. Okay, so you have it like this, let's save. And now by default, let's give the unit, let's give it the zombie unit game object. Again, just for testing, just so we preset an object for the target. But of course, later on, when the units themselves, when they spawn a bullet, they won't give the bullet the actual target entity. But for now, like this should be good. Let's just add one more thing to prevent that visual bug. So over here on the bullet, let's add the linked entity group. So let's have this one so that when the bullet is destroyed, the visual destroys with it. Okay, so great. So here is our bullet. The setup is all correct. We have all the data. Now let's make a system to do some logic on this data. So let's go in our systems, right click, construct a brand new entities iSystem. Call it the bullet mover system. In this one, let's first keep just our update. Okay, so on update, let's do a system API.query. Now we want to move the bullet. So first, let's grab the local transform, and then we need the data from the bullet. So let's grab the ref RO. We just need to read it for the bullet component. Okay, just these two. So let's do a for each on the ref RW local transform. Call it local transform. And then ref RO for the bullet and call it bullet. Do this in that query. Let's just format it. So put it down there, break it on the in, then on the query, break on this one, close the parentheses, open and close. Okay, great. So here's our query. Now first, let's actually move the bullet, which means we need to calculate the movement direction, which also means we actually need the target. So let's also add that one. So the ref RO for the target component. So let's grab this one, put this one for the target, and then let's calculate a float3 for a move direction. And by the way, float3 is inside unity.mathematics. Okay, so for the move direction, we need to know the target position. So let's go through the system API, call get component. Let's grab a local transform, and it's going to be the local transform of the target. Let's read the value and grab the target entity. Okay, so this returns a local transform for the target local transform. So now we can grab this one, .position, minus the current local transform of the bullet, .valueRO.position. So with this, we get the move direction. And of course, this move direction is going to have some magnitude. So let's make sure to normalize it. So equals math.normalize, and let's normalize our vector. Okay, great. So here we have the move direction. Now to move the bullet, local transform, let's grab the value RW for writing. And for the position, do a plus equals on this move direction, multiplied by, let's go inside the bullet, read the value, grab the speed, multiplied by system API.time.delta time. Okay, that's really it for the movement. We calculate the move direction based on the target position and the current position, and with that move direction, then we just move the unit so that the bullet goes from the start position until the target. Then let's just do some logic for testing when to reach the target. So for that, we can access the math library, and in there we have the distance. We have two functions for this. I talked about this a while ago, but let me mention it again. Like the name implies, one of them gives you the actual distance in actual units, whereas the other one gives you distance squared. So it's the same thing as the length versus length squared that we saw quite a while ago. It is really the exact same logic. Basically, when calculating the distance, you are actually going to get the square by default, and then you need to do a square root of whatever this returns in order to get the final distance. But doing a square root, that is a little bit costly, so technically, if you don't need the actual distance number, you can just use the square. In this case, we don't really care about the distance, we just want to compare it with a number to know if we are close enough. So let's use the distance squared and compare the distance between two of them. So let's say the local transform.valueRO.position and the target local transform.position. So we check distance and basically check if distance is close enough to destroy. So let's define a float, call it destroy distance squared, and let's put it 0.2f, that should be close enough. So if the distance is under this, then we want to destroy this bullet. But before we do, let's actually damage the target. Now this is actually a bit of a game design question, which is, do you want to deal damage on the shoot attack system like we were doing? Or do you want the shoot attack system to just spawn bullets and then the bullets themselves are what deals damage? Basically, both options can work perfectly fine. Now, since we already saw this one about the shoot attack system doing this, let's put this on the bullet just to be a little bit different. So on the bullet, we're really going to do the exact same thing, so we can actually just copy this. And on the bullet mover system, okay, the bullet is close enough. So let's say close enough to damage target. So we get there, we grab the target health. Yep, then for damage amount, instead of defining a local one, we define that on the bullet. So bullet, RO, damage amount. And yep, that's it. This one is going to deal damage to the target. And then all that's left is actually destroying this bullet. But again, creating or destroying entities is a structural change. So let's make sure to use an entity command buffer like we saw previously. So up here, let's find an entity command buffer, and let's go into the system API. Let's get the singleton, and the singleton of type the n simulation entity command buffer system dot singleton. Again, don't forget the dot singleton. So you grab this one, call create command buffer. This one requires an unmanaged world, so that's on state dot world unmanaged. Yep, so this one gives us the entity command buffer. So then down here, after we deal damage, let's call destroy entity, and we want to destroy the bullet entity, so let's add it up here onto our query. So with entity access, this means we need to add the entity over here. So this is going to be the bullet entity, and yep, this is exactly the one that we want to destroy. Okay, so that should do it. Our bullet mover system should be nice and workable. So we do a query for local transform, bullet, and target, which yep, our bullet has all of these. Then we grab the target position, calculate the move direction towards it, move the bullet towards the target, then check the distance squared, if it is close enough, if so, deal damage to the target, and then destroy this entity. So yep, like this should be working. Let's save. And over here in the editor, just make sure you assign over here the zombie unit as a target. And now we can test, and we should be able to see the bullet move. So let's test. And if there it is, the bullet is moving towards the target. Let's move these away. And as it gets there, yep, it does indeed hit the target. Let's just make sure it's actually dealing damage. So start playing. Let's pause. Let me select the zombie unit. Just look at it. So on the inspector, let's look at runtime mode. Let's look at the health amount. Okay, 100. I just need to move these out of the way. So move them out of the way. Okay, and let's see 100. And bullet gets there, and yep, 95. All right, awesome. So our logic is indeed working perfectly. However, we have a bit of a sneaky bug here. Right now it did work, but if we set the bullet speed as super fast, So let's go on the bullet on the authoring. Instead of 2, let's put it 100 so that it's super fast. And then over here for the destroy distance, instead of this, let's use a really tiny number, like tons of zeros. Okay, like this. So destroy distance is going to be super small, and the speed is going to be super fast. So let's see exactly what is the problem here. Let's test. And if there it is, look at that. The bullet goes towards the enemy, and look at that, it is constantly jumping back and forth. So look at that, it is constantly jumping. It does not actually destroy. It is bouncing back and forth. It is not actually hitting the enemy. It is not actually dealing damage. Sometimes it might randomly hit, but as you can see, it bounces around quite a lot. Now, this is a common issue, and basically the problem is that it's overshooting the target. Basically, the problem is that the bullet is over here on this side, and then on one frame, the bullet is going to move a massive amount, which means it ends up sort of on this side, but this point is not close enough to destroy. So the next frame, it is going to move another massive amount in this direction, and again, it is not close enough to destroy, so it moves another massive amount, and so on. Basically, the problem is that since the bullet moves so much in a single frame, and the target distance is so small, it constantly jumps back and forth. It never actually gets close enough in order to hit and destroy itself. So this is the problem with very fast moving projectiles. Now the solution to this is basically we need to test to make sure the bullet is not overshooting the target. Now there's one very simple way to test for that. As the bullet gets closer to the enemy, we can just compare the distance towards the target. We compare the distance towards the target, compare it before moving and after moving. And basically if the bullet was closer before than it is after moving, if so, then we can assume the bullet has overshot the enemy. So over here, let's do that. So we grab the target local transform, then let's grab the float, call it distance before, and let's grab the square distance. Do a math.distance squared, and we're going to do distance just like we saw, so the local transform towards the target. So let's do exactly this distance. Okay, so we get that. Then we calculate the move direction, then we move the unit, and then we calculate distance again. So this is the distance after. Calculate before, move, calculate again. And then we can just check if the unit, if this bullet did overshoot the target. So if the distance after, if after is bigger than the distance before, if so, then we have overshot the target. And if so, then we can just place it directly on top of the target position. So local transform, let's set the value RW, let's set the position equals straight on top of the target. So target local transform dot position. So yep, that one goes straight on top, and then even if this distance is super tiny, if so, it is still going to trigger this and run this logic. Okay, great, so yep, let's save it and test. So let's hit on play and see, and if there you go, even though the unit was moving insanely fast, it still managed to hit the target. So even if over here we put a giant amount of speed, so like 10,000, which guarantees this is definitely going to overshoot the target, even so, yep, there you go, and we can verify, we can look on the zombie unit, and yep, we do see this zombie did take damage. Alright, awesome, so that's our logic fully working. Now let's just put some proper numbers on there. So let's go back into the bullet. Let's put a speed of something like 60. And over here for the destroy distance, let's put it 0.2. Okay, let's save. And let's play and see the bullet move. And this move does deal damage. Alright, awesome. So this is working, the bullet is working perfectly. But naturally, we don't want to manually place some bullets. We want our soldiers to be able to spawn them. So this means it's actually time for us to learn how to dynamically instantiate objects and dots. This is quite simple, but does have one interesting quirk. So let's learn how to do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to dynamically instantiate some entities. We're going to have the soldier spawn the bullet, which will then move towards the enemy and deal some damage. Okay, so in the last lecture, we already created the bullet entity. If I hit on play, the bullet starts moving towards the enemy, hits the enemy and deals some damage. So now let's leave that with the exact same behavior, but spawn it from the soldiers. For that, let's go here onto the shoot attack system. And here, instead of dealing damage instantly, instead of that, we want to spawn a bullet. Now, spawning an entity is actually quite simple. We just need to access the entity manager. So here inside a system, we can access the state, and from the state, access the entity manager. Now from this, we can call instantiate. So just like you instantiate a normal game object, you can instantiate an entity. But of course, the question is, how exactly do we get a reference for the bullet object? Normally, when writing normal monobehavior code, I would just expose some kind of field. Then in the editor, I would simply drag the prefab reference. But systems in ECS, they do not have any game object in the world, so there's really nothing for us to drag a direct reference. Then of course, there's also the fact that we have to go through the bake process. Here, we are not instantiating a game object, but rather an entity. So we need to take the bullet prefab, bake it into an entity, and then we get the entity that we can use over here. So one solution is to make a component that takes a game object field and converts it into an entity. And we could do exactly that, make a specific component just to store the bullet prefab. But as we're going to be making this entire game, eventually we're going to need to reference various object prefabs that we're going to spawn, like the soldiers, the zombies, the bullets, and so on. So instead of just one specific component for each object type we want to spawn, Instead of that, let's create a component to store a bunch of entities references. So let's build that. In the authoring, let's right click, create a new MonoBehavior script. Let's call it entities references authoring. Okay, let's just clear our error. Over here, let's just comment out this code just to make sure the code compiles. Okay, let it compile so we have our component. And on the entity subscene, let's construct an empty game object, call it entities references. And I like to put it up here, so let's just drag it up to the top of the hierarchy. And now let's attach the entities references authoring. Okay, so now let's open this. Over here, let's write the normal stuff. So a struct entities references implement I component data, and then make the baker. So class for the baker of entities references authoring. Then let's implement the abstract class. Let's get the entity, get entity, get it as dynamic. Then add component on this entity, new entities references. Okay, great, just like this. Now with this, over here on the entities component, let's add an entity field. So public entity, let's call it bullet prefab entity. Yep. And now up here on the authoring component, let's add a public of type game object. And this is going to be our bullet prefab game object. Okay, and now we do what we've already seen. So down here on the entities reference, let's set that one equals get the entity of the authoring component dot bullet prefab game object with dynamic. Okay, yep, just like this. Let's save. Now here in the editor, let's just drag our reference. So we've got the bullet, which actually means we need to make it into a prefab. So let's drag it onto the prefabs. And on the bullet itself, let's get rid of the one over there. And now on the entities reference, let's drag the bullet prefab. Okay, so far so good. Now back here on the shoot attack system, so we've got the code for calling instantiate. And over here, we just need to reference that entity. So here's another important question, which is how exactly do we get that component? Now we can't really add it here. This is the query that is cycling through the units, and the units do not have the entities references component. So we can't just add it over here on the query. But the goal that we did with this entities references, this is basically just a single component that exists on a single entity that in itself is going to contain all the references that we need. So since there's just a single one, that means this one is going to be a singleton. And like we saw previously, System API has a really useful function called getSingleton. So with this, we can very easily get it. So let's get the entities references. Let's get it just like this. Entities reference equals down. Okay, so with this, we can easily get it. And then down here on the instantiate, let's go inside and grab the bullet prefab entity. All right, awesome. So this is going to spawn our bullet prefab. Let's just define an entity for the bullet entity. Okay, now all we need to do is actually initialize it. So first, let's actually position it on the correct position. So let's just do system API call set component. And we're going to set the local transform component on this bullet entity. And we can actually use one of the helper functions inside local transform. It has a bunch of functions like this one, from position. This one basically takes a position, returns a local transform filled in with that position, 0 rotation, and 1 on the scale. So since once again we use our nice trick of having an empty parent game object that has a scale of 1 by default, and we only modify the scale on the child object, because of that we can use this one. So from the position, we just need to know the position from where to shoot. So let's set it as the position for this unit. So let's modify over here the query. Let's grab a ref ro local transform. We grab this one and let's put it over here. Local transform. Okay, we have that. And from that one, grab the value ro and grab the position. Okay, so this is going to initialize the position. Next, let's set up the bullet component. So let's go on the system API. Let's get the component rw of type bullet for this bullet entity. So it returns a ref rw of type bullet. So this is the bullet, bit of a strange name, but it makes sense. Okay, so then on this one, let's go inside the value rw and let's set the damage amount. So as to where we get this damage amount, let's store it in the shoot attack component. Let's put it over here so that different units with different shoot attack components can deal different amounts of damage. So up here, just an int for the damage amount. And then we just pass it through. So add it on the authoring component. And then over here, that one equals authoring.that. Okay, great. So now back on this one, let's initialize the bullet. Go inside the shoot attack, value ro just for reading, and let's read the damage amount. Okay, so that's the bullet component setup. We probably don't need to modify the speed. We can probably just leave that one with the speed that the prefab has. So final thing is really just a target. So system API, let's get the component rw. In this case, it is going to be the target component, and it's going to be that for the bullet entity. So this returns a target for the bullet target. And then we go inside this one. Actually, this is a ref rw. So then we go inside this one, value rw, and set the target entity. And it will be the same target entity as the one on this unit. So let's go into the target. This is the unit's target, value ro, and grab the target entity. Okay, yep, just like this should do it. So here we are spawning the bullet entity. Then we are setting it to have on the position from the same as this unit position. Then we set up the bullet by setting the damage amount, and we set the bullet target by setting the target entity. So yep, just like this, let's test. Okay, here we are. Let's grab a unit. Let's get it close enough and see if it starts shooting. And if there you go, it does indeed start shooting towards the target. All right, awesome. However, I actually forgot to assign the damage, so right now the bullets are dealing 0 damage, so let's fix that. So on the project, let's select the soldier unit, and down here for damage, let's put it 5. Okay, great, let's test. So here we are, let's select one of these, move there, and start dealing damage, and yep, and after a while, it should kill the zombie, so let's see. And if there you go, it did shoot the zombie. All right, awesome, so that did work. But now let's actually see one interesting thing. So instead of one, I'm going to shoot with a ton of them, so we have tons of bullets flying around. So there you go, tons of bullets, and as soon as the zombie dies, yep, there you go, we have an error. The error is saying the entity does not exist. Now this is actually basically the exact same issue we already encountered on the shoot attack system. Here on the bullet mover system, this system assumes that the target always has a valid target. But of course, if the target is set as null, then this one is going to throw an error. So we need to check against null, so let's check if the target.value_RO, if target entity equals entity.null. If so, that means the target is now dead. And if the target is gone, then over here on the shoot attack system, we're just continuing. But on the bullet, we really don't want it to continue. If the target is already dead, then this bullet is no longer going to do anything. So if the target is dead, we want to destroy this bullet. So let's use the code that we have down here for destroying an entity. Let's destroy this bullet right here, and then just do continue. Okay, so let's test. So here we are, let's pick a bunch of these, get them all close so they all shoot at pretty much the same time, and if there you go, it does work. So they all shoot a ton of bullets, and they all get destroyed if the target is now dead. And actually, let's just solve one bug that I just noticed right now. It has to do with our reset target system. So over here, if we play and if we have multiple units, all of them shooting bullets, all of them firing towards the enemy, if there you go, we eventually have an error. It says the entity does not exist. And this error is coming from the bullet mover system. So basically the issue is that the bullet mover system, this one the bullet still has a target, but the target has since been destroyed. So what is happening is actually a very strange thing. So basically on frame 1, the bullet moves, the bullets hit the target, destroy the target. Okay, great. Then the help that system test, that one runs. That one eventually queues up the entity for destruction on this one. And then on the next frame, the entity still has a target because the reset target system, that one does not reset the target because it is only destroyed afterwards. So then the next frame, the bullet mover system runs and still has a target, and that throws the error. Except that is not just the error, it is actually a bit more complex than that. Technically, if that were the error, we could put the reset target system, put it at the beginning of the frame, and that could work. So let's try doing that and see. So over here on the reset target system, instead of updating on the late system group, trying to update it at the end of the frame, which again, it's only actually going to reset on the command buffer, which happens way at the end of the frame, so even after this one. So instead of doing that, let's pretty much reset the target on the beginning of the next frame. So we can put this on the simulation system group, and then we can use order first and set that one into true. So like this, it should run pretty much at the beginning of the frame. Okay, let's see like this. So let's test and pause. And yep, we can see the reset target system is running at the beginning of the frame. Okay, so let's see if it still throws that error. So they all go, they all shoot, destroy, and nope, we still have the error. So even though we technically fixed that, the error still exists. So on frame 1, the bullet moves, it hits the target, it destroys the target, then the help that system, that one is going to destroy the entity, or rather it queues that up, and the entity is actually destroyed in this one. But for some strange reason, on the next frame, when we reset and come back over here, for some reason the entity actually still exists. It was queued up for destruction, but it still sort of exists. The entity still exists, and it's actually only over here on the parent system when the entity is sort of destroyed. So by the time we get to this one, technically it thinks the entity still exists because the target was not reset, but the entity no longer exists, so again, we have an issue. Now this is a very, very strange thing. I have no idea if this is a bug. We can add some logs here just to verify exactly what I'm talking about. So let's do entity engine, debug, do a debug.log. Let's print out the name of this system, and let's also print out the time, the unity engine.time, and let's print out the frame count, the frame number. So let's print this one, and then over here, let's also print if the unit actually exists. So unity engine, debug.log, and let's print if this unit exists. So let's see this, and then also let's go onto the bullet mover system over here. Let's do the same thing. Let's also print in order to see in which frame this system is running. And then over here, let's do the same thing. So let's see if the entity still exists. Let's test that out on this one. Okay, so let's see like this. What exactly does it say? Okay, here we are, and let's shoot and kill the enemy. and find the error. Okay, the error happened, and now let's look at our logs. And yep, here we do see these strange things. So on reset target system, the target still exists, but then on the exact same frame, frame 497, on that one the target no longer exists. These false, by the way, this is actually just entity.null. We can verify that. Let's just print out the entity, just make sure we are talking about the same thing. So print out the entity like that, and same thing on the bond mover system. Over here, print that one. Let's see everything. So let's move the units, attack the target, and let's see, fire the error. There you go, there's the error, and now we can definitely see. Okay, so on the reset target system, so previously it makes sense that the unit does exist. Unit 196, that's the zombie. And that one does exist, it does say as true, so the entity does exist. And now let's see over here, so on frame 495, on this one the entity still exists, so it still does exist. And then on the bond mover system, again on the exact same frame, for some reason in between this system and this system, all of a sudden the unit stops existing. So basically when this runs, it does not clear the target because technically it seems like the unit still exists. But then down here at the end of the frame, on the exact same frame, the unit no longer exists. I've done some testing and it seems like the thing that actually destroys the unit is over here, the parent system. I have no idea why that one is specifically the one that is actually destroying the entity, but there's actually one more very strange thing. Let's add another log here to verify another thing. Let's call system API that has component of a local transform on the same target entity. So target value RO, target entity. Okay, let's print this to see if this target entity has a local transform component. Let's print it out on this one and also over here on the target. Okay, so let's see what both these say. Let's go ahead and shoot them all. Okay, there's the error. Now let's look at our logs. And okay, so frame 493, that's when we have the error. And if we look at the frame before, on 492, yep, the entity still exists and it does have the local transform component. Okay, makes sense. But then on the reset target system, so on this one, the entity technically still exists, but no longer has that component. So this is why I'm saying this is very strange. I have no idea if this is a bug or not. The entity should really be destroyed on the previous frame, but it doesn't. But then for some reason gets queued up for destruction and only the parent system actually destroys it. So anyways, this is all very strange. So the entity that exists, that one seems to behave very strangely, but we can basically use has the component of the local transform, use that as a sort of proxy. So over here for the reset target system, we're going to reset the target if the entity no longer exists or no longer has a local transform component. Since the targets are always going to have local transforms, we can assume that if the local transform is gone, that means because the entity is also gone. So over here on the reset target system, let's just add that logic. So we're going to reset the entity, reset the target entity if system API, if the entity no longer exists, or the entity no longer has a local transform component. So that one or that one. If it is either of those, then the entity will reset to null. Another thing is, here we are running this code all the time, even when the target entity is null. So that makes no sense, that's just wasting a bunch of performance. So up here, let's check if target entity is not entity.null. If it isn't, then we do this, but if it is null, then the entity is already not assigned, so we don't need to do anything. Okay, so like this, finally, everything should be working. We should not have that error, and our reset target system should now be behaving correctly. It should be 100% resetting the target at the beginning of the frame. So over here on the bond mover system, we can get rid of our logs, and yep, let's save everything. And now let's test. So here we are, let's move, have all the units shoot at the zombie, destroy the zombie, and yep, there you go, no more errors. Alright, awesome. So this was very strange, but we figured out a solution to our problem. We set the reset target system to run at the beginning of the frame, and we added some extra logic. Instead of just checking if the entity exists, which seems to behave very strangely, instead of that, we also check for the local transform, and that does seem to work. So the bullets move, the bullets hit the target and damage the target with a health below 0. Then this system runs and queues up the actual entity for destruction. Next, this entity command buffer system, this one runs and supposedly actually destroys the entity. And then on the next frame, this one says that the entity technically still exists, but does not have a local transform component. So we use that to basically invalidate the target. And then when this one runs, it no longer has a target, so everything does work. So very strange, but now all the code is working. Okay, so here's an update that I'm recording later on. I believe I have figured out the reason why this is happening, thanks to a comment from a student. I believe the issue has to do with cleanup components. These are special dots components that will basically keep an entity sort of half alive until they are manually removed. The transform system uses a cleanup component, so that's why the entity stays sort of alive until the transform system runs on the very next frame. Only at that point does that system finally remove the cleanup component for the transform, which then finally allows the entity to destroy itself. So if I'm correct that this is what is happening, then this is not a bug. It is working as intended. It looks a bit strange as to how the entity is destroyed in the middle of a frame, but it does make sense based on this. Essentially, the entity is only destroyed when all the cleanup components are manually removed. So if while working in your own DOTS projects you encounter this issue with entities being sort of half dead, half alive, if so, then remember this, remember all about cleanup components. Okay, awesome, so our bullets are working perfectly fine. They spawn, they move towards the target, deal damage, and destroy themselves. However, we have a bunch of annoying issues. For example, one issue is how the bullet is actually spawning from the floor. Look at that, it's spawning from the floor instead of spawning from another. The other issue is that the unit is not looking at the target, it is looking away while shooting. So let's solve a bunch of these issues, let's do a bunch of improvements for our shooting logic, and let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture we're going to take the bullets that we implemented in the last lecture and fix a bunch of tiny things. Okay, so the bullets that we made, they are all working correctly in terms of logic. So if I take a unit and I get it close enough to the enemy, yep, the unit gets close enough and starts shooting, so it does work. The bullet spawns, moves toward the target, deals damage, and destroys the target. So the logic is working, but we have three odd things. So the first thing is how the unit isn't really stopping. So I move and the unit is shooting and moving at the same time. Secondly, it is not rotating to face the target. And thirdly, the bullets are spawning right from the character's feet instead of from the weapon. So let's solve all of those issues. First, let's handle the stopping. So let's go here onto the shoot attack system. And on this one, we scroll down. And right now we are always attacking. So if the entity has a target, it always attacks. Technically, we should probably define an attack distance so that we can have a different find target distance and attack distance. That way our units can find targets from far away, but can only attack when they're a little bit closer. So let's go here onto our shoot attack component, and let's add an attack distance. So public, make it float, call it attack distance. Okay, like this, and let's put it on the authoring component, and let's bake it equals authoring.attack distance. Okay, great. So then on the shoot attack system, on this one, let's check if it is close enough to attack. For that, we need the target position. So let's go system API, let's call get component, get the local transform component, local transform of the target. So target is going to be target value ro.target entity. So we got that one. So this is going to be the local transform of the target local transform. And then with this one, we can calculate the distance. So math.distance, it is math, not mathf. So this one, which exists inside the namespace unity.mathematics. So this one call distance, or actually distance squared. Since on the find target we already have the actual number, then over here let's also use the actual number. So let's use just the regular distance. So there's going to be distance between this local transform dot value ro dot position and the target local transform dot position. So distance, if distance is close enough to attack, let's put this in an if this distance, actually let's test if it is too far. So let's test the shoot attack value ro and let's grab the attack distance. So if so, then that means the target is too far, so let's move closer. And with that, let's tell it to move closer. So let's also add another component. Let's add our unit mover. So we add this one for the unit mover. And in order to tell it to move closer, let's just go into the unit mover, set the value RW, set the target position to be the target local transform.position. Okay, so yep, so like this, if it is too far, it will move closer towards the target. So let's just move closer, do not shoot, and let's continue. Else, so if it is not far enough, if so, then over here it's close enough. So let's stop moving and attack. And for stop moving, just go into the unit mover, and let's write for the target position and put it the same as this local transform dot target position. So yep, simple math, calculate the distance from this unit towards the target. If it is too far, let's tell the unit mover in order to move closer. But if it is close enough, then let's stop moving. Tell it to go to exactly where it is already. Stop moving and then shoot. Okay, this should do it. So let's save, make sure to save both files. Okay, let's test. Okay, so let's just assign the value. So let's go in our soldier unit and over here, let's see. So for the find target authoring, for this one, we set the find target, let's put it on 8. And then for the shoot attack, let's put it on 7. Okay, let's see. Okay, let's start, let's begin, pick up one of these units. And if I move close enough, yep, there you go. It does go there and it stops moving and starts shooting target. Okay, so now the unit does stop while shooting. And now you might have also noticed something interesting. Here, if I take one of these units and I tell it to go there, it gets close enough to shoot. Now I pretty much can't move away. While the unit is still within range, I cannot move. That's a bit odd. Basically, the unit is getting stuck while shooting and I can't really move it much. That's obviously not ideal, but so far that is actually correct. Later on, we're going to make a component to override the movement so the player can still manually tell it to move even when there are targets in range. So later on, we're going to solve that. But for now, let's leave the behavior like this. So if the unit is within range, stops moving and starts shooting. Okay, great. And just one more thing, like you saw, I could actually move a little bit. That is because this logic is only running after the timer. So if we put this just before, that makes a little bit more sense. So instead of testing just 5 times per second, if it is close enough, instead it's going to test all the time. So with that done, now let's solve the second problem, the rotation. So up here, let's just rotate towards the target. And that is going to be pretty much the same logic that we used on the unit mover system. So first, let's calculate a float 3 for, let's say, the aim direction. And the aim direction will be the target local transform dot position minus this local transform value RO dot position. That gives us the aim direction. Let's just normalize it. So this one equals math dot normalize. Let's normalize our aim direction. And then to rotate this one, so local transform, let's set the value RW. We're going to need that. So let's actually modify this one from ref RO to ref RW to modify the local transform. Okay, so then over here, let's grab the value RW. We're going to want to modify the rotation. So for this, like I said, let's do exactly like we did on the unit mover system. So let's define some kind of target rotation. So quaternion target rotation. And we're going to go into quaternion and call look rotation. Take this aim direction to calculate that vector 3 into a quaternion and use mathf.up. Okay, that gives us the target rotation. And now for smoothly rotating, let's use math.slurp. And let's slurp from the current rotation local transform value ro.rotation towards this target rotation. And by the time will be system API.time.onTime multiplied by, let's go inside the unit mover, grab the value RO and grab the rotation speed. Okay, yep, so just like this, the unit should be rotating to face the target. So let's save and let's test. Okay, here we are. Let's pick one of these units. And now if I move a little bit closer, and if there you go, I can't move away and the unit is indeed facing the target. Okay, great. Now for the third problem, the issue with the shoot position. So right now, the bullets, those are being spawned from the origin of the position and goes towards the origin of the zombie. So it spawns from there and hits the floor instead of being spawned on the weapon and hitting around the center mass. So we want to modify how they are spawned. We want to basically have some kind of offset. We need an offset for both the shoot point as well as for the target hit point. So first for the shoot position, we can go here into our shoot attack authoring and we can add basically that offset. So let's make a public float 3 for the bullet spawn local position. Okay, we have this. And then on the authoring component, here we actually have an interesting question that relates to dots. Remember how in the beginning we learned how authoring components do not have to perfectly match dots components. So here, technically we could define a float 3 that would work. We would have to manually write the number in the editor, or we can actually do something a bit more user-friendly, which is let's just use a normal transform field. That way we can easily position an object using a transform during edit time, but then during runtime, everything will be baked into a super fast float 3. So yep, let's do exactly that. So up here, make a public, make it of type transform for the bullet spawn position transform. And then on the baker, we just set bullet spawn local position, go inside the authoring, grab that transform and grab the local position for that transform. So yep, that's it, perfect. Now we can easily just position a transform. Also note, very important how we're grabbing the local position, not the global position. This is extremely important. We want to store the offset of the shoot position, not the global position whenever the prefab is baked. The prefab or the unit itself, after being spawned, that one is going to move. So that is why we do not want to store the global position. Instead, we want to store the local position. Okay, so now let's set this one up in the editor. So let's go inside our soldier unit prefab. There it is. And now inside, let's right click, let's construct a brand new empty game object. Call this the bullet spawn position. And now with this transform, let's just manually position it roughly on the tip of the weapon. So something like that, just position it, put it a bit more to the side. Make sure it looks good from all angles. Yep, pretty much like this. Maybe lower it a little bit, just like that. Okay, perfect. And now on the soldier unit, let's scroll down, find over here the shoot attack authoring, and we just drag our normal transform. So you can see how it is much easier to be able to manually position a transform in world space. That is much easier as opposed to coming here and having to write X, Y, and Z. So this is a great example of how using an empty game object is much more user-friendly than having to write numbers directly. It's a great example of how different authoring and runtime data can be quite helpful. Okay, so now let's exit, go back, save the prefab. Yep, that makes sense. And now let's go here on our shoot attack system and let's see to where we are spawning the bullet. So right here, we are spawning the bullet on this position. So now we can go inside the shoot attack. We can grab the value RO to grab the bullet spawn local position. But again, this one is in local position. We need to convert it into a world position. And the way we do that is we access the local transform. So that is going to be the transform for this unit, for the actual soldier. Let's grab the value RO. And on there, we have a super useful function called transform point. And this one is basically going to convert the local position onto a world position. So we use this. We pass in our local position just like that. And that gives us the bullet spawn world position. So a float 3 for the bullet spawn world position. And then we spawn it directly on this position. Okay, yep, just like this. Let's save, let's test and see if the spawn is spawning on the correct position. So here, let's just make the bullets a little bit slower, just so we can easily see. So let's put with a speed of just 5. And over here on the scene view, let's position it something like this so we can easily see if it is spawning. Okay, so let's test. Okay, let's pick up one of these units, push it over there, get it a little bit closer and see. And yep, there you go, it does work. So the bullets are indeed being spawned from there. Okay, great. So all that's left is the target position. We do not want it to shoot at the zombie's feet. We want to shoot sort of center mass. And now for this one, we don't already have any component that makes sense. Now technically we could place it, for example, on the unit component. We could add the offset on there, but that would be a bit odd because not every unit is necessarily going to be shot. So it makes more sense to have a dedicated component, one that just stores that position for that purpose. So let's go ahead, make another authoring component, create new mono behavior. Let's call it shoot victim authoring. So this is data for the shoot victim. Then over here, let's do the usual stuff. So first let's make the struct, call it shoot victim, implement I component data. And then over here, let's make the Baker class, Baker of type shoot victim authoring. Let's do it like this. Let's implement the Baker class. Let's do entity, get entity of dynamic entity, add the component on this entity and new shoot victim. Okay, great. And now let's do literally the same thing we did on the shoot authoring. So we have a local position and then a transform. So over here for the component, let's do a public float 3, call it hit local position. And then on the authoring component, a public transform for the hit position transform. Okay, we have that. And then over here on the component, set the hit local position equals, go inside the authoring component, grab that one. And again, importantly, grab the local position. Okay, yep, just like this. So now here in the editor, let's go inside the zombie unit. And now on this one, let's right click, construct an empty game object. Call this the hit position. Let's move it a little bit up, so just like center mass, and then let's drag the reference. We need to attach the shoot victim authoring and drag our hit position. Okay, yep, let's save, let's go back. And now let's go here to the bullet mover system and scroll down, and we're getting the target local transform, and we're basically using that position as a target. So let's refactor this. Let's define a float 3 for the target position, and let's just refactor all of these instances. So find this, instead of using that, let's use the target position. Okay, they're all sorted. So now we just need to assign this. So target position is going to be the same thing that we saw previously. So first let's actually grab the shoot victim component. So shoot victim of the target, shoot victim, so target shoot victim. Then we go inside the target local transform, grab, do a transform point. A transform point, target shoot victim dot hit local position. This one is actually going to be a float 3, not a float, and yep, just like this. Okay, this should do it. Let's save and let's test. Okay, so here we are. Let's put them a bit far away. Let's put it like this so we can see it side by side. Okay, so as I move the unit closer, as it gets close enough to shoot, and there you go, it does work. So the bullets spawn from there and they hit on center mass. Then you also made it rotate to face the target, and we also made it stop moving. All right, awesome. So all of this is working. Now let's just give the bullet some proper settings. So over here on the bullet for the speed, let's put it back on 60. Then on the soldier unit, let's make it have a bit more interesting values. So for the find target, let's put it something like 15. Then for the attack distance, let's put it on like 13. And for the shoot attack timer, yep, 0.2 makes sense. So shooting 5 times per second. And same thing for the find target, 0.2 also makes sense. Okay, so yep, now our shooting and all the logic, all of it is looking really nice. So we have a bunch of units, they find targets, they move, they start shooting, and everything does work. So this is great, but what would be more fun would be to actually have some more enemies to shoot. So let's build a super simple zombie spawner in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to build a super simple zombie spawner. This is going to be a quick lecture because we have already learned everything we need to do. This is going to be an excellent example about how after you learn how dots works, it becomes actually relatively simple to build brand new systems. Okay, so far here we have our soldiers, we have zombies, I can approach with the soldier, and yep, there you go, starts attacking the zombie and eventually kills the zombie. So yep, all of it is working perfectly. We've got the soldiers, we've got bullets spawning, everything works. So now that we have the bullet spawning working, let's also spawn some enemies as well. Like I said, the logic is going to be very similar to what we already did, so this is going to be an easy lecture. First, let's begin by making our authoring component to store some data. So a new model behavior script called the zombie spawner authoring. Then over here, let's write our normal code. So we have our zombie spawner. It's going to be I component data. And then let's make the standard baker class. So baker, let's bake zombie spawner authoring. So not the zombie. Okay, this one. And over here, same thing as always. Entity, get entity. Let's get a dynamic entity and add component onto this entity, a new zombie spawner. Okay, great. So now let's think, okay, what data do we need over here? The goal is to spawn a zombie and to spawn a zombie every certain amount of time. So let's store a float for a timer, another one for a timer max. And on the baker, on the authoring class, over here, let's expose the timer max. And when constructing the zombie spawner, let's set that one. So timer max, authoring.timer max. Okay, just like this, let's save. And now over here, let's make an entity. So inside the entity subscene, create the new empty game object for the zombie spawner. And over here in the world, let's place it over there on that corner. Okay, great. Then let's attach the component. So let's put the inspector back into authoring mode, add the zombie spawner authoring, and let's put the timer at something like 1.5. So we want to spawn one zombie every 1.5 seconds. Okay, that's the data. Now let's make the system to run this. So in our systems folder, let's go ahead, create a new entities system called the zombie spawner system. And now here, let's first get rid of these. We just need the on update. So let's do our on update. And now let's do system API.query. And for handling this logic, first we need to have the local transform so we know where to spawn the zombies. Let's do refro local transform. Okay. And then we're going to need our refrw for the zombie spawner. Okay, that should do it. So let's put this inside a for each. For each, our refro local transform, call it local transform, and then refrw for the zombie spawner, call it zombie spawner. Okay, like this, let's just format everything. Refro, refrw. Okay, yep, here's our query. Now, first, let's do the usual thing. So count on the timer and reset. So let's go inside the zombie spawner, grab the value rw, and grab the timer, count it down by system API.time.delta-time. And then let's check the zombie spawner value. Let's just read the timer. And if the timer is above 0, if so, then the timer is not yet elapsed. So let's skip it. Let's continue. But if not, then let's run this code, go into the value rw and reset the timer. So set the timer back into the zombie spawner. Let's read the timer max. Okay, so this handles the timing logic. And then over here, we just want to spawn our zombie. So for doing this, it's pretty simple. We're just going to do the exact same thing we did for the bullet. So in order to get the reference, let's go up here onto the entities references authoring, and let's add another field. This is going to be for the zombie prefab entity, and then up here for the zombie prefab game object, and then let's paste both of them. So the zombie, pass in this reference as that one. Okay, great. So now back in the spawner system, over here we can grab that one. So the entities references, let's grab it, system API, get the singleton of type entities references. With this, we have our component, and then from this one, inside, we can simply grab the zombie prefab entity. So now for this, we can spawn it. So let's go in through the state.entity manager. Let's instantiate the zombie prefab entity. This will be an entity zombie entity. The spawn zombie, and let's just position it. So system API, let's set the component on this zombie entity. And the component, let's go inside the local transform, inside the type itself, and let's use from position and pass in this local transform, read the value for the position. Okay, yep, that's really it. This should be working. As you can see, super simple, all the exact same logic that we already did. So let's save both files. And here in the editor, let's just make sure to drag the zombie prefab reference. So that one, and yep, let's test. Okay, here we are. And yep, right away, we do see one zombie spawning, another one spawning, and another one. So yep, that's it. Everything is working. So our zombies are spawning, our soldiers are shooting them, and everything is working perfectly. So yep, this lecture is actually an excellent example about how, after learning how dots works, you can build new things rather quickly. It took a while to learn everything that we just did here for the first time. Learn how to do queries, how to set up entities and components, how to handle the baking, the entity instantiation, the system logic. So it took a while to learn all of that for the first time. It took a while to change from an object-oriented mindset onto a data-oriented mindset. But now that we've learned all of that, now this becomes pretty straightforward. We create components, create systems, and easily add logic. So yep, with that, here we have our zombie spawner fully working. Now, just before we end this lecture, let's quickly see the bug that happened a while ago, the one where the zombie was destroyed, but the visual actually remained. Like I said, we need to add that component. So on the base unit, we add this one, the linked entity group. I said that we need to add this to components that were placed in the scene if we don't add it by default. So if I just remove this one from the base unit, so remove that one, so the zombie unit now no longer has it, okay? And now if we test, let's see what happens to that zombie. And that one goes, and if there you go, that zombie was destroyed, but it is still moving. If we pause on the entity's hierarchy, we can see, yep, that one has the mesh. So the mesh stayed alive, but the zombie entity was destroyed. However, note how that bug is not happening to any of the zombies that have since been spawned. So the zombies that are spawned dynamically, they do die completely, they have no problem. But the zombies that were placed during edit mode, those destroy the main entity, but not the child entity with the visual. Now this is a really strange issue. Basically, entities that are dynamically spawned, they get this component added automatically. So here I'm selecting this zombie unit which was just spawned, and this one does have this component. But if you look over here into one of the soldier units, which again were placed by default in the subscene, they were not dynamically spawned, these do not have that component by default. So that's a very strange thing. I don't know if this is an intentional dots thing or if it's an actual bug, but thankfully the solution is quite simple. We just go into our prefab and manually add that component. So the linked entity group, just like this, and that does solve that problem. Basically for the units over here, it is going to actively add this one, but then units that are dynamically spawned, it already has this component, so it won't add a second one. Like this if we test. So if we have these two, so that one was spawned in the scene, that one was spawned dynamically, and yep, they all die exactly as intended. Finally, let's just solve one very strange bug that I just noticed was happening. It's actually a similar issue to what we saw on the bullet. This time it is happening on the find target system. It is on this one over here for getting a component. So it does an overlap sphere, and for some reason it is finding an entity that has since been destroyed. So since the entity has been destroyed, it technically is still alive, so it still shows up in here, but then no longer has any components. So this one throws an error. Here are the logs that I had to verify. So we can see that on frame 1012, on this frame, the entity was killed, but then on the next frame, that physics query was still finding that entity. So again, it's a very strange thing. I have no idea if this is an actual bug. For the solution, we can just validate this. So we can check if system API that exists to check if this entity exists. So this inset.entity. So check if that one does not exist or does not have that component. So if the entity does not exist or does not have that component, then let's continue. Again, I have no idea why the overlap sphere is returning with entities that have since been destroyed, but still this simple validation should fix it. So let's test. And if there we go, the entities find the target correctly and we have no more errors. Okay, so here we have our object spawning zombies. However, they are all still going to position 000, so that's a little bit boring. It would be nice to give them some random movement. So let's create a system to make them walk randomly in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to make the enemies walk randomly around their spawn position. This is really interesting and requires us to learn something different because the way the mathematics random class works is quite different from the one you might be used to. Okay, so here we have our zombie spawners. Zombies are being spawned and they constantly go towards position 000. Now let's create some logic for the zombies to roam around randomly instead of always going to the same position. As usual, first let's create a component to store our data. Let's call it random walking authoring. Now first let's make our standard logic. So a struct for the random walking, it's an I component data. Then we have our baker of random walking authoring. And then we implement this baker, grab the entity and add a component on this entity, a new random walking. Okay, good. So now let's think, what data are you actually going to need? The goal is to randomly walk towards a target position. So that means we need to store that target position. So a float3 for the target position. That is where this unit is going to right now. And then in order to generate positions, we want those to be generated around a certain position, like a spawn position, something like that. So let's define a float3 for the origin position. And then you want to randomize how far from the origin position they should be. So let's make a float for the distance min and another one for the distance max. Okay, great. So now let's pass all of these into the baker, even though for the most part, we're actually going to be adding this dynamically. So the baker is mostly just going to be used for testing, but still, in order to test, in order to make sure that the logic is working, let's set it up. So target position, go in the authoring and grab the target position, and same thing for all the others. So the origin position, distance min, and distance max. Okay, let's save. And now let's attach this to our zombie here. Again, we want to attach the zombie, not to the base unit or the prefab. We want just this one, just the one that is placed in the scene, just this one to have the override. So by default, zombies should not have this component. We're going to dynamically add it to some, but not all zombies. So, but on this one, selecting the one on the scene, let's add the random walking authoring. Okay, great. Now for the target position and origin, let's just choose the exact one that we have. So let's say 11,012. So 11,012, 11,012. Again, we're only setting this up manually just for testing. Distance min, let's say 3. Distance max, let's say 10. Okay, great. So that's the setup. And again, this one is an override. Okay, so far so good. Now let's make our system to run this logic. So in our systems, construct a new entities iSystem. Call it the random walking system. Okay, on this one, let's keep just our nice update. And over here, let's do a system API.query. And for the query, we're going to need the random walking component. And we're going to eventually have to update target position. So let's grab it for writing. So for the random walking component, then in order to tell the unit to move, we're going to need the unit mover. So unit mover. And finally, in order to test if we have reached the target, we're going to need the local transform. So ref, in this case, we probably just need to read for the local transform. Okay, great. This is our query. Now let's do the for each and put the ref RW for the random walking. Call it random walking. Then ref RW for the unit mover. Call it unit mover. And finally, the ref RO for the local transform, local transform. Okay, yep. Now let's see what are we going to do. First, let's get the distance between the current position and the random target position. So math, and let's grab the distance. We can either grab the distance or distance square. Although one very important thing here, which is we need to make sure that whatever value we use in there, it is either the same or smaller than whatever value we're using here. Otherwise, the unit mover is going to stop within this distance. And then if we test over here for a bigger distance, then this one is never going to trigger. So if we want, we can make this a constant so we don't need to constantly repeat ourselves. So up here, let's do that. Public const, make it a float, reached target position distance square. And we defaulted it to 2f. And down here on the system, let's use that. So the unit mover system and use that. And then over here on the random walking system, we can go into the unit mover system. And from there, grab that distance. Now we just need to make sure that we use the same logic. So over here, we use less than. So let's make sure to use less than, not equals. Or in order to make our code more robust, let's also include the equals here, just so we don't make any mistakes. Okay, so anyways, here, let's calculate the distance. So distance squared is going to be between this position. So that's the local transform. Grab the value RO, grab the position. And then the target position, so random walking, value RO, the target position. So if the distance is less than this one over here, the unit mover reached distance. If so, then we have reached the target distance. And if not, then too far, move closer. Okay, so for the move closer, let's just go into the unit mover. Let's write to it, value RW, and set the target position equals the random walking, grab the value for the target position. Okay, this is telling it to move closer towards the random position. And if we have gotten there, if so, then this is where we want to change the target position onto a new random position. Now, normally you would go inside Unity engine and use the random class inside of that one. You would use that and then call random.range and easily generate a random value. This is how I normally do random generation in any of my games. However, this is a class, so it cannot be used inside bursted code. So let's do it the proper dots way and actually use the random, the one that exists inside the mathematics library. This one works quite differently. So this one does not have any static functions. Instead of that, it requires an instance to run. So let's create a new one. So a new random, call it random. And over here on the constructor, this one takes a scene. I will cover what exactly is a seed in a little bit. For now, let's just use the number 1. Okay. So we have this random, and from this random, then we can now generate all kinds of things. We can generate a bool 2, 3, 4, can generate doubles, floats, uints, and so on. Here we even have a next float 3 direction. However, this will generate a random direction with random values on the X, the Y, and the Z. However, in our game has a flat plane area. We only want a random vector that is random on the X and the Z. The Y should be on 0. So instead of using this one, let's just use next float and basically construct our own random direction. So a float 3 for the random direction. And this one, let's do a new float 3. And for the X, let's do a next float. Randomize the float between -1f and +1f. Then 0 on the Y, we don't want that one to be random. And over here on the Z, same thing, next float, -1 and +1. Okay, this gives us our random direction. Let's just make sure that it is normalized. So let's go math.normalize to normalize this value. Okay, great. So with this, we have our random direction. Then all we have to do is multiply by the random distance and add it onto the origin position, and we have our random. So let's go inside the random component. Let's write to it, and it's actually the random walking component. On this one, let's write to it and set the target position. For that, first, let's grab the random walking. Let's read the origin position. and then add the random direction multiplied by a random dot next float of the random walking. Let's read the distance min, and let's read the distance max. Okay, yep, so just like this. First, we construct a brand new random, then we calculate a random direction with random on the x and on the z, we normalize the random direction, and then we assign the new target position, starting from the origin position, then adding the random direction plus a random distance. So yep, this should be working. Let's do just a quick log just to see what position this one is returning. Let's use the debug inside Unity Engine, debug.log on this random position. And actually, since I added the Unity Engine up here, now here we have a conflict. So if this happens, if you want to have both the using Unity Engine and using mathematics, if so, then you can just write the full name here, unity.mathematics, and that does work. Or alternatively, let's just not put the Unity Engine and let's put it over here on debug.log, unityengine.debug.log. Okay, this should do it. So now let's test and let's see exactly what positions we are generating. Let's save it, make sure to save everything. Also, let's disable the zombie spawner. We can literally just disable this game object and it will be disabled in the empty. That way only this unit will test. So let's see what position this one is going to return. Okay, there's the zombie and it's starting to move and it goes somewhere and now it stops. Now in reality it is moving, meaning that code is running. We can see down here messages are constantly being spawned. Except the issue is that it is generating the exact same position every single time. So it's not really random. This is one big difference relative to the other random class. If you call random.range, then it always gives you new values. Whereas with this random type, this one basically requires us to persist with this object. We need to create this object, then use it to generate a bunch of things. And then after generating, we basically need to resave this object. If we're always constructing the exact same object, we're always going to have the exact same generation. Essentially, this random class, this one is deterministic, meaning if we always create a random, always with a seed of 1, and we always do a next float, and another next float, and another next float, if so, then these sequence of supposedly random numbers will always generate the exact same values. If we want different values, which we do, if so, then we need this random to persist. So instead of constantly creating a new one, let's just store it inside our component. So over here on the random walking, let's create it. So a public random against the one inside mathematics, call it random like this. So inside unity.mathematics, and over here on the bake, let's construct random equals new mathematics.random. And for the seed, again, let's use 1. I'm going to explain that one in a bit. Okay, so we have our random. Now the random is being saved in the component itself. So now over here in our system, instead of using a brand new one, instead of that, let's actually grab the random that is inside the random walking, go inside and grab the random. But like I said, this needs to persist. If we do this, then we are not actually saving back the data. We are taking this random copy and we are updating it by generating all these floats. So after we do this, we need to make sure to save it back onto the random walking component. So for this one, let's go into that one, random equals random. Okay, yep, this should be this should be working. So let's save everything and test. Okay, so there it is. There's a zombie going in that position and then goes up that one and then down and then right. And yep, it does seem to be working correctly. Okay, great. So the unit is going to random positions. Now let's test with another unit. So I'm going to duplicate this one and put it a bit over there. Okay, now let's test with 2 units. And yep, look at that, how strange. Both of them are going to the exact same position. Both of them are following basically the exact same order of random positions. So it is generating a series of random positions, but it is always generating the exact same series. So this is exactly where the seed comes in. Like I said, this random type, this one is deterministic, meaning that if you use the exact same seed, it will always generate the exact same series of values. This is how, for example, games like Minecraft work. They don't actually store the entire world. The world is generated from a seed, so if the seed is the same, it will always generate the exact same world. So if we want the random position to be different for different units, then we just need to use different seeds. A seed is really just a number, and as long as the number is different, then it will work. So on our component over here on the bake, instead of hard coding just the number 1, instead of this, we could just generate a random number. So for example, here, we could use the random class, do a random.range, and generate a random number between 1 and 10,000, something like that. So technically we could do this, but then we would have a slight problem. This is the bake logic, which like we already saw, the bake logic runs only once. It does not run every time a unit is spawned. So if we did this, even if we randomly generate a random number over here, all the units would still end up with the exact same seed. So we need a different method than this one. And now for units placed in the scene, we can basically just define here on the authoring component a random seed. So a public int random seed. Actually, this is meant to be a uint. Okay, a random seed, then over here let's pass it in, authoring.randomSeed. And then for units that are spawned dynamically, basically we're going to use a different method in order to generate a new random component whenever the unit is spawned. But let's first make sure that it works on the ones on the scene, so let's save. And now here on our bakers for this zombie, let's set this one with a random seed of some random number, let's say 56, and for this one, let's say 32. So as long as they are different, it won't work. So with this, let's play and test. And if there it is, right away they are moving to different positions and they are randomizing different locations all the time. Alright, awesome. So yep, everything is working correctly. Now all we need to do is just add this same logic onto the zombie spawner. So over here on the zombie spawner system, we count down the timer and then we spawn the zombie entity. Okay, so far so good. Then afterwards, let's add that random component. However, adding a component won't be a structural change. So if here we do state.entity-manager add component data, if we do this, this is actually going to throw an error. Now I'm actually not entirely sure why this one throws an error, but the instantiate doesn't. But either way, yep, this one will throw an error. So instead, let's not immediately add a component. Instead, let's use the normal entity command buffer. So up here, let's just grab it. So the entity command buffer, and let's simply go into the same one. So system API, let's get the singleton for the end simulation command buffer system. Let's go inside, grab the singleton for this one, and let's call create command buffer, pass in the state.world_unmanaged. Okay, so we have the entity command buffer, and then down here, now we can do that one. So we can call add component, and let's add onto this zombie entity and add a new random walking component. And now here we just need to initialize all of the parameters. So first for the origin position, the origin is going to be wherever this unit is being spawned. So let's use exactly this one. And for the first target position, which is supposed to be a random position, but we can set it to exactly this one, which means it will generate a random position on the next frame. Okay, and then for the distance min, distance max, let's actually expose these values on the, over here, the zombie spawner component. So let's go into this one and do exactly that. So a public float, random walking distance min, and then we have the distance max. Let's expose these in the authoring component and pass it in that one. So both the min and the maximum, okay. And now back here on the zombie spawner system, over here we can go inside the zombie spawner. Let's read it. In this case, the distance min and then the distance max. Okay, so the final component is just the random one. Let's construct a brand new random. And for the seed, let's start with just one, just for testing. Again, this will not exactly work, but let's test. We just need to make sure to assign these values. So back in the editor here, let's go on the zombie spawner. And first of all, let's enable this game object, okay? And let's set up these, let's say 3 and 10. Okay, that should do it. Let's disable the other 2 zombies and let's test and see where exactly these spawn zombies will go. Okay, that one spawn's going down there, that one spawn going down there, spawn going down there. So yep, we have the exact same thing. Since all of them are being spawned with the exact same seed, all of them are following the exact same random positions. Now to solve it, like I said, you could randomize the number, or for example, use the clock time. That could work, but with those, technically we could still end up with multiple units using the exact same seed. So something that is both simpler and actually guaranteed to be unique is to really just use the zombie entity, use the index. So we go inside the entity and we grab the index. And yep, this is basically an int value that defines the index for this entity. This one is guaranteed to be unique for all of the alive entities. So this way basically guarantees that every single zombie entity is going to have a different random seed. We just need to convert this into a uint because that's what that one takes. Okay, so that's it. Let's test and see if all of them are going to random positions. And by the way, here on the random walking system, we can now get rid of our log just like this. Okay, so there's zombie, first one going up, second one going a bit more to the side, that one going over there, that one going down, and that one going down. So yep, they are indeed going to random positions. Each zombie that spawns is getting a different seed, and because of that, they are generating different random positions. All right, awesome. So here we implemented a really nice random walking logic. As the units spawn, they randomly walk around their spawn area. In doing so, we also learned how to work with the random type inside the mathematics library, and how that type is different from the default Unity random class. By using this type instead of a random class, we can now use burst to make this code super fast. So with this, our zombies are looking quite nice. They spawn, they move around, I can use my units, I can approach and I can shoot them. However, one thing we don't have is some kind of visual for the health. Right now, the enemies, they just take some bullets and eventually they die. Would be nice to have some kind of health bar to be able to see what health they have, so let's add that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to create a nice health bar. Now, this is a very important lecture because it requires us to learn some tricks for how to scale transforms and also make them face the camera. We need to do that, and we're also going to make sure that our health bar is as decoupled as can be from the rest of our code, which requires some interesting logic. Okay, so here we have a bunch of stuff working. We've got our units, we've got some enemies being spawned, and they're randomly walking around. Then I can move with my units around, and when they get close, they shoot the enemies. But there's no feedback. There's no way to tell which of these enemies has been damaged or not. They have a health, but there's no way to see it. So let's build a nice health bar. Now first, let's set up the structure for the health bar. And in terms of building that, you might first think to make it just in the UI. Now that's a good option if you're making a game kind of like an FPS where you just have your own health. But in an RTS with tons of units in the world, you really want a health bar to also exist in the world. You want a health bar per object on top of each object. And in terms of making a world health bar, let's just go inside the base unit. Yep, inside this prefab. Now, one thing I normally do when I want to make health bars for units is just create a world space canvas. So go into UI, create a canvas, and build this. Then over here on the render mode, set it to world space. And then inside this canvas, create images for displaying the health bar. That's what I normally do. However, like this, we are not using dots, specifically not using dots rendering. So if we use this approach, our game will end up being very slow, since we're going to end up having hundreds or even thousands of canvases being rendered. So let us not use this approach, let's do something else. We want to render it just like on normal units, using the same rendering system. So let's use a normal mesh filter and mesh render. Now for the setup, first let's construct just an empty game object, name this the health bar. Let's put it first of all on 0, 0, 0, and then just lift it up on the Y, something like this, okay. Now inside it, let's make another empty game object, call this the background. And for this one, let's add both a mesh filter and a mesh render. For the mesh filter, let's go with a quad. And for the mesh render, let's go over here on the materials, general, and choose the gray material. And yep, there it is. It's on the other side, but don't worry about that. Like I said, we're eventually going to make this face the camera, so it doesn't matter that it's only rendered on one side. So on this, let's scale it. So on the Y, let's put it something like 0.3. Okay, we have a nice rectangle. This is going to be our background. Now let's duplicate this. So duplicate the background, name this one the bar. Let's move it on the Z just by a tiny bit. So literally over there on the Z by 0.01. That's just so we don't have issues with Z fighting. If both of them are on the exact same position, then we're going to see some flickering. But if they are slightly off, like by that amount, that is more than enough, that will make sure this one renders on top of the other one. Okay, so for this one, we want it in red. So let's choose over here the health bar material. Yep, just like that. Then for scaling the health bar as the unit takes damage, for doing that, we're going to want to modify over here the scale, modify the X, just like this. Except not really like this. This is scaling from the center. This is not what we want. Usually health bars scale from the sides. Now doing that is actually quite simple. We just need to change the pivot for this object. And the way we do that is with another game object. So inside the health bar, let's construct a new empty game object. Call this one the bar. And this one, let's offset it to the left side. In this case, since the background bar has a size of 1, let's put it literally on minus 0.5. And that makes it perfectly on that side. And now we can make the one in the visual a child of this one. And yep, just like this. Now if we scale this one on the X, yep, now it does scale correctly. Okay, so far so good. So this is going to be the structure for our health bar. Now let's apply some logic to it. So first let's make the component to store some data. So on the authoring, let's create a new MonoBehavior script. For the health bar authoring, on this one, let's make the same stuff as usual. So public struct health bar I component data, and then up here make a class for the baker health bar authoring, and let's implement this, get the entity, and add a component on this entity, a new health bar. Okay, just like this. So now over here, for the data, we're going to essentially need references to two things. First, we're going to need references to the visual health bar. So let's make a public of type entity for the bar visual entity. And secondly, we're going to need a reference to the parent entity that has the health component. So let's put public entity for the health entity. Yep, just like this. And like we saw previously on the baker, let's add them as game objects. So this one's going to be a game object for the bar visual game object, and another public game object for the health game object. Then over here when you construct for the bar visual entity, let's call get entity on the authoring dot, this case the bar visual game object with dynamic. Okay, and same thing for the other one. For the health entity, go inside the health game object. Okay, yep, like this. Let's save. Then here in the editor, let's choose the health bar. So this one, the parent game object, and let's add the health bar authoring and drag the references. So for the bar visual object, that is this one. Again, it is this one, not the child one that actually has a visual. We want the one where we made the special pivot. So let's drag this one. And for the health is going to be on the base unit. So yep, just like this. By the way, here you might be thinking, wouldn't it be better to place this component either directly on the bar visual or perhaps on the unit that actually has the health component. That way, technically, we would avoid one of these references. And the answer is, yep, you could do that, and it would likely be a tiny bit faster since we would only need one reference. But the performance difference is so tiny, and in doing either of those methods, we are really complicating the structure of our object. Either we would have this health bar component inside a child object. That would make it look very messy with the health bar, the main health bar, that one having no component. Or if we place that one on the unit object, if so, then we are kind of tightly coupling this unit to the health bar. We want it to be as separate as possible. So that is why I prefer keeping things like this, keeping the health bar over here with references to everything that it needs. That way, this health bar over here is as self-contained as possible. Which is important because later on in the future, we are going to have things other than units that also have health, like for example the buildings. And by keeping this structure, by keeping this one as self-contained as possible, we are going to be able to reuse this health bar on other systems, other buildings, and so on. But again, let me also point out that refactoring is always a possibility. So if later on you find out that for some reason your health bar is your main performance bottleneck, if so, you can always come back here and refactor it. So always remember, refactoring is always an option. Okay, so here we have our health bar. We have the component with all our data, so now let's make the system to run it. So in our systems, let's create a new entities system for the health bar system. And now here, let's do our update. And on update, let's do system API.querying. Let's query for the health bar. And for this one, we're really just going to read the references. So let's make it ref.ro for our health bar. And this is the main one that we need. So let's just do this. So for each, doing a ref.ro on our health bar, like this, okay. So then from inside this health bar, inside we have references to the bar visual and the health entity. So let's go on the health entity and let's grab the health component. So system API, let's get the component of type health inside of this entity. So this returns a health component, okay? And now for calculating the size for our health bar, we're going to need to normalize our health. So let's define a float for the health normalized. And normalizing the value is actually quite simple. We just take the health amount and divide by the maximum. So that means we also need to store the maximum. So over here on the health component, store the health amount and the health amount max. And let's make sure to pass this in over here on the baker. So the health amount max, authoring.health amount max, okay? So now over here, the health amount divide by health.health amount max. And let's just make sure to convert one of these into a float so we get a nice normalized value. Now with this value, we can really just apply it to the bar visual. So let's go system API, get the component of local transform to modify the scale. And we want the one that is inside the health bar. Let's read the bar visual entity. So this returns a local transform for the bar visual local transform. And actually we want to modify it. So instead of get component, let's use get component RW, which returns a ref RW. This makes it super easy to modify this one. So then let's go into the value RW and set the scale to the health normalized. Okay, yep, just like this. Now you might be guessing this won't exactly work, but still, let's set it like this. Let's save everything. And then here in the editor, let's just make sure to assign the health amount max. So over here on the base unit, let's go onto the health authoring and set the health amount max also to 100. Okay, that's it. Let's exit and make sure to save the base prefab. And now let's test. Okay, so here we are. And right away, our units do have their health bar. Now they are sometimes visible, sometimes invisible. That has to do with the rotation because again, it's only visible in one way. But that's not a problem. We're going to solve that in a little bit when we make sure that the health bar always looks at the screen. And now if we try attacking a unit, to make it easier to see, let's actually stop playing. And over here, let's disable the zombie spawner and just enable this one, just so we have just one to test. Okay, let's see. So we have that one. And now let's move closer with one of these units and see if that one starts taking damage. And if there you go, it does start taking damage. There's our zombie with the health bar, and the health bar is indeed shrinking. However, it's shrinking in a strange way. It is not going right to left. Instead, it's actually scaling across all the axes at the same time, whereas the goal is to only scale the visual bar just on the X. So this means that it's time for us to look at the baking logic. So over here on the health bar authoring, so far we've pretty much always been using the transform usage flags and putting them as dynamic. Now this is great, this means that the transform can change, but making it like this also makes it so that the scale can only be uniform, meaning it has to have the exact same scale on the X, Y, and Z. It cannot have a different thing on the X, different on the Y, and Z. Now this is a performance thing. It is much faster if the scale is uniform, but in our case we do not want it to be uniform. We want the X to be something we change, and we want the Y and Z to remain at 1. So here for the usage flags, instead of dynamic, let's go with this one, non-uniform scale. And if just like this, let's save. And now if we inspect one of these entities, so over here on the zombie unit, let's go select the health bar and select the bar. So this is the one that has the reference. And in the inspector, if we go into runtime mode, and yep, here we do see now it has this component, a post-transform matrix. This component basically applies a second transformation on top of the regular transform, which in this case will allow us to scale the visual just on the X. You can note how, for example, on the main zombie unit, which set as just dynamic, yep, this one does not have that component. And also, by the way, even without explicitly baking something as non-uniform, if the game object has a non-uniform scale, like for example the background, where we set a non-uniform scale with a y of 0.3, just by doing that, it does automatically add the post-transform matrix. So if in the authoring game object you already modified the scale to non-uniform, then when the entity gets baked, it already has this component. Or of course, if we are explicitly over here saying non-uniform, then it does also add that component. Okay, so here on our health bar system, instead of working with this local transform, instead let's go system API, let's get the component RW. In this case, let's grab that one. So that's the post transform matrix, and it's from the health bar value RO, and let's grab the bar visual entity. So this will return a ref RW of post transform matrix. Let's call it the bar visual post transform matrix. Okay, yep, we have this one. And then from that one, we can go inside the value RW. And for the value, this one takes in a value of type float 4x4. So let's put that float 4x4, this one over here. Basically, it's a matrix 4x4. And this one, thankfully, this one has a helper function over here for the scale. And we can set the scale, and there's a version that takes X, Y, and Z. So that's exactly what we want. Let's put on the X, the health normalized. Then on the Y, 1, and Z, also 1. And yep, just like this, let's test. Okay, here we are, and let's approach just with one of these soldiers and start shooting and seeing. And if there you go, it is indeed working. Look at that, the scale is indeed modifying perfectly, exactly, right to left, exactly as we want it. All right, awesome. So it's working. Now let's add 3 more features to our health bar. First one is let's make it look towards the camera. So basically we just need to grab this local transform for the health bar and make it face the camera. So the way we can make it face the camera is essentially by grabbing the camera's forward vector. We apply that same forward vector to the bar and it will be looking towards the camera. So first let's grab that vector. So vector 3 for camera forward, and we can grab camera.main and grab the transform.forward. And here this actually added system.numerics that is not the one we want. We want the vector 3 that exists inside Unity engine. So yep, like this one, camera.main, and yep, like this. Except this might actually throw an error. It has to do with the difference between the lifespan of dot systems and the lifespan of just game objects on the scene. That has to do with how the dots bootstrapper works, how it automatically creates the systems and starts them running. So on the first update, the camera might not exactly exist. It might only exist on like update 2 or 3. So let's add some safety code here. So by default, let's default it to vector3.0 and then check if camera.main is not null. So if the camera has been initialized, if so, then we can indeed set it. So camera forward equals this, like this. Okay, so we have our camera forward vector. Now the goal is for the health bar to be rotated towards this exact same forward vector. However, this is actually a tricky thing that took me a while to figure out while researching for this course. If we just take this and we apply it to the bar rotation, which by the way, let's actually include over here in the query. Let's include a refrw local transform, and over here we need to include that one. So let's put the refrw local transform. Okay, we have this. Now if we go local transform and right towards the rotation, if we do this and use quaternion.local rotation to convert this one, the camera forward, convert this one into a quaternion. Let's use math.up. Okay, if we do this, let's see, what does this do? And nope, it doesn't actually work. It doesn't actually seem to do anything. Look at that. As the units rotate, it is still clearly not looking towards the camera. Basically, this is actually the exact same issue that we had on the bullet spawn and how we need to have a local position and convert it into a global position. Over here, it's the exact same thing. The health bar, that one is a child of another transform. So we need to convert the camera forward from a global vector into a local vector. Now, thankfully, that's actually quite easy. We just need a reference to the parent local transform, and the parent is going to be the same one that has the health component. So let's go system API, let's get the component, and it's going to be the local transform of the health bar. Let's grab the value RO and the health entity. So this one is going to be a local transform for the parent local transform. And now we can rotate this health bar. And for the rotation, for that we use the parent local transform and we use inverse transform rotation. So this will convert a global rotation onto a local rotation, exactly what we want. So let's do it just like this. And yep, with this, let's save and test. And yep, right away it does work. So our units can move around and you can see, yep, like that, it does work. Alright, awesome. Okay, so now for the second thing, let's make the bar only show up if the bar is not full. Now this is really a personal preference kind of thing, but since our game is going to have tons of units, I think it looks better if the bars aren't always visible by default. For doing this, we can use some super simple logic. So over here we have the health bar normalized, and when the bar is full, we can just hide it. So if this one, if it is 1F, if so the health bar is full, so we can hide this. So local transform, we can go into the value RW and set the scale. In order to hide it, let's set it to 0. And if not, then let's set it into 1. And if that's it, super simple, let's test. And if right away the bars are not visible, so the zombie over there has no health bar, but as we approach and starts getting shot, once it gets shots once, yes, there you go, it does show up the health bar and it does go down. Okay, great. And now for adding a really nice bonus. In order to make this code slightly more performant, let's make it only update when something actually changes. As opposed to what it is right now, where even these units who have the health bar invisible, even these are still constantly updating their health bar on every single update. So that's really quite wasteful. For this, we can once again use the exact same event logic we've already used for the unit selection logic. Let's use an event to define when the health changes. So let's go over here onto our health component, and let's set an event. So public bool on health changed. I'm using change just in case it supports both health going down, taking damage, and health going up, healing. Okay, so we have this. And then let's go into our reset event system. And on this one, let's do the same thing. Let's reset our event. So in this case, that's the health. So we go into the health for the component query for health, and we don't need the with present. Okay, cycle through the health, then health.valueRW, and on health change, reset into false. Also, by the way, one thing that I forgot a while ago, over here for the updating group, right now we are already making it updating the late simulation system group. That's great. But this is not necessarily guaranteed to end up at the end. Looking at our systems window, we can see, yep, there's the reset event system. And just by chance, it did end up at the end. But like I said, this is somewhat random between Unity builds. So on your PC, it might not end up at the end. Let's make it explicitly update only at the very end. So for that, over here on the attribute, we can use the option order last and set this one equals true. Okay, now this one will guarantee it runs at the very end of the late simulation system group. Okay, so that's the reset. That sounds good. And then on the health bar system, on this one, first of all, let's make it run before the events are reset. So we can just put update in group on the type of, on the late simulation system group. Okay, then down here for running our logic. Now, one thing is the rotation here. This one we need to run all the time, not just on the event update. However, we only need to run it all the time if the bar is actually visible. So we can check if the local transform the value ro.scale. If the scale does have 1F, then the health bar is visible. So yep, if so, the health bar is visible. Great. Now let's check if the health has been changed or not. So here, if health, and let's check on health changed. So if that one is false, meaning the health did not change, if so, then let's just skip. Let's just continue. And if it did change, then let's continue running this logic. By the way, let's get rid of these comments just like this. Okay, this should do it. And to validate, let's just do over here debug.log and say health visual updates. Okay, let's see how often this one runs. It should not run on every single update. Over here, the logic should be set up correctly. All that's left is to fire off this event. So let's go here onto the bolt mover system. This is where we are actually dealing damage to the units. Over here, we are counting down the health. So really all we need is just over here on health changed and set it to true. And if that's it, so this one will set it to true, then the health bar system will update it, and then reset events will reset it back into false. Now just one more thing, over here on the health authoring, let's default it true just to force the health bar to actually update. So this one equals true. Okay, just like this, let's save everything and let's test. Looking down at the log, we can see we have a bunch of updates, so all of them updated just once as soon as they started, which makes sense, but they are not updating right now. Now if I take one of these units and I move, it should only update once every time that unit is shot. And yep, there you go, only when the unit is shot does it update. And now when it stops moving, yep, there you go, it stops updating. All right, awesome. This is working perfectly, so let's remove the log. Now let's just solve one issue. It's this burst error over here. It is on the health bar system and it's telling us the manage function, Unity engine, camera get main is not supported. So this is the usual burst limitation of not being able to access managed objects, and the camera itself, that is a managed object. So we cannot access camera.main inside bursted code. Now, even though this is an error, it does not stop us from playing the game. So we can head on play and everything does work, so it's technically not a problem. However, this error existing, that does mean that we cannot make a build. If we try, we get an error and the build fails. And thankfully, in order to solve this, it's actually quite simple. Here on the health bar system, the issue is we cannot have both burst compile and grab the camera.main. So to fix this, let's really just disable burst compile on this function. So like this will not be using burst, which means it will be a little bit slow, but will not throw this error. And also, by the way, don't worry too much about the speed of this system. We're going to refactor all of this to use the job system in a future lecture. Okay, so that's really it. Let's save, and now wait for it to compile. And yep, we have no more errors. Okay, so here everything is working perfectly. The units have a health bar, and that health bar only shows up when it actually takes damage. So if I move, now it does show up. The health bar updates to show the health of the unit. It correctly scales. It shows and hides depending on if the unit is fully alive or not. And it only updates when something changes. So that's perfect. Here we built a really nice health bar, but our units are also still looking quite a bit too basic, just shooting the bullets. It doesn't have much impact. So let's add a nice visual light and learn about companion components in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to add some nice lights to our shooting visual. This will also help us learn more about what are companion game objects and how they work alongside dots entities. Okay, so here's our game so far. We have our units, we can control them, there are some zombies, and our units can approach and they can shoot. So yep, that works, but the shooting looks a bit too basic just like this. The bullet simply spawns. Let's add some nice lights when we shoot. So first things first, let's just build our light. So inside the entity subscene, let's construct and let's actually build the light directly. We could make it a child of a game object, but this one's going to be super simple, so let's just create a straight point light. Let's name this the shoot light. Then over here for the settings, for the color, let's make it a slight orange. Okay, like this. And for the intensity, let's make it really intense, like 20F. And over here on the scene, let's just lift it up a bit so we can see the intensity. Yep, that's good. And for the range, let's put it a bit lower, just 5, that's good enough. And down here for the shadows, let's maybe go with hard shadows, but with low resolution. Okay, that's it, pretty simple. And also, by the way, here we do see a message. It has to do with Shadow Atlas. Technically, we could disable shadows here, but I think with hard shadows it looks a little bit nicer. So what we can do is just go into our settings, go into our render pipeline asset, and over here on the lighting tab, we see additional lights. And over here, we see the Shadow Atlas resolution. So if you want, you can play around these values or disable shadows. Like I said, both works. In my case, I'm going to move this up to 4K just because I really like having some lights. Okay, so yep, that's good. Here we have our shoot light setup. And again, if we look down here onto the entity baking preview, we can see there are a bunch of companion game object components. So this is just like we saw in the beginning of the course for the sprite render. Basically, Unity Dots does not currently support lights natively. So what it does is basically it creates an entity that will match exactly this game object. So both the entity and the game object are linked. If I move the game object around, the entity moves with it. But importantly, the game object still exists, as opposed to the normal baking process where the game object is gone and only the entity exists. Meaning this is not going to be as performant as using native dots entities, but it's still going to be fast enough, and it also means it is possible to use lights in our scene. Basically, the fact that it's a companion game object doesn't actually mean you can't use it. It just means it won't be as performant. In this case, it doesn't really matter too much because our light isn't going to live for too long, but do be aware of companion game objects and how they are special. Okay, so what exactly do we want to do with this light? Basically, we want to spawn it when a unit shoots, and then destroy itself after a short amount of time. So let's handle the spawning logic, which for spawning, first of all, we actually need to make this into a prefab. So on our prefabs folder, let's just drag it over there. Okay, great. Then for dynamically spawning the prefab, we need to add the reference over here on our entity references. So over here, let's add the same thing. So another field for the shoot light prefab entity, and up here for the shoot light prefab game object. And then over here, same thing, shoot light game object. Okay, like this. Then for spawning, it's on the shoot logic. So let's go into our shoot attack system. Yep, over here. Let's scroll down to where we are spawning our bullet. Here it is. So we spawn the bullet, and afterwards, let's spawn the light. So let's use state.entityManager to instantiate. Let's grab the entity's references, and we can grab the shoot light prefab. So this will be an entity for our shoot light entity. Okay, great. And then all we need to do is just position it. And it's going to have the exact same position as the bullet. So we can actually just copy that one in order to end up on the exact same position. So shoot light entity spawn on the exact same position. Okay, that's really it. Just like this, we should already be spawning the lights. So let's test. Over here, let's just delete the prefab from the scene. And let's go over here on the entities references and let's drag the shoot light prefab. Okay, let's test. Okay, here we are. Let's select just one soldier, move closer, and let's see. And if there you go, it does work. It does spawn the light. Okay, great. Now, obviously, we need the light to eventually vanish. So let's do that. Let's make a component to store a timer. So on the authoring, construct a monobehavior script. Shoot light authoring. Then over here, the usual standard stuff. Construct for the shoot light, I component data, and up here our baker. shoot light authoring, grab the entity, and add a component on this entity, a new shoot light. Okay, so now what data do you need is really just a timer. So up here, a public float timer, and let's also define it up here on the authoring component, and then just pass through. So super simple stuff. Okay, let's save this. In the editor, let's select the prefab, so the shoot light, and let's add the shoot light authoring component. And then for the timer, let's put it 0.05. So this is pretty much just going to spawn for about 1 or 2 frames. Okay, so that's good, that's data. Now let's make a system to actually destroy it. So on our systems, let's construct a new entities iSystem for the shoot light destroy system. And over here, let's keep our update just like this. Let's do a query. So system API, let's do a query for our shoot light component. And we're going to want to write to it. So ref rw. And that's really the only one we need. So let's do a for each ref rw for the shoot light. Okay, we have this. And over here, let's count on the timer. So shoot light, let's go into value rw for the timer. Minus equals, and it's on system API.time.delta time. And then if this one is low enough, so the shoot light value RO, grab the timer. If it is under 0f, if so, then we want to destroy it. And for destroying, as usual, let's use an nt command buffer. So nt command buffer, and let's grab it. So system API, get the singleton of the end simulation nt command buffer system, grab the singleton. And from the singleton, create the command buffer and just pass in state.world unmanaged. Okay, so then over here, we can just go nt command buffer and call destroy entity. And now here we need a reference to our entity. So let's modify our query here and add with nt access, which means we need to add our entity over here. So entity, let's just format this. Tip like this, pass in and destroy this entity. Okay, like this, so let's test. So here we are, let's move with 1, see if it spawns and destroys itself. And there you go, it does spawn and does destroy itself. All right, awesome. So this is working perfectly fine. However, here in our shoot attack system, on this one, I don't think it makes sense for this system to be responsible for both spawning the bullets and spawning just a normal visual effect. This system should really only handle logic. So let's separate the visuals from the logic like I normally do. Let's use events, except of course we have to use the special dots events. So let's go here on the shoot attack component. And on this one, let's make an event. So public bool on shoot. Okay, great. So now let's go on the shoot attack system. And on this one, instead of doing all this, let's just go into our shoot attack, value RW, and set on shoot equals true. Then on the reset event system, on this one, let's reset it. So let's make another query. This time, listen to the shoot attack. And let's go on that one and set the on shoot back into false. Okay, so like this, all of it is working. So let's save all of it. All we need is now an event to actually spawn the light. So let's make a new system. So new entities iSystem called the shoot light spawner system. And over here first, let's make it run before the reset events. So as always, update and group on the type of for the late simulation system group. And let's get rid of this one and this one. Okay, so now here let's do a query, system API.query. Let's cycle through all the shoot attack. And we just need to read it. So ref RO on the shoot attack. Let's do a for each ref RO on the shoot attack in this. Okay, so now let's test. If shoot attack, let's read the value. If the on shoot has been triggered, if so, then here we want to spawn the light. So let's go on the shoot attack system over here. Let's just copy this logic. So let's go over here, paste this logic, which means we need the entities references. So let's also copy that one. Go up here just like this. Okay, so we have that one. We can spawn the shoot light, except for setting it up, for setting up the position. This is a bit of a tricky question. Here we don't know exactly where we should spawn the light. All we know is that an event just happened. Now, technically, we can go inside the shoot attack and grab the bullet spawn local position. We can grab that and do the same calculations, so that would work. But this is also the perfect time to see how we can add extra data with our events. Now, instead of storing just a boolean, which really doesn't store any data, really just stores true or false. So instead of that, let's create a new struct to store all our data. So inside here, let's make a public struct, call it onShootEvent. Then inside, let's have a boolean, call it isTriggered. This will be true when the event is triggered and then reset. And then let's add any extra data we want. Like in this case, we want a float3 for the shoot from position. Okay, yep, like this. And now on the onShootEvent, instead of being of type bool, it's of type onShootEvent. And over here on the shoot attack system, instead of just setting that one to true, let's go into the onShoot and let's set the isTrigger into true. Let's actually rename this. Instead of isTrigger, isTriggered. Okay, the event has been triggered. And then for the shoot attack, for the other one, for the shoot from position, let's pass in the bullet spawn world position. Okay, yep, that one does. And over here, let's not spawn that one. Great. Now let's go onto the reset events. And over here, Let's modify that one. So we just need to reset the is triggered. Great. And finally over here on the shoot light spawner, on shoot dot is triggered. If the event is triggered, let's go inside again the shoot attack. Let's read the value, the on shoot, and here we have the shoot from position, and now we can convert it. Okay, this should do it. So now let's test, and let's also enable all our zombie units. Okay, let's test. So here we are, and if I move a little bit closer, and if there you go, it is indeed spawning the lights on all of them, all the units. They do see, they do fire, and they do spawn some lights. All right, awesome. So here we have added a really nice light to our shooting. Everything looks quite a bit more polished. In doing so, we'll learn more about companion components. And very importantly, we'll learn how to separate our logic from visuals using events. And we'll learn how to handle events and dots with extra data. Okay, great. So with this, our units can now shoot. It would be nice for the enemies to also have some kind of attack. So let's implement a nice melee attack for the zombies in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn how to handle melee attacks. So our zombies will find targets, move closer, and attack. Okay, so we already have quite a lot of things. Our units can move around, they can find targets, and they can shoot. But the zombies are still not doing anything. So let's add a nice melee attack onto our zombies. And this task is actually a great example of one of the powerful features of dots, or rather a data-oriented design. It's the fact that systems and components really only care about themselves. We already made our find target component in system. That logic only cares about finding targets. It does not care if the target is going to be attacked with a bullet or with a fist. It does not matter. It just finds targets, that's it. So for our melee action, we can reuse the exact same find target system. All we need to do is make sure that the zombie already has the find target system, which it does. So if we inspect the zombie unit and we scroll down, yep, it already has the find target authoring and already has the target authoring. So the zombies are already good enough for finding targets. Let's just increase the number over here just for testing. Let's put it 15. Okay, great. So just like this, it's already working. Let's just quickly validate it. So over here, let's get one of these units close to a zombie. And now if we pause and let's select one of these zombie units. And let's go put our inspector into runtime mode and find the target component. And if there it is, and yep, it did find a soldier unit. So yep, just like this, our zombies are already finding targets. Like I said, this is a very real use case of the benefit of reusing systems and dots. As long as we are clever with the components that we use and how we make our systems, as long as we make them as self-contained as possible, then we can reuse them in many use cases. So since finding the target is already working, let's just handle the melee attack logic on top of that. So first, let's make a component to handle our data. So in our authoring, let's go create a new mono behavior script for the melee attack authoring. And now on this one, let's first make the whole thing. So struct for melee attack. It's an I component data. And on this one, let's make the Baker class as always. Baker on melee attack authoring. Let's implement that one, get the entity, and add a component on this entity, a new melee attack. Okay, so now what data do we need? Just like in our shoot attack, we're going to need to have some kind of timer. We don't want to attack on every single update. So up here, the usual float for a timer, and another one for a timer max. And let's expose just the timer max on our authoring component and pass it in over here. So timer max equals authoring.timer max. Okay, yep, just like this. Let's attach this component to our zombie. So here, let's select our zombie prefab. Yep. And let's attach the melee attack authoring. Then for the timer, let's put it something like 0.5. Okay, so far so good. Now let's make the system to run this. So in our systems folder, let's construct a new entities iSystem for the melee attack system. Now on this one, let's keep just the update, just like this. Let us cycle through everything. So system API, doing a query. And first we're going to need the local transform. We're eventually going to need to know if this unit is close enough to attack. We're just going to read it. So ref RO of the local transform. Then we also need the melee attack. That one has a timer, so we're going to write to it. So our melee attack. And we're also going to need to know what target we're attacking. So ref RO for our target. Okay, let's do the for each for this. Ref RO on the local transform, then a ref RW for the melee attack, and finally ref RO for our target. Okay, yep, that's our query. So now first, let's check if the target is null. So up here, let's check target value RO, and if the target entity is entity.null, if so, that means we have no target, so let's just skip. Let's just continue, okay? Then if we do have a target, here let's see if the target is close enough to attack. So for that, let's grab the target position. So grab the local transform for the target local transform. We go inside the system API, get the component of type local transform of the target.valueRO target entity. Okay, with this we have the target local transform. So now for finding the distance, let's do math.distance. And again, we don't really care about the actual value, so let's use distance square. The distance between the local transform dot value dot position, so this position, distance between that and the target local transform dot position. Let's check if this distance is close enough to attack. So define a float for the melee attack distance squared, and let's put it at something like 2f. And we check if the distance, if it is bigger than this, then that means the target is too far. And if not, then target is close enough to attack. Now, over here on doing just a distance check, this is actually going to have an interesting error, an interesting problem, but we're going to see that in a little bit. For now, this is great. So we test distance between this unit and the target. And if it is too far, then really over here, all we want to do is move closer. So let's actually also add a ref RW for our unit mover component. And let's define it up here as well, the unit mover. So if the target is too far, let's move closer. So let's value RW, set the target position to the target local transform dot position. Okay. And if the target is close enough to attack, then first let's stop moving. So let's stay moving exactly where we are. So set that one to that position. Okay. We stop moving, then let's count down the attack timer. So let's go inside the melee attack, the value RW, and for the timer, let's count down by system API.time.delta time. Count on the timer, then just check if value for the melee attack, let's read the value of the timer. And if it is still above 0, then it's not yet time to attack. If so, let's continue. But if not, then let's reset the timer. So go in the value RW for the timer and set it to melee attack. Let's read the timer max. Okay, so then down here, let's just attack our enemy. In this case, let's deal damage to the target health instantly. So let's do it just like we did on the bullet. So let's actually go onto the bullet mover system. And over here, let's see how we are dealing damage. And yep, that's it. Very simple. We get the target, deal damage, and fire the event. So up here, same thing. Let's grab the target and then just deal the damage amount. So that kind of means we also need to store the damage amount. So over here on the melee attack, let's store that public hint for the damage amount. And we also need it on the authoring component and then down here. So damage amount, authoring.damage amount. So then over here, we can just go into the melee attack and read damage amount. Apply that damage to the health, fire the event, and yep, that's it. So just like this, it should first test if it has a target. If so, then check distance. If too far, move closer towards the target. If close enough to attack, then stop moving and actually attack. Okay, so let's save everything and let's test. Here in the editor, let's just make sure that the zombie actually has quite a bit of health. So let's keep just one zombie. Let's get rid of the other ones just temporarily. Let's put that one on authoring, and let's see for our health component, let's put it with 10,000 instead of 100. And on the melee attack authoring, let's also make it give some damage, but let's apply it on the prefab itself. Let's give 10 damage. Okay, with this, let's test. So here we are. Let's take one of these soldiers, get close enough for the zombie to start chasing me. And there you go, the zombie's chasing me, the unit is attacking, and now as the zombie gets close, and yep, there you go, as soon as he gets within range, it does indeed deal damage. Alright, awesome. So yeah, part of logic, as you can see, it is already working. Thanks to reusing our find target system, thanks to that, and our knowledge of dots, based on everything we've already learned in this course, because of that, we managed to build this new interaction actually very quickly. And just for fun to see the adaptability of dots, let's do something funny here. So let's take one of our soldiers, and let me just duplicate it, just to make a nice fun test. Let's put it over there near that one. And on this soldier, let's go down and get rid of the shoot attack authoring. Again, I'm just modifying this soldier just for a quick test. I am not modifying the actual prefab. And now let's set the melee attack authoring and set pretty much the same thing. So that and let's say 100. Okay, yep, like this, let's test. And yep, there's our melee soldier constantly going towards the other one. And yep, both of them are indeed dealing damage. So yep, it works. This is how easy it is to change behavior when working with a data-oriented design. All it really depends is just what components are attached to the entity. So if you change what components are on a certain entity, you can easily change its behavior. Okay, so that's great. Now let's cover the potential issue with distance that I mentioned a while ago. So this is working. The zombie gets close enough to the soldier and attacks. That works. But now if we see something, first of all, let's get rid of this testing soldier, okay? And let's actually grab another one of these soldiers for testing. Okay, this one, going to use this one for testing. And on this one, let's say that this, instead of being this soldier that we have right here, this is actually meant to be the tank unit that we're going to create later on in this course. So let's say this one actually has a big collider. So over here on the capsule collider, right now it has the same size as that. But let's say the size is actually super big. So let's say it has a radius of 4. So yep, this is supposedly how big the unit is. Again, eventually we're going to create some tank units which are going to have roughly this size. So if we do this and we test, let's see exactly what happens. Okay, this is the big one. Let's move closer and see. Okay, the zombie is coming in and nope, there you go. That is what is happening. The zombie is constantly basically pushing the soldier down. It never gets close enough to attack. The issue is because the size of the collider. If the collider is big enough and the soldier is trying to get within 2 units, but because the collider is too big, it can never get there, so it's constantly moving towards the same position, constantly trying to push it. So this is the issue we need to solve. We need to make sure that the melee attack logic is not dependent on the collider size. So here on the melee attack system, on the logic for testing if we should attack, here we can't just test for distance, because this will break if the colliders are too big. And at the same time, you might think, okay, over here, so the solution is make it too big. But if so, then it will look broken on a smaller collider. It won't do a melee attack from like a mile away. So the solution is to not modify distance here. This one is good. The solution is to actually have 2 checks. We can have a simple distance check just because it is super simple, super fast. So let's put pretty much like this. Let's define a bool for is close enough to attack. And it will be close enough if this one is under the melee attack distance. Okay. And then on this one, let's just replace not if it is not close enough to attack, then target is too far, move closer. If not, it is close. Okay, great. And then let's define another boolean. So boolean, let's call it is touching target, and let's default this to false. And then let's check if it is not close enough to attack, if not is close enough to attack. That means it is not within the attack distance when calculating just distance itself. So that might mean that it is generally too far, or it might mean that it is close enough to attack, but the collider doesn't let it get close enough. So over here, let's do that test to see which one it is. And the way we are going to define whether we are close enough to attack is, like I said here, is by testing if we are touching the target. We're basically going to do a raycast starting from this unit going towards the target unit. We're going to do a raycast just a tiny bit bigger than the collider for this unit. And basically if that one manages to hit the target, then we can assume both units are touching each other. So yep, over here, let's do a raycast, which means we need to get the physics world singleton. So let's do that. So system API call get singleton, get the physics world singleton, get this one. So that's the physics world singleton like this. Then we're going to grab the collision world, just go in the physics world singleton and grab it. Okay. So now we have this collision world, and over here, we just want to do a raycast, meaning we just want to do .cast ray. And this one takes in a raycast input, so let's construct it. So raycast input for the raycast input, and let's make a new one like this. Now this one takes a start, and for the start, we can start on the origin of this unit. So let's do local transform. Let's read the value of the position, okay? And then for the end, for this one, we need to know the size of the collider for this unit. Now we can either up here add some components in our query for the physics components and use that to get the actual collider, but that can become a little bit complex given how we might have different collider shapes. So instead of that, the simplest way is really just add another field in our melee attack. So over here, let's just add that. So a public float for the collider size. Yep, like this. And let's put it on the baker and pass it in. So authoring.collider size. With that, we can now go back here, and we just need to get the direction towards the target, then multiply that vector by the collider size, and eventually we have our end position. So let's define a float3, call it the direction to target. And for this one, target local transform, sort of the usual thing. Let's grab position minus this unit's position. Okay, we have the target, and let's normalize it. So math.normalize. And then down here on the end, so the end position is going to be the current position plus direction to the target multiplied by, let's go in the melee attack, and let's read the collider size. And yep, just like this. Although like this, if we input the exact same collider size, then it's going to be mathematically perfect, just barely touching it. So let's add a little bit of an offset, just to make sure that we have the actual collision being tested. So let's give it just a little bit of extra space. So up here, let's find a float for the distance extra to test our raycast. And let's put it at something like 0.4f, so that should be more than good enough. So up here, let's multiply direction by the collider size plus our small offset. Okay, so that should do it. Finally, we just need the collision filter. Now here we could reuse the same thing that we already used for doing a collision filter just for the units. But instead, just for fun, let's actually hit everything. Let's do that just to be a little bit different and just to see how we can use these super useful constants. So instead of doing a bunch of things with min-masks, instead of that, we can just go inside collision filter and we have two constants. We have default and we have 0. So 0 doesn't hit anything, whereas default, this one makes the raycast belong to all layers and hit all layers. So yep, we can use this one in the scenario just like this. That's our input. Let's pass it in over here. And then for the other one, we can either go with this version, which will just return a single thing that it hits. Now this will likely work, but when we have a ton of units, we might actually have some units close to other units. So for example, if two zombies are attacking a soldier, it might actually hit first the other zombie that is near it, as opposed to the soldier. So instead of this version, let's go with this one that basically has all the hits. So that requires us to create a native list of Raycast hits. So let's build exactly that. And let's build it up here so we can then reuse it. So the native list of Raycast hit. So the Raycast hit list. Let's construct it with allocator.temp. Okay, that's our list. And now in our Raycast, before we do it, let's make sure to clear our list and put it in over here. This one has the ref keyword, don't forget that, just like this. Okay, so now this one will return true if it hits at least one thing. Then all we need to do is just cycle through this entire list and see if what we hit was the target that we're looking for. So let's do for each on the Raycast hit, in the Raycast hit list. Cycle through all of them, and now we just check. In here we have the Raycast hit, we have the entity, this is the entity that we hit, and really just check if this one is a target. So let's check if this one equals the one that is on target, on the target component. So let's read the target entity. If so, then we have Raycast hit target. That means we are close enough to attack this entity. So here we can set our boolean is touching target equals true, and let's break out of the cycle. Okay, yep, just like this. Then down here for the logic, if it is not close enough to attack and is not touching the target, then that means the target is too far. Whereas if it's either close enough to attack or is actually touching the target, touching the collider, if so, then we're going to do our regular attack logic. So that's it. Basically, we have two checks, just a simple distance check, and then we have a more complex Raycast. With this, we should be able to attack regardless of how big is the size of the collider. So let's go ahead and save both of these. Then over here in the editor, let's choose our zombie unit prefab. And on this one, let's set the collider size. So let's see. Yep, here we are using the capsule collider on 0.5. So let's try using that value and let's see. Okay, so there they are. This is the one that is actually pretty big. Let's get close enough and see if that one starts touching the collider. And if there you go. As soon as it starts touching the collider, even though the distance is still pretty far, yep, it does consider it to be close enough to attack. So yep, that's it. Even with a soldier that has a giant collider, the zombie still does a melee attack as long as it's touching the target collider. Alright, awesome. So here, let's just get rid of this testing unit. And on this zombie unit, let's just revert it back. So up here on this component, let's revert those changes so it has the same amount of health. And on the zombie unit, let's make sure the prefab is all set up correctly. Yep, it does seem correctly. So let's just enable the other zombie unit and this zombie spawner and let's test. So yep, here we are and a bunch of zombies. Let's let a bunch of them spawn. Yep, there you go, a bunch of zombies. Now our soldiers go in, start shooting. So the soldiers attack the zombies, but now the zombies also attack the soldiers. So they get close enough, they start dealing damage, and a bunch of soldiers are going to start dying. And there you go, they're starting to be overwhelmed by all of these zombies. And yep, everything does work. So now the zombies are not just there to catch bullets, they can also actually damage our units. Okay, awesome. So with this, we have two factions that can fight each other. So a lot of our systems are already working great. Now, one annoying thing is we still have the soldiers getting stuck while attacking. So here, if I try to control one of these soldiers, I can move it around, okay? But if it has a target, nope, I cannot move it. So let's finally solve that. We need to create some move override logic. So let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to create a move override component so that we can keep giving orders to our units even while the AI is trying to attack enemies. So we basically want to manually override the AI state. Okay, so here we have our units. Everything works great, but when they get close enough to attack, as soon as they are within range, they start attacking and I cannot move it away. So as long as they have a target, then I can no longer control the units. We want a way to be able to override that default AI movement. But before that, let's actually solve one small annoying thing. So right now, as soon as we hit on play, right now the units by default, they're all going to 0, 0, 0. Now that's because that's the default float3 value. Later on, when we create buildings and set up unit spawning, this is not going to be an issue. We're going to give the unit a relevant position as soon as they are spawned. But for units that we are placing directly in the subscene, for that, we want them to be able to stay exactly where we dropped them. So let's just quickly solve that. We really just need to make one special component that basically only exists for one frame. It will set up the unit, set up the target position, and destroy that component so it only runs once. So yep, let's do exactly that. So on the authoring folder, let's create the new model behavior. Call it setup unit mover default position authoring. And then over here, let's do the usual stuff. So public struct setup unit mover default position. It's an I component data. And let's do the classic baker so we can add it to the unit, just like this. And if that's it, we do not want any data. This is really just a tag component. So that's it, let's save. And now let's attach this component to the units placed in the scene, the soldier units. Importantly, that's these units on the scene. We want this to be an overridden component. We do not want it to apply to the prefab. Like I said, later on, for units that we're going to spawn dynamically, we're going to give them default positions as soon as we spawn them. So we only need this special component on the ones that are spawned on the subscene. So up here, let's just drag our component. That's it, nothing else. Now let's make the system to run it. So a new entities iSystem. For the setup, unit mover default position system. And over here, let's keep just our update. Then let's do a system API.query. So for the query, we want to set the unit mover to the current position, which means we need the local transform. We just need to write it, so ref RO. Then we need the unit mover so that we can write to it, so ref RW for the unit mover so we can set our position. And finally, we just need our component, so just ref RO for the setup unit mover default position. So yep, these are the three ones. Let's just do it for each, including all of these. So let's write all of this. Okay, like this. So we simply want to set the unit mover. So unit mover, let's write to it. And let's write target position to be this local transform. Let's read the current position. So that's it, super simple. And importantly, we only want to run this once. So let's make sure to remove that component. Let's use an entity command buffer to do it. So entity command buffer, and as always, let's go system API. Let's call get singleton to get the end simulation, the singleton for that one. And let's create the command buffer using state.world_unmanaged. Okay, we have the entity command buffer. So we set up the unit, and then we go here and we call remove component and remove this one, the setup unit on this entity, which means we need the entity reference. So let's add with entity access and add the entity over here. So entity. And yep, let's remove this component on this entity. So yep, that's it, super simple. This logic will run just once because we are removing the component, and it's going to do whatever setup logic we want. Now let's add a quick log just to verify. So up here, debug.log. And it's actually not the debug inside diagnostics, but the one inside Unity engine. Let's do this one, say just setup, and let's make sure this one only runs as many times as we have units in our scene. Okay, let's test. And if it works, the units did stay there, and over here we can see the setup did only run for as many as we have units. All right, awesome. So this, by the way, is a great example of how you can do any kind of setup that you want. You can just make a tag component and then have a system that goes through that tag and removes that tag at the end, meaning it only runs whatever setup you want just once. So yep, this works, it's all fine, great. So with that done, now let's make the move override. Let's begin by making the authoring component, so a new model behavior. Call this move override authoring. Okay, here let's write the usual stuff, so public struct for the move override, I component data, and inside we really just want to store a float3 for the target position, just like this. And now let's make the class for the baker and add component on this entity, a new move override. And now here, let us not write the target position over here on the authoring. This one is really just going to be set by code, so we don't need to add it here. So this target position is what will override the unit mover's position. And like name implies, this one will be an override, meaning we want to essentially force the unit to go to this position. But after it's done, we want to essentially disable this move override and go back into the usual AI. So for that, let's also make this an I-enableable component. That way we can enable or disable it. We enable and set target position, the unit gets there, disables this, and continues growing on with the rest of the logic. And by default, enableable components start off as enabled, but for this one, we want to start off as disabled. So let's set the component enabled on the move override on this entity, and let's set it to false. Okay, yep, just like this. Let's save. And now here in the editor, let's add it, but we want to make sure to add it just to the soldier unit, so don't add it on the base unit or the zombie. Only the soldiers can have the move override. So let's add the move override, and yep, just like this. Okay, so now let's make the system that is going to run this. So on our systems, let's construct a new iSystem called the move override system. And now here, let's keep just our update. Let's do our system API.query. And let's query, first of all, for the local transform so we know our position, and let's read it. So ref RO for the local transform. Then we also need to read the move override so we get the target position. So ref RO for the move override. And of course, by adding this, that means that this query will only run when the move override is actually enabled. And finally, we just need our unit mover component. We need to be able to write to it. So ref RW for the unit mover component. Okay, yep, like this. Let's write the for each for all of these. Okay, so now here for the logic, it's actually pretty simple. First, we test the distance towards the target position. So math.distance, or actually let's use the distance squared, from this local transform dot value RO dot position. towards the target position, which is the move override value arrow target position. Yep. And we check if the unit is too far. So let's actually use the constant that we have on the unit mover system, the reach target position distance squared. So if the unit is too far from this distance, if so, then we want to move closer. And if not, then we have reach the move override position. So if it is too far, then we want to move closer. So just go into the unit mover, value RW, set the target position to be the move override, the target position. And when we get there, when we do, we really just want to disable the move override. So for doing this, we can actually learn something very useful. Over here to disable this component, we can use the system API and call set component enabled. So you can do this on the move override, pass in the NT reference and set it as false. So we could do something like this. However, there's actually a better, simpler approach. It's actually over here on the query. So we can query for refRO or refRW. Those are references to our components. But then we also have another special type called enabled. And we have enabled refRO and enabled refRW. This one basically lets you read or read and write the actual enabled state of that component. So if we do enabled refRW of the move override, this will actually give us the move override enabled component. And now with this one, we can very easily either make it enabled or disabled. So in this case, to disable it, let's access the value RW and just set it to false. And if that's it, this one will disable our component. Okay, so just like this system should be working. So let's save it. Okay, so here we are and we have all of these units. And if I take one of them and let's look in the inspector in runtime mode. And now here scroll down, let's see, yep, here we have the move override and target position is defaulting to 000, yep. And we can see that the unit is not on 000, so it is not moving towards this move override position. And now as soon as I enable this, if there you go, the unit starts moving, starts going towards 000, and then let's see what happens. And if there you go, as soon as it gets there, it sets that one back into false. Alright, so yep, everything is working. Now let's just set this component through gameplay. We want to set it when we give the unit an order. So over here on the unit selection manager, let's go down to where we are doing our right click in order to tell it to move. So over here, we grab the unit mover and we grab the select component. So instead of setting the unit mover directly, instead of that, let's get rid of this. And let's add with present. We need to say with present just in case the move override is not already enabled of move override. Then here for the component, again, we are not going to modify the unit mover, so we can just replace this with the move override, replace all of these references. And let's also rename this. So here we can use the super useful Visual Studio shortcut to rename, and we'll rename all of them. That's the move override array. And this one is the move override. And yep, same thing. We go inside the array, we grab it, we modify the target position, and then we save it back onto the array. See if that works, except over here, we are not enabling it. So let's also go to the entity manager and let's set the component enabled. It is going to be on this entity. So let's grab the entity array on the same index, set it to true, and it's going to set it to true for the move override component. Okay, yep, that's it. So we assign the target position correctly and we set the array and we set the move override to enabled, which will then make the unit go there and keep going until they get there. So that's it, let's save. Okay, so here we are, let's inspect that unit and scrolling down, we can see the move override is disabled. Now as I right click, yep, there you go, it does get the target position, does get it enabled, and when it gets there, it becomes disabled. So yep, that one is indeed working. However, now if I spawn some zombies, let's see, so spawn some zombies, this one get closer, now try to move, and nope, I still cannot override it. Now this is actually easy to solve, we just need one more thing. It's over here on the shoot attack system, so we have our query, which does our AI logic for shooting the target. And essentially what we want is we want to make sure we only run this logic when the move override is not enabled. So up here for our query, let's set the option with disabled for the move override, meaning this logic will only run if the move override is disabled. If it is enabled, then just leave it do its thing. When it becomes disabled, then runs this logic. So yep, that's really all we need. And let's also make sure to also add this on the melee attack system. Exactly the same thing, just like this. So let's save it. Okay, here we are with a bunch of soldiers and a bunch of zombies. Get close, get them all close enough to start attacking. And they get close, they start shooting, and I click to move, and yep, it does work. I can control them, tell them to move, they go back, they start shooting, and everything works. Alright, awesome. However, in implementing this, we broke the melee attacks. So we already implemented the melee attack logic, but right now, if I approach one of these enemies, if I get really close, and nope, the enemies are not attacking the player. They are no longer running the melee attack logic. Now the reason for this is because we implement the move override, so that's how we can have some target, either a shoot target or a melee target, and we can still override the movement. And when we implemented that, we messed up over here the melee attack system. We can see here on the melee attack system, and basically it's over here on the query. So on this query, we added with disabled move override. This means that units will only do the melee attack if they have no move override active, which makes sense, that's what we want. But like this also means that this query will not match anything that does not have a move override component. So this query works great for player units that do a melee attack, but does not work well for the enemies because the enemies do not have the move override. Now to fix this, we have two options. We can either add some logic to make sure that this really only stops the friendlies from attacking. So we could remove the with disabled over here and simply add an extra logic and check if this entity, if this one does have the move override, is it disabled? We could go with that option, or we can simply add the move override to also the zombies. Both those options work great. Let's do the easy one of just adding the component to the zombies. This might also be helpful later on in case we want to force a zombie to go to a certain place. So if we just want to add that component to all of them, let's go inside our prefabs. And to modify all of them, let's make sure we want to modify the base unit. So on the soldier itself, let's go down, and on the soldier, let's get rid of the move override. We don't want that one. Instead, we want to add it to the base unit. That way it gets attached to all of them. So the move override authoring, just like this. Okay, that should do it. So let's test. Okay, here we are, and if we approach the zombies, let's see if they come to attack. And if there you go, they are now running the melee attack logic. Alright, awesome. So here we have added a really important move override logic. Right now, with this, we have full control of our units. We can tell them to move, we can tell them to attack, and we can override their AI in order to move to a different place. Hello and welcome, I'm your Code Monkey, and congratulations on watching through this entire free course video. Here you'll learn a ton about how Unity Dots works and how to make an awesome RTS game. You'll learn what exactly is Dots, how to create entities, components, and systems, and how to make it all super fast with the job system and burst. With this knowledge, you can now go make some super awesome games that push the CPU to the absolute max. If you want to continue this project, then you can check out the link in the description. The full course is 17 hours long, so 10 hours more than this one. It is split across 18 lectures. So in the remaining lectures, we're still going to learn a bunch of really awesome stuff. For example, how to make a custom dots animation system, build that from scratch. We're going to learn how to implement a grid system in dots, again, all data-oriented. And we're going to implement some nice flow field pathfinding. This is a super awesome type of pathfinding. It is absolutely perfect for games like this with tons of units. We're also going to learn how to refactor a ton of the systems that we built and make them into super fast bursted jobs. Then we're going to learn some awesome stuff like how to make a persistent fog of war system. This one looks really cool. How to add some buildings to the game, add resource nodes, super fun ragdolls, and a bunch more. So the remaining lectures in the complete course, they are full of awesome knowledge. Check it out through the link in the description. But if you can't afford it, then that's fine. I hope you'll learn a ton from this awesome free video. Here you'll learn more than enough knowledge to start applying dots to your own games. Now you have knowledge of this super awesome tool that will help you whenever you encounter any kind of performance issues. Also remember how you don't have to go full dots or full game objects, you can mix them both. So you can keep making games mainly with game objects and then use dots just for the performance intensive parts. Remember how dots is really just another tool in your tool belt? And now you know how to use this really awesome tool, so definitely make sure you use it wisely. Alright, so I hope you learned a lot from this free video. Go ahead and like the video and subscribe if you haven't already. Thanks for watching, and I'll see you next time.